from that group,
All right,
and
I'm going to record.
unfortunately, I failed the test the first time. So this is going to be my second time trying.
Yeah. Well, are you taking lots of practice tests?
Oh yeah, on hamstudy.org. Yeah.
Uh,
Unfortunately, with my disability I have, the medications I take and stuff cause me brain fog and it kills me. But I'm determined.
well, do you find that you can study smaller amounts easier?
And that's what I started doing. Yeah.
Yeah.
I started taking smaller chunks.
Uh-huh.
Yeah.
Okay. Well, all right. So we're at 43. Like I said, about 100 people sign up. So we'll see. Um, so good
It's,
morning. My name is Scott. My call sign is N7JI, and I'm gonna test out the whiteboard here, and I'm gonna share my whiteboard, the whiteboard that I hate. Here we go. And like I said, the whiteboard that I hate. We'll see if I can get it to work. Okay, so that's my call sign, N7JI. Can everybody see that okay?
yes.
And when I do this, do you see a little
Yep.
cursor of me trailing along?
Yep.
Oh, okay. Well, that's kind of annoying. I don't want it to do that, but um, okay. But everybody can see it, and there's not like a million cursors on the screen.
That's correct.
Thank goodness. Okay. All right. So that's the whiteboard that I'm gonna use frequently, and I just accidentally exited the meeting. Apparently, that button is a little too close to the other button. Okay, I need to make sure that I disconnect from audio here because I don't want to stay co-host. Disconnect audio. Okay. So anyway, my name is Scott. I live in Eugene, Oregon, and I've done a lot of these classes. I really enjoy teaching it. My way of giving back. The reason I do it for free, a lot of people say, why do you do it for free when you could charge? The reason I do it for free when I could charge is because long ago I had somebody who taught a free class, and I took the free class, and it worked out really well. And um, and ever since then, I've thought, I should teach classes for free. This is my way of giving back. So, um, so what we're going to do today is we're going to cover a lot of material. And in fact, today is the hard day because today is 7 hours minus lunch. And tomorrow is, I believe, 4 hours and no lunch. Um, and what's going to make this interesting is the fact that I like to keep it uh, very lively. I like to have people ask me questions. So if I happen to be talking about something, feel free to interrupt me. Don't have to raise your hand because I'm not usually looking at the little hands up thing. So I would ask that you keep yourself muted unless you have something to say and pay attention to that because otherwise, somebody might have a dog barking in the background and that can be really loud or a TV in the background and things like that. So just keep track of yourself. Um, and let's see. The other thing is that did everybody get the information packet that I sent out, which had all the links and all the books and all the
If it was called materials, I did.
yeah, okay, good. And one of those things was this book, which looks just like this.
No
Ev-
nonsense.
Everyone recognize that?
No, actually.
No,
That was
no.
Yep.
that was
As
in that was in
Yes.
the information packet.
Yes, that's awesome book.
Yeah.
so when I clicked on it, it gave me a different one, an orange one.
No nonsense. General class.
Yeah, the
Okay.
general class. You had to scroll down to find the free one.
Got you.
Yeah. It's confusing. It takes you right to that general class, and you have to keep scrolling to get
Mhm.
the
Right, but it was
class.
I also included it in the information packet.
Yeah, there's a separate link
That's
that
a zip file at the very
yeah.
bottom in the
The very
materials.
bottom.
In the materials, if you open up the materials, you've got like 11 zip file. You've got a zip file with like 11 things in it, and one of them is that book.
Gotcha.
And it's also, you can download it for free. It's also a free PDF. I mean, that's how I got it. I also know the author, so I would recommend that everybody, if you don't already have it downloaded, you really need to download it because we're going to be using that. So here's my philosophy on this, that I basically teach to the book, but I move around quite a bit. And when I'm moving around, it's because I think that the flow of the book is fine, but I think that it's more important to cover the radio theory first, wave theory, do some of the math, and then from there, that sort of like bridges into the electronics. So I mix up the first few chapters of the book a little bit. And once we're on about page,
Scott?
I don't know. Yeah. Yeah.
I am looking back at your emails right now, and I don't have a material like you described, a zip file. I've got the Zoom, I've got the book, I've got exams.
Okay. All the way at the bottom to be an attachment.
Yeah, Scott, this is RC. I ran into the same issue, and actually, I ended up ordering the general book from Amazon, and
Okay.
eventually, I did find your link.
Okay, so Luetta, right?
I did not receive anything, Scott.
You,
Nothing beyond this thing to connect to the Zoom
hey,
today.
all right, let me go out and make sure that everybody's got it. I'm gonna forward you.
Thank you,
Just
Scott. I appreciate it. This is Luita.
just make sure you're looking for the May 5th email because he did it from a slightly different email address. The ARS.N7JI is the one with the attachment. His other two emails use his full name and his call sign. But the
Really?
one with the attachment, May 5th, or at least for me it was May 5th, but somewhere around that time period, ARS.N7JI.
Okay, so
ARS.
okay, wait. So who else needs it?
I do.
Okay.
I do too.
Okay, wait. One name at a time.
Deborah.
Okay. Deborah. Okay, let's see. What was last name?
Jameson.
Okay. Okay. What's your email address?
DJ97107.
I have it right here. Okay. Who else?
I do.
Okay. Email.
Tweety_Tony@yahoo.com.
Okay. I have that. It's possible that Yahoo may have stripped out the zip file.
Okay.
Anything is possible. Anybody else? I've
Yeah,
got
Diane Herman at Comcast.net.
Diane Herman with 2 R's and 2 N's. Yep.
Yes.
Okay, so I've got La Femme Wolf. And who else?
Me, Tasia.
How do you spell what's the email?
RADTAZTIC@gmail.
There it is. Okay. Anyone else?
Yes. Sam.
Yep.
So it's Stone, Sam, J.
Stone Sam J. Okay, anyone else? Here it goes. Okay, I just sent it out. You never know. I mean, email servers do weird things. It could end up in your spam folder. I mean, I've had that happen too.
Mhm.
Okay. So take a look in your email. You should have it. One of the things in the email should be the book. So my philosophy on the book is that I downloaded the at one point. I downloaded the audiobook. Yes, there's an audiobook. It took 2 hours for KB6NU to read it, and he has a very strong Michigan accent. So that was fun and amusing, but it took 2 hours for him to read the whole book. And I figure I have about 10, which means I've got 2 hours to essentially read the book and 8 hours to talk about other stuff and do drawings and pictures and things like that. So my philosophy is that if you have any questions, I want you to go over it, because if you're brave enough to speak out and say, I don't get this, you're not the only one, I'm sure, who doesn't get it. So just don't be afraid to speak out and have me go over something again. I really don't mind. I'd much rather spend a little bit of extra time on something than have people not understand it. Because I'm telling you right now, if there's stuff that you don't understand, you are going to be lost for the next hour after that, at least. So I would really much rather have everybody, go over it again. And I don't mind going over it again. And I can be pretty creative as far as coming up with new analogies and things like that to try to hammer a point home. So that helps me learn, that helps you learn. So don't be afraid.
Hey, Scott, do you mind?
Yep.
It's Miranda. Thanks.
Uh-huh.
I just am on, I have moved Zoom to the auxiliary screen, which is oversized, as completely as expanded as it can be. And normally down there, you see under React and you can do raised hand. And I'm seeing everything completely expanded. Where in the heck is raised hand? What is it nested under?
I'm not even worried about it. If I can hear you yell, then you should yell.
Alrighty.
That's going to be easier for me.
Hooray.
Yeah. Okay. Here we go. So, again, my name is Scott. I have been let's see, I have a bachelor's and master's in electrical engineering from the University of Maryland. And I've been a ham radio operator since before I was in college. I got my license when I was 15. So I just went through my 40-year mark. And I'm a contester and a DXer, and I enjoy DXpeditioning, and all these things will start to make sense as we keep going. I like to operate QRP, which is very low power. I'm also the American Radio Relay League's Oregon section manager, which means that ARRL is an organization of about 140,000 hams in the United States. There are approximately 750,000 licensees in the United States. The ARRL is our voice on Capitol Hill, as well as doing training and dealing with licensing and dealing with the FCC and dealing with Congress and all other kinds of stuff. In addition to doing a lot of publishing. So basically one of the largest ham radio member organizations in the entire world. So I handle the Oregon section, which basically means of the roughly 3,000 members of the ARRL who live in Oregon, I get to be the liaison for local problems and stuff like that, where I have to talk to somebody at headquarters and try to give them answers. And I do a lot of coordination with volunteer stuff and emergency communications and all other kinds of cool stuff like that. So if you happen to live in Oregon and you get your license and you join ARRL, I am your representative. So okay. So let's start by just talking about this picture. Does anyone know what this picture is? First of all, can everybody see it?
Yeah.
Yep, got it.
Okay, so this picture is, notice on the top, we have frequency, little letter F. I will be using that all the time. On the bottom, we have a little Greek letter lambda at lower left, which is wavelength. So those are shorthand for frequency and wavelength. This is known as the electromagnetic spectrum. This is our playground that we are learning to mess with. And by the way, I'm not going to teach you how to use any particular radio. So if you have any designs on that, I don't know how to use my Baofeng, I'm not going to teach you how to do that. My goal is to get you to the point where you understand. And by the way, Diane, this is in that packet. So,
Okay.
so it'll be better resolution in the packet.
All right. Thank you.
The whole point of this class is that everybody has to get to the point, if they're going to get a license, where they are understanding enough to get a license, right? Ultimately, what has to happen is that you have to pass an exam, and I can't help you pass an exam. You have to figure out how to pass an exam on your own. What I can do is give you a little bit of guidance as far as some of the background that makes the questions on the exam make sense, right? This is what I teach is some specifics as far as rules and regulations, but I teach a lot of foundational knowledge and mathematics that makes all that other stuff make more sense. So that when you see a question, you say, I don't remember the answer, but I have an idea where to start. It's also a basis for the fact that amateur radio is so let's say that you had a license to buy a car and drive the car, right? That's essentially a driver's license. Does that give you the right to build your own car and put it on the highway? What do you think?
No.
Most likely no.
No. You'd have to go through a bunch of different processes and get it legal, et cetera, et cetera. Okay, so people will say, why do we need to get a radio license why is there such a thing as a ham radio license in the first place? I mean, you can walk into a store, or you can go online and you can buy a GMRS handheld, you pay your $35 and you can operate the radio and it works fine, right? You can go into a store and you can buy an FRS bubble pack and buy 2 radios, open the pack, turn on channel 12 and talk to each other. That works just fine. So you can also do the same thing with MERS, which is at 154 megahertz. So why is this thing called amateur radio? Why is there actually a license for it? Because when we get down to it, we are given the ability to not only buy stuff and use it, but we are given the ability to go and build stuff and use it legally. So if you go and build a transmitter, what is one of the assumptions? Let's say you build a car. What are some assumptions that you have that have to be made when if you're going to build a car and put it on the highway?
Horsepower, transmission.
Yeah, okay. What else?
Handling.
What else? Handling.
Headlights, taillights, signals.
Headlights, signaling. What else?
Make it safe.
Yeah,
Safety.
make it safe. How about everybody else on the road? How about the fact that something's not going to go wrong and a wheel's going to come flying off and you're not going to careen into a truck and cause a major wreck? So you have to play. The reasons those regulations exist is because whatever you're building has to be able to play well with everything else. If we are given the right, through virtue of getting a license, to build our own stuff and use our own stuff, even if you don't ever decide to do that, your license covers it. And since your license covers it, that means you have to get tested on it. And what it essentially means is, like, for instance, you have to understand what decibels are. You have to understand not only what decibels are, but the fact that you have a fundamental frequency, which is a single transmitted frequency, and you also have other frequencies that come out of your radio, which are known as spurious emissions, which are known as harmonics, and many other different things that come out of your radio, which have to be a certain number of decibels down from the fundamental frequency that you transmitted on. The reason being that those things that you're transmitting that you didn't decide, that you didn't intend to do, can interfere with other services like air traffic control, You don't want to mess with air traffic control. There's lots of other ways for you to screw up other things by virtue of building something that you did not build properly. And since what you built is built under essentially the auspices of your license, which was granted by the FCC, it's a big deal. And that's why there is a licensing process. Because this is not a go to the store and use it kind of thing. We are not appliance operators. We can function as appliance operators, but we are not appliance operators. Amateur radio is not an appliance operator thing. Okay, so let's go back to, I'm going to share this and let's hope it works. Here we go with a whiteboard. Okay, so the first thing I'm going to draw is this picture. If I drew it well, what is this?
A circle.
A circle. Okay, excellent. Good. Great place to start. Now I'm going to take this circle and I'm going to cut it into 4 pieces. All right. How many degrees are there in a circle?
360.
360.
360. Okay. So we start by definition over here. This is the 0 line. All right. And we rotate as we increase our angle this way. So when we get up to this point, where are we? How many
90.
degrees? We're at
90
degrees.
Okay, excellent. Okay. How about when we get over here?
180.
180. And how about when we get down to the bottom?
270.
270.
270. Okay. And then all the way over to here,
360.
which has another name.
Circle.
It's 0. Yeah. So basically we're going around and around and around and around. Okay. So what you have to picture now is the fact that you now have this thing, we'll call it a merry-go-round, where you are sitting on the merry-go-round, and every time you go around the merry-go-round, you end up right back where you started. It might be a little more nauseous than when you started, but you end up right back where you started. How many degrees in one revolution or rotation have you gone through?
360.
360 degrees. Exactly. Okay. So now what we're going to do is take a look at this circle, and we're going to try to be a little creative with it and say, okay, well, we've got this circle, and here's a picture of me. If you're not seeing the whiteboard, you just have to click on top, probably. It says whiteboard. There's a couple of different tabs. All right, so what we're going to do is change the color. Where'd it go? Come on. There we go. Okay, so what we're going to do is we're going to make... Can everybody see what I'm drawing? Okay. So what we're going to do is put me on that whiteboard, right? And here's me. And now I'm on the circle. Everybody see the little picture of me there? Okay, so now what we're going to do is we're going to, because I'm green. Okay, we're going to say, how far above or below the green line am I if this is 1 unit? This is known as the unit circle. The radius is 1 unit. So at any point in time, at any point on that circle, how far above or below the green line am I? So when I'm right here at the 0 point, how far above or below the green line am I?
0.
Here.
0,
Here.
right. I'm on the 0. And I'm going to mark that as 0 degrees, and my height is 0. Okay, how about when I'm all the way up at the top?
1.
1 unit. So I'm going to be at 90 degrees, and I'm going to be up here. How about when I get back down to 180?
0.
I'm going to be at 0 again.
Oh.
Okay. And how about at 270?
-1.
-1. So that's at 270. I'm going to be down here. I'm going to be below the line. by 1 unit. And when I get to 360,
0.
I'm going to be back at 0. If I connect the dots, because it actually is curvy, this is known as
A sine wave.
sine wave.
Yeah.
Yep. Okay. So this is now known as a sine wave. Everybody still see okay?
Yep.
Okay.
Yep.
All right. So this is known as a sine wave. Now I'm going to do another color. I'm going to make it red. Okay. And now we're talking, instead of up and down, here's where we start. And now I'm going to do left and right. I'm going to mark my 0, 90, 180, 270, 360 again. Okay, so how far left and right am I at 0?
1 unit.
I'm 1 unit. That's right. I'm starting to and it's +1 because this is plus and this is minus. So I'm up here. And how about when I get up to the top? I'm on the line, left and
0.
right, which means I'm
0.
right there.
0.
And then I'm at 180, I'm here, and then here, and here. Connect the dots. This is known as a cosine wave. Is that on the screen or is that off the screen, everyone?
No, it's on.
It's on, okay.
Yeah.
Okay. So there's a sine and a cosine. These are mathematical trigonometric functions that define the functions of a circle. These are two very basic functions of a circle. Okay, now here's an important thing to note. What happens to the left of that 0 degree mark? So here's the 0 degree mark. And here's the 360 degree mark. What
Is it going
happens?
to decrease?
No. What's going to happen? Well, do you know when the circle actually, do you know when the merry-go-round actually started spinning?
It'll repeat.
It repeats over and over and over. And how about over on the right?
The same.
Same thing. Okay. So now, how about all the way down at the bottom here? Well, this one keeps repeating. So really what we're looking at is a little chunk of time or a little chunk of position of that circle. What's one thing you notice about those pictures?
They're opposite each other.
They're not opposite.
90 degrees out of phase.
They're 90 degrees. Notice that this one is at the top up here, and this one's at the top up here. So everything is shifted by 90 degrees. And that's known as a phase shift. Phase is measured in angle. So what we have is two sine waves essentially, but to make the cosine wave, we just shift it 90 degrees. So what's important to note is that is where sine waves come from. Sine waves are generated by circular movements. And think about things in the universe that move in a circular fashion. So let's hear it. What do you think?
Earth.
Earth around the sun. Yeah. Other things?
Electrons in an atom.
Electrons in an atom. Yep. Circles are very, very prevalent. You know, stars around the core of a galaxy. So circles are really, really common. And it just so happens that if you were to look at the way that our days get longer and shorter, well, that follows a sine wave too, because we're going around the sun in a largely circular pattern, which is why when we get up to the top, let's say right up here, that would be June 21st. The days are longest, and notice we're not adding a lot of time or taking a lot of time really fast. And back in December, the days are really short, right? But you get a lot of change. That would be spring, and that one would be fall. The days get very short and very long very rapidly. And that's because your slope is bigger at those times. Okay, so now what we're going to do is clear that page. Glad to see that works. And we're going to look at other things we can say about this circle. All right, so we're going to draw our circle again. Whoop, whoop. Okay, well, here's our 0-degree mark, and we're going always this way if we're going in the positive direction. Okay, there's a couple of things that we can say about this circle.
It's a little up high.
Oh, it is a little up high.
Yeah.
Now let's do it again. I got to get used to this thing.
We can grab our whiteboards and move them around. So
Yeah,
but
exactly.
But I want to do it right. I want to make it so everybody can use it, including me. This is okay. So is that in the center more or less? A little bit to the left, maybe?
Yeah.
Okay,
Exactly.
there we go. There we go. Brand new whiteboard. Okay, so we're starting at 0 degrees and we're going up and around that way, counterclockwise, increasing angle. So as we are doing this, what are a couple of things we can use to describe the trip that we're on? How can we describe the trip that we're on other than nauseating?
Orbit.
Yeah, okay.
Counterclockwise.
Yeah, we're going counterclockwise. What's another thing we can do? What's another way to describe this trip?
Speed.
Yes, how fast? And what's another way to think about that? Like you said, speed. And there's also time.
Mm-hmm.
So now we can try to relate these things. We can say how, whoops, I don't want to do that. Yeah, you know, make sure I have an eraser. There's an eraser. Okay. So now what we could say is we have a couple of things. We have time. And notice it's not little letter t, which is little letter time. The big letter T is time, but this has another name. We use it for the period, and it's measured in seconds. That is how long it takes us to go around the circle. All right? So let us say that our period is 1 second. How long would it take us to go around the circle?
1 second.
1 second. Okay, so how many times would we go around the circle every second?
Once.
One time.
Once. That has a name. That's called frequency.
See.
Something, the number of times that something happens in 1 second is known as the frequency. And if that's true, that we could say that it's one thing happening per second. The thing happens to be one complete rotation of that circle in this case. But essentially a frequency is a measure of how many things that happen every second. So now let's change this up and say that our period is 10 seconds. How far, how many rotations would we go around every second? 10.
10.
It's not 10. It takes 10 seconds to make one full trip.
Oh.
1/10.
1/10. Yeah. 1/10 of a rev per second. Okay, so we've slowed down. And obviously there's an inverse relationship here. So the other thing we can do now is say that, let's say that our time was 1/100th of a second. Let's say we're working for NASA and they put us in the in the big G-force chair and they're spinning us around 100 times every second. Right? Well, before we black out, we realize that we're going really fast, right? Okay. So if we're going around in 1/100th of a second, how many times per sec, or how many times do we go around every second?
100.
100. Okay. Revs per second. Okay, so you notice that the per second thing is really important here. And a revolution is just a thing. All right. this actually has another name. A thing per second measured in frequency is called a hertz.
But if it's okay, and this is Meredith Sykes. I'm learning challenged with memory and processing deficits, and I'm pretty much good with that. And I thought I was really accustomed to hertz, but it would be nice to hear what you said for the 1, not the 10 or the 100, just in one bullet point in one statement. And
okay. Basically, okay. So if you have something that is happening in this amount of time, let's say time is equal to 1 second to do one thing. That would mean that it would take, you would be able to do one thing in 1 second. A thing in 1 second, that is the definition of a hertz. So what we now have is we have a relationship. The period is equal to 1 over the frequency, or the frequency is equal to 1 over the period. So if we have a period, which is t, one thousandth of a second. Our frequency is equal to 1 divided by t, which is 1 over 1/1000 is equal to
1,000.
1,000 hertz. Okay, so what we now have is something that is happening at a rate of 1,000 times per second. We have a frequency of 1,000 hertz. We could also do this, for instance. We could take our hands and I could clap them together. We'll do a slow clap, about once a second. What's the frequency of that clap?
1 hertz.
1 hertz. How about if I went?
Well, let's call it 4 hertz.
Yeah, okay, we'll call it 4. Okay, yeah. I'd say it's like more like 2 or 3, but 4 is pretty fast. 4 is, but I don't want to hurt myself. So, okay, so now that we have a relationship between a frequency and a period, we can add something to this. And what we're going to add is we're going to take that circle that we drew, and we're going to, instead of having it like this, going around and around and around like this, which is fine, we're basically making this trip. We're going to take that circle, but instead we're going to rotate it on its side. We're going to look at it edge on. And so now that we are, shoot. Like I said, it's going to take some getting used to. Okay. So here's our circle, and we're going to start like this, and we're going to start to rotate it so that we're looking at it edge on. As we do that, it's going to look more oval. And as we go further, it's going to look even more oval. And what's going to happen when it's totally edge on?
Straight line.
Straight line up and down. Okay. So if we are able to see the person, me, riding around the circle like this, what will happen when the person is on what looks like a narrower and narrower oval?
You're just moving up and down.
You're just moving up and down. That's right. So now what you will see is me just moving up and down because you don't see the depth. Okay, so now I'm just going up and down. How fast am I going up and down? At a given frequency and a given time period. That's how fast I'm moving up and down. If the circle is spinning at, let's say, 100 hertz, How fast will I move up and down when you look at it edge on?
100 times a
100
second.
times a second. Okay. So now what we have done is we've taken this moving circle and looked at it edgewise. And so what we're going to do is we're going to take this, which is moving up and down, me, on the circle, moving up and down. But instead, what we're going to do is very slowly advance the circle to the right at a different speed altogether. So as I'm moving up and down, what will happen to the picture? My
create a wave.
Yes, my motion is no longer just like this around a circle, but now I'm moving through space, and what I actually make is a spiral pattern. Except that we can't see the spiral pattern because we can't see me moving into and out of the page because that doesn't work. So instead, what we have is a picture of me doing this. As this thing is moving to the side. Everybody agree with that?
Yes.
Really, I'm going into and out of the page, but you can't see that because because the circle's turned on its side. So it's like what happens if you hold a bicycle wheel and spin it and you're looking at a piece of tape on the wheel and then you slowly move it to the side. It'll make an up and down pattern. So now we have a couple of things happening here. This has an inherent frequency that we've given it. And what have we also done? We've created a velocity by moving it to the side. And what do we measure velocity or speed in?
Time?
Meters per second.
Yeah, a distance per second. And we usually do in the meters, kilograms, and seconds realm, we do meters and seconds. So in this case, our velocity is in meters per seconds. And what is our frequency measured in? Do you remember that?
Hertz.
Hertz, which is also known as 1 divided by seconds. It's things per second. Okay, so what do you notice that's common to both of them?
Seconds in the denominator.
Seconds in the denominator. Yeah, you have 1 per second over here and meters per second over here. So the great thing about math is that I can do things in math that I say I want to do just because math lets me do that. So what we're going to do with this math right now is we are going to divide, just because I say I want to, one by the other. And in fact, what I'm going to do is up at the top, I'm going to say I'm going to divide my velocity in meters per second divided by my frequency. Really, this is one wave. Now, because this makes a wave pattern per second. And I'm going to arbitrarily divide those one by the other and see what I get. Well, what do you notice about those per seconds? They cancel out. So now I'm left with this new thing called a meter per wave. So now let's look at this wave. And what does that really tell me? That one wave that I just made takes up how much distance?
A meter.
Or however many meters I decided it was going to have. And how does that change? If I change the velocity, that changes the number of meters per wave. So this is actually like pretty profound because we just decided we're going to create something out of the blue. That has a name. that has the Greek letter lambda. And that is our wavelength. It's meters per wave. I mean, that makes sense that it would be a wavelength. It's a physical distance. So what we can do with this now is, let's say that we have a wave that we're going to draw. And we're going to start with a circle. And this circle is going around and round, which turns into this going up and down. And we're going to say this has a frequency of 440 hertz. So the thing that's making it is going around 440 times every second. Any musicians out there? Anybody? You know what 440 hertz is?
A.
That's an A. That is a concert A. Okay. Okay. So that's an A. So now what we're going to do with this is we're going to allow this to go toward the right at 330 meters per second. Okay. So because we are allowed to by math, we're going to do a little division and say that this is our frequency over here. And this is our velocity, 330 meters per second. And we know that we already calculated, we defined this other thing, which is wavelength. And that is in meters per second. So we have to arrange the other stuff so that it comes out in meters per second. So we're going to say, velocity divided by frequency. Because, again, math is awesome, and math allows us to do that. So we then have 330 meters per second divided by 440 hertz. And remember, what does hertz mean?
Happens 1 per second.
Right. And those are actually cycles or a wave. So it's 330 meters per second divided by 440 waves per second. So we do some division and we get, what's our wavelength?
0.75.
So any idea what this 330 meters per second is?
Speed of sound, if we're
Speed of
talking music.
sound. Yep. That's the speed of sound. So if you were to play a concert A, which is 440 hertz at sea level, you would find that the wavelength that it made was approximately 3/4 of a meter long. Anyone play a woodwind? Come on, raise your hand if you play a woodwind instrument like I do.
My son I used to play a saxophone.
Okay, saxophone. What other woodwinds?
I've dabbled in didgeridoo.
Okay, didgeridoo is tough though, because I don't know if you can tune a didgeridoo. Anyone else play a tunable woodwind?
Well,
Clarinet. Clarinet. Okay. What happens if your pitch is too low?
Oh, I haven't touched it in a long time. I don't
Yeah,
remember.
but what do you do if your pitch is too low to tune?
Push it in the mouthpiece.
That's
You
right.
shorten it.
You shorten it. By shortening it, that changes the resonant column and that changes the frequency. I used to play the flute. Same thing. You shorten the instrument to make it higher, you lengthen it to make it shorter. That same thing works in radio, believe it or not. Because what we're going to find now is we are no longer talking about sound. Sound doesn't go very fast. Also, sound doesn't travel through space very well. It requires a medium to go. So what we're going to do instead is we're going to change from a pressure wave, which is like sound, And we're going to instead draw that circle again. Here's the circle. And we are now going to say that this has two functions. It has a sine and a cosine. Which is how far up and how far down and how far right and how far left. Well, once again, we're going to take this and turn it on its side, but we're not going to completely eliminate the fact that we can see it. So we're going to have to draw this in 3 dimensions. So this is going to get a little bit tricky. So what we have is we have this. So we have our circle going around here. Around and around and around. Okay? We now take this and we move the whole thing this way. And that does, in fact, make a spiral pattern. And so, because we are now concerned about the fact that we can actually see all three directions, that makes a spiral pattern as it's going like this. Okay. So, we are now, instead of sound waves, we are talking about a different kind of wave. There are 2 different portions to a wave that is generated by an electron moving in space. So instead of just me, we're going to put a charged particle, like an electron, which is going around and around and around. It could be contained in a piece of wire. It could be just about anywhere. And what we now have is, as an electron moves, it makes two different distortions in space. It makes an electric field and a magnetic field. Those together form a wave as we move things in space over time. That wave is called an electromagnetic wave. And what is really interesting about an electromagnetic wave is that it has 2 components. One component is an electric field, and the other component is called a magnetic field. They're exactly what we think of when we think of electricity and magnetism. What is interesting, however, is that due to Maxwell's equations, the electric field and the magnetic field, and yes, we use the letter H or B for the magnetic field, are always perpendicular to each other. So if the electric field rotates 180 degrees, the magnetic field will rotate also. Now, what's also important is that as those electric and magnetic fields exist, and they're moving in this way, we have something called an S vector, which is the pointing vector. This is the direction of energy flow. These are all perpendicular to each other. And if you want to kind of understand how that works, all right, everybody put up your right hand. It can't be your left hand, because if it's your left hand, it won't work and it'll be backwards. Okay, so your thumb is the electric field. Your index finger is the magnetic field. Okay, those are perpendicular to each other, right? Okay, now you stick out your middle finger so that it's perpendicular to all 3. This is known as the right hand rule. So electric field is your thumb, magnetic field is your index finger, and direction of energy flow is your middle finger. And you can see that if you keep your middle finger in one place and you rotate the electric and magnetic field, they always stay proportional to each other. The other thing is, if you keep the electric field in the one direction and you rotate this, then by changing the magnetic field, you change the direction of energy flow. They always have to follow that basic rule. Okay, so now
That's a great bullet point. Will you just say the bullet one more time? If you change the blank, it does blank. Thanks.
well, just hold your hand up.
Yeah, got it.
Just hold your hand up and hold one of them so all it can do is turn. It can't move. It can just spin. If you whichever one you hold so that it's only fixed in one direction, the other two have to maintain their relationship to each other. So if you hold the energy flow still, so it's always moving this way, then your electric and magnetic fields are always in proportion to each other and at right angles. If you hold your electric field like this by holding your thumb, then the magnetic field and the direction of flow are always at right angles to and proportional to each other.
Okay, and it goes electric, thumb, magnetic index, and direction metal.
Yep. And that is the basis. That is the basics of what Maxwell came up with as far as energy flow and electromagnetics. So now, once we've established that we have these electric and magnetic fields and they are moving around and around and around in a circle, they basically look like this. So let's say this is our electric field, and it's going to follow the pattern of a sine wave because remember we have a moving circle. When that peaks at that same point, we're going to do this. This is the magnetic field. It's getting to be kind of a mess, isn't it? I'll try it a different color and see if that helps. Okay, here we go, magnetic field. So that they are peaking at the same point in time. And notice that they are always shifted a quarter of a way around the circle from each other. Okay, so what are some things you can use to describe this wave as it's traveling in space? What are some things you can use to describe it? Take a look at what I've drawn. What are some things you can change?
Speed.
Yeah. No, actually, that one thing that you can't change. I mean, you can, but for all intents and purposes, we have a speed of c. And I didn't cover that yet, but that's a really good one. What is c?
Speed of light.
Speed of light.
Universal constant.
Yep. 2.998 times 10 to the 8th meters per second, or roughly 300 million meters per second. That is the speed of light in free space. Okay, so now it's important to note that these electromagnetic waves, have I said anything about what they are yet? Other than distortions of the electric field and magnetic field in space. Have I said anything about them? Could you measure it?
Yes, you could measure it.
Okay, and what would that be? What is that? What is the name of that length?
Wavelength.
Wavelength. It's a wave, and it has a length. So that's a wavelength. That's our little Greek letter lambda. What's another thing we could do? How do we change that wavelength if the speed doesn't get to change?
Frequency.
We could change our frequency, how fast the thing is going around in circles. We could change our frequency, f. So those we know are related to that velocity. Because if you increase the frequency, you decrease the wavelength. And if you decrease the frequency, you increase the wavelength. And that formula is C is equal to F times lambda, which actually is that same, very same thing that we did when we did V is equal to, lambda is equal to V divided by F. When I did that arbitrary division thing, turns out that what I was doing was developing the relationship between the speed of light of an electromagnetic wave, the frequency of the wave, and the wavelength. So what we've now done is we've now equated a wave to moving energy through space, and we have this formula for it. C is equal to F times lambda, where again, this is the speed of light, and this is your frequency, and this is your wavelength. This is measured in meters, this is measured in hertz, and this is in meters per second. So most importantly, all the units work out and everybody's happy. We can actually take this and we can draw this in a circle. This is one of those mnemonics that I typically use, where I go C, F, lambda. All right. So if I don't know something, I cross it out. So that means that lambda is equal to what's left. I have a division sign, C divided by F. So if I were to say for a frequency of, let's say, I'm going to erase that, frequency of 300 hertz. I'm going to redraw this. Lambda is equal to C divided by F. Okay, so what is the speed of light?
300,000 meters a second.
300 million meters per second. And what is our frequency that I've just set up there?
300.
300
hertz,
which is 300 times per second. What is the resulting wavelength?
1 million.
100,000 meters. Oh, 1 million. Ooh.
Or 1,000 kilometers per second. Or sorry, 1,000, whoops. Erase that. 1,000 meters. 1,000 kilometers. So a wave that has a frequency of 300 hertz has a wavelength of 1,000 kilometers, or about 620 miles. So we're talking pretty big things, right? Well, how do we shorten that up? How do we make those numbers make a little more sense? Let's go with a different one. Instead of 300 hertz, let's go with a different frequency. Let's say 300,000 hertz. Okay, so now instead of 300, we're plugging in 300,000. And we can cancel the zeros, and we can cancel that and that. We get 1,000 meters, which is about 0.6 miles. It's a little easier to work with, right? Still pretty long, especially if you're trying to build an antenna to receive it. So let's change it again. Let's make it 300 million hertz. Well, first of all, whatever is sitting on that circle that's spinning around 300 million times per second is getting pretty sick, right? 300 million times per second. But let's do the division. What's 300 million divided by itself?
1.
1 meter. So that is a 1 meter wave. That is about 39 inches long. So we are obviously, if we're dealing with things that we can actually like touch, that makes sense. Remember, like a 1 meter wave traveling through space, through air, that's 330 hertz. This is for the same wavelength, 300 million hertz. So what does that tell you about the speed of light compared to the speed of sound?
It says it's much, much faster.
Much, much faster. Has anyone ever been to a baseball game? And
Yeah.
sat way, way out in the bleachers? Like way, way out in the bleachers. And notice that the sound of the ball getting hit is way later than the crack of than what you see as the crack of the bat.
Yeah, it echoes.
Well, it's not that it's echoing, it's just taking that much longer to get there. That's the same reason that you can see a flash of lightning and be able to count the seconds and figure out how far away it was. Because it's that much slower. I mean, it's many orders of magnitude slower. Okay, so now, and it's almost break time. So what we're going to do now, that's right, or that's why concerts have to have delays in the sound system, because yeah, things are, all echoey. That's why there's a thing called acoustics. Different things take different lengths of time to make that trip, But the fact that you actually have, for instance, let's say that you have 2 speakers. That's actually very interesting that you would have mentioned that, because let's say that you have 2 speakers. You have a speaker over here and a speaker over here. And they are transmitting signals which are identical right along this line down the center. Those waves are going to travel the same distance, and so they will add together. But how about like you have a person that's over here on the left? Which wave gets there first?
The left.
The left wave gets there first. This wave takes longer, right? Is it possible that they could be at exactly a particular spot where at a given frequency, these waves look like this, one looks like that, and by the time the other one gets there, it looks like that?
Yes.
Yes. And what happens when they add together and are opposite?
Cancel destructively.
They cancel. And guess what happens to what you're listening to? It gets all distorted.
Nothing.
It gets all distorted. You don't hear that, but it's only at, it's possibly only at one particular frequency. So you might have like a hole in what you're hearing. And that's when you start getting distortion. And that's when acoustics become really important. Now, believe it or not, we do the same thing with radio. We build antennas that actually have phased arrays. So we do this on purpose. Okay, so what I'm going to do is I'm going to share this now. I'm going to close the whiteboard and put this back up. Okay, can everybody see that shared screen?
Yes.
Okay. What do you notice across the top?
Yes.
What are those measures?
Frequency.
Frequency. And notice instead of carrying all those zeros, we have placeholders. The placeholder for 1,000 is K for kilo. The placeholder for a million is mega or big M. The placeholder for a billion is giga, big letter G. The placeholder for tera is a trillion. That's the big letter T. All right, and then across the bottom, what do we have? We have our wavelengths. We have our wavelengths. And So what are those measured in?
Meters.
Meters, okay. And all the way on the left, notice we have 10 kilometers. Again, that's kilo. That means 1,000. As we go to the right, we have, like, for instance, this 1 meter. And what do you think you'd find if you multiplied 1 meter by 300 million hertz? What would you get?
Speed of light, maybe.
Speed of light. Yeah, exactly. So basically, this is all defined by maintaining the speed of light. And notice as we go higher to 3 gigahertz, our wavelength gets 10 times smaller. It's now 100 millimeters. As we get to 3 terahertz, it's 100 micrometers. Micro is 1 millionth. And what happens when we are up at like, let's say 700 terahertz? We're at 400 nanometers, 500 nanometers, 600 nanometers.
Visible light.
It's visible light. Okay, so this is actually really significant. Red, the reddish light is about 660 nanometers long. That's a typical red laser. Green is in the 500s and purple is in the 400s. So what happens if you go shorter than purple? You're in ultraviolet. If you go longer than red, you're into the infrared. You get longer wavelengths. Well, okay. So what happens when you go really long waves? How are radio waves different than visible light? There's really only one way. Well, there's a couple ways. How are radio waves different from visible light?
Less energy or, longer frequency.
Lower frequency, longer
Really long
wavelength,
Yeah.
but really they're the same. Radio waves are just another color or a whole range of colors, but we don't see them as colors because we don't have the ability to do that. We see these as colors, but we don't see radio waves as colors. But if we could, they would all be different colors.
Synesthesia makes so much more sense now.
Yeah. So, and notice we have our microwaves at roughly 2.4 gigahertz, which is at the upper end of the UHF band. Notice that they're also broken up into these 3 bands that we frequently use. 3 to 30 megahertz is known as HF or high frequency. 30 to 300 is very high frequency. 300 to 3000, which is also known as 3 gigahertz, is known as ultra high frequency. Then there's also an EHF and an SHF. And then down below, we have MF for medium and LF for low and VLF and ELF. And so they have lots of different names. But really, these are all just different colors of light. Of some importance, the higher the frequency you go, the more energetic the photons are that are carrying the energy. So a radio wave is very low energy. Infrared is higher. And then you get through the different colors. Red is lower energy. Purple or violet is higher energy. X-rays are extremely high. Then there's gamma rays and cosmic rays. And so anyway, that's our trip through the electromagnetic spectrum and a little bit about why we are where we are. The fact that essentially we've now done wave theory, and now we have a good understanding of how waves work and why they are what they are. And then combine that with electromagnetics and able to see that every color of light that you see, including radio waves, is just another color of electromagnetic waves. How about a 5-minute break?
Could you please repeat that last sentence?
Yeah, basically every wavelength of electromagnetic radiation is just a different color. That radio waves are really fundamentally no different than X-rays. The only thing that makes them different is the frequency of the thing that was generating it in the first place and the amount of energy in it. The thing that carries energy, like light energy, is called a photon. Radio works in photons. I mean, it obeys the same laws as visible light. I mean, how does a microwave oven work? A microwave oven is at 2.4 gigahertz. So it's about right where my cursor is. So that's UHF. It's at 2.4 gigahertz. Why was that frequency picked?
Because it resonates with water.
Because it's at a perfect resonant frequency of the H2O molecule. So motion is heat, and when water is exposed to frequencies of that range, it starts to vibrate. Vibration is movement. Movement is heat. Heats up your food. So the question then becomes, let's look at that chart again, right here, and let me ask, since radio waves and light waves are really the same, why can you see the food in your microwave boiling and not get bombarded with radio waves?
Faraday cage.
Nope.
They absorb.
Nope. Think about what you're looking through.
Glass insulator.
Well, it's not the glass.
No.
They can't get through those little holes.
Radio waves have too big a wavelength to fit through the tiny holes.
Can you repeat the question?
How come you can look into your microwave and see your food without getting bombarded with the 1,000 watts of radio waves inside the microwave?
It wouldn't be that it dissipates before it reaches you, right?
Nope, definitely not. Otherwise, we couldn't talk.
If they couldn't come through, what does come through? Because like they have warnings for pacemakers in hospitals.
Yeah,
and
there's a tiny little bit that may leak. But if a microwave is built properly, then everything is contained inside. So what are the two wavelengths? What are the two things that exist inside that microwave when the light is on and the microwave is on?
Emitter.
You have a ton of radio energy, and what else?
Heat and light.
No heat. Just light, because the light bulb is on. What's the wavelength of light?
1 micro or 700 nanometers.
700 nanometers,
Just
500 nanometers. What's the approximate wavelength of 2.4 gigahertz, which is right here?
12.5 centimeters.
About 12 centimeters. Okay. How big are those little holes in the grid that you're looking through to look into your microwave?
About a millimeter.
Millimeter-ish.
Like a millimeter wide? Okay. So for light waves, that's huge, right? That's like a giant open door. How about for radio waves that are 12 centimeters long or this big?
Oh, they can't get through there.
Might as well be solid.
And they can't get through. So that is why electromagnetics is magic. And that is one of the reasons that we do this, because, that's a big part of understanding why all this stuff works. I mean, the fact that you're probably going to go upstairs and reheat your coffee right now and be able to see the coffee in the microwave without getting flooded with radio frequency energy is a miracle. It really is. It's an understanding of the physics involved, and that's basically what we're trying to teach. That's what the first part of the class is.
So I have kind of a question.
Mm-hmm.
So does the microwaves break up when they hit the holes, and or does it like slow them down? Because I feel like we would hear it.
They physically can't pass.
So they just block and they bounce back.
The orifices, yeah, it looks like a solid wall to the microwave.
Okay.
It looks like a solid metal wall. and then we're going to get into antennas too, because
So it bounces around until it gets absorbed by the water.
Yep.
Or you turn it off and it somehow magically dissipates.
It dissipates. Yeah. It has to go somewhere. So it heats stuff until, well, and that's a problem. What happens if you take a microwave and you run it with nothing in it? Microwave is not particularly happy. But that also explains why if you take a knife, don't do this. If you take a knife and stick it in your microwave, what'll happen to your microwave?
All the waves bounce off of it.
Sparkly.
Well, yeah, what you end up with is waves which are forming in there, and those are different voltages. And we're going to get to Ohm's law very soon. But basically, if you have a solid metal object which has very low resistance, and one end of the fork or the knife is at one voltage, and one end is at the other end is at another voltage, you get current flowing through there, and then you can get sparks and heating, and you can melt things. And
tinfoil.
Aluminum foil works very well for that. I've also seen putting a CD in there.
Yeah.
Because that has a very thin layer of foil.
Yeah.
All right. How about a 5-minute break?
Yeah, before the break, I just want to shout out to Leslie to look at your chat. Thank you. That's all.
Okay. All right. Everybody back?
Yep.
That's a 1.
Present.
Aye, aye.
Yes.
Yes, sir.
I am here.
Excellent.
Mandel's here.
All right. So, well, now what we've done is we're going to get started again. We talked about waves and we talked about things that they do when they're in space. Well, yes, it also turns out that electromagnetic waves travel at different speeds depending on what they're going through. That's why if you ever take a spoon, you can try this, and you stick it in a glass of water and you look at it from a certain angle, it looks like the spoon is bent. And then you pull it out and it's really not. Essentially, it's an optical illusion that's created by different indices of refraction, which basically are properties of the material like water that change the speed of light through it. And yes, it does the same thing for radio waves, believe it or not, because they're really the same. Okay. So I don't know exactly where we are in the book, but it really doesn't matter right now because we're just covering the fundamentals, the foundational stuff. And now what we're going to do is we are going to draw this thing called an atom.
It's 13:30.
All right. So what is an atom made of? We have a nucleus.
Electrons.
We have protons in the nucleus, and we have neutrons, which have no charge. And then zipping around that, we have in different orbitals, we have electrons that are negatively charged. So protons are fine, but they're really heavy and big. So we don't usually deal with them. They have a positive charge. Anytime you move a charge in space, it creates an electromagnetic wave. Or at least it creates a disturbance in an electromagnetic field. If you move it back and forth, it creates a wave as it goes up and down, up and down, up and down. So let's take a look at an electron. Let's say we can separate this from its atom so that we now just have an electron sitting there in space. And we're going to move this electron, and we're going to move it back and forth and back and forth. We're going to cause it to vibrate. Well, this actually has a name. If we take an electron, which is a fundamental particle, and we move it, it has a negative charge. And as an electron moves, this has a name. Number of electrons that are moving in one direction at any given time. That's known as a current. We represent this with the letter I. We measure it in A, or amperes. Those are all things that describe current. Current is the movement of electrons. And that can be anywhere. That can be in space. What's a way to constrain electrons from jumping around too much?
Keep them in a conductor.
We can put them in a wire. Yeah. Okay. So what we're going to do instead is we're going to, instead of having it just float around in space, we're going to take a bunch of atoms and we're going to line them up like this. And here's our nuclei. And flying around these, we have our electrons. And some are closer to their nuclei than others. They're held in place by electric charge. Well, some atoms are very, very tightly bound. They have very tightly bound electrons. If they're very tightly bound, that means that they don't allow those electrons to come free. Well, since we know that current, well, this is what we said, current is the flow of electrons. And if we try to push an electron in, ideally, what we're going to get out is an electron coming out. As this first electron makes its way into this one, which displaces another one, which displaces another one, and eventually it comes out the other side. Again, some atoms are not particularly good. Some, and it doesn't even have to be an atom, it can be bigger. Some molecules, some crystals are not particularly adept at moving electrons just because of how they're built. So something that is a good conductor of electrons is known as a conductor. Something that is poor at conducting electrons would be known as an insulator. An insulator does not allow electrons to flow. So that being said, can everybody think of some different names of things that make good conductors?
Copper.
Copper, excellent.
Aluminum.
Aluminum is actually really good.
Gold.
Iron.
Gold. Iron, pretty good.
Silver.
Silver, excellent. Okay, how about
Gold.
some? Yep. Okay, how about some things that make good insulators?
Glass.
Glass.
Glass, yep.
Rubber.
Rubber, good.
Wood.
Wood, unless it gets wet.
Right.
Other things?
Air.
Air, very good.
Plastic.
Plastic.
I'll be plastic.
Paper. How about water?
No.
Depends.
Insulator, unless.
It depends.
That's a good conductor, I thought.
It's actually a very poor conductor. Because water, what's the formula for water?
H2O.
H2O, okay.
It's
So
the extra ions in the water that make pure water.
that's right. So here's our hydrogens, and here's our oxygen, and it has a negative end and a slight positive end. So there's our H2O, and water is a polar molecule. And because it develops polarity, it can line up with other ones like this. It's really good at making ice crystals and stuff like that. So water is really good for that. But when you try to push an electron in, it doesn't really like to push one out the other side. So that would be deionized water. Deionized water is actually a really good insulator. How about when you dissolve salt in it?
Really good at conducting.
Really good at conducting. Yeah. Okay. So here's our pool of water, which is lots of H2O, but then it also has Na. I'll use a different color.
And in this
Na
instance,
plus and
in this
Cl
instance in water,
minus.
is it the same reason that there's free electrons like in metal
Mhm.
that allow that?
Similar. I mean, basically, what'll happen is you end up with an electron floating in, and it manages to find its way out the other side.
Is
But-
that why people are good conductors?
Yes. That is why, even though you can get, well, for instance, your skin is not a very good conductor, what are you largely made of?
Water.
Not just water.
Salt water.
Salt water.
Oh,
That's
yeah.
right.
Yeah.
So we're made of salt water, which is why electrocution can happen. Because once a high voltage breaks through and gets into and under your skin, into the juicy insides, which are mostly salt water, it makes it really easy for current to flow. And current flow gets in the way of your body's natural ability to like function. Stops your heart, stuff like that.
Because
Causes
we're
your
using
muscles.
electricity to function.
That's right. That's right. We are basically top to bottom, we have electrical signaling. So you get a current that disrupts it. Okay, so now we've discussed conductors and insulators. So what we're going to draw is here's an electron, and we're going to have something that it's trying to pass through. The degree to which this thing right here allows electrons to pass through from one end to the other, this is known as resistance. This is measured with the big letter R, and the units are the the Greek letter ohm, or omega for ohm. The units are ohms. Okay, so that's resistance. The amount of push that we have, so let's say that we have like me pushing super hard against this, trying to push that electron in. If I don't push very hard, that's not a lot of push, and nothing will happen. The harder I push, the greater the chance that I'll actually be able to develop a flow of electrons. And what's the flow of electrons called?
Current.
Current.
That's
Amperage.
That's current. And again, that's big letter I, and it's measured in amperes, or A. The degree to which I'm pushing, this is known as the voltage, or EMF, which is electromotive force. This is measured in volts. Sometimes it uses the big letter E for electromotive force. And again, this is measured in volts. Now you'll probably hear that there are a lot of units that are named after famous people, like Georg Simon Ohm. Ampere was a scientist. Volta, big time scientist. Hertz, big time scientist. There are many. It was a good thing to be a physicist and scientist in the 1800s, because if you did anything cool, you got something named after you. And that's what we use today. So the voltage is the amount of push or pressure. Resistance is how hard the material that you're trying to push through fights back. And the current is how much the net result is of current flow or electron flow. So what we're going to do now is going to close that. Okay. So now I'm going to erase the screen. And somehow we have to generate a source of electrons in order to have a push. And that is known as a battery. It has a positive terminal and a negative terminal. And this generates a current in this direction. And it has a voltage, or in some case, we'll call it big letter E. That generates a current measured in amps, but we have to have some place for this to go. So it has to go through something to get all the way back. Right? Okay. This is, we're actually going to change what that looks like. That is the schematic symbol for a resistor. This is a battery. Okay, so the relationship between volts, this is measured in ohms, this is measured in amps, volts, ohms, and amps. Ohm's law. There's actually two of them. We'll just write one for now. E is equal to I times R. Ohm's law. So what we're going to do in this case is we're going to take this battery and we're going to say that this battery has a voltage of 9 volts. So your classic 9-volt battery. And we're going to run this through a resistor, which is, going to get rid of that, make it nice and clean, 9,000 ohms. Okay. The question then is, we have a current, letter I, and we are now trying to take a 9-volt battery, which is generating a surplus of electrons, and shove it through a 9,000 ohm resistor and figure out what the current flow is. The same way that I did that circle before, 300 and
1,000 amps.
and lambda. It's not 1,000 amps. Thank goodness.
Oh, wait a minute. It's
So here's what you do. Here's what you do. EIR. You can always start with drawing the circle because there's a lot of different ways to write this. This way, always make sure that you got it right. So I got I that I don't know. I cross it out. I'm left with E divided by R. That is Ohm's law. That is the right form of Ohm's law for me to be.
It's 9 divided into 9,000, correct?
Yep, 9 over 9,000.
Yeah, I thought I got it right. But
Yep. So I is equal to 9 volts divided by 9,000 ohms is equal to 1/1000th of an amp.
Okay. 1 over
1 milliamp.
Yes, this is also known as 1 milliamp.
Had it flipped around.
Yep. And that's why I always end up writing out the equation just so I don't mess it up. Even now, even after doing this for the last 50 years of my life.
Just to ask a clarifying question from earlier, as far as all the test go, current flows from positive to negative.
Ah,
is that yes or no?
Hold on. Okay.
Here we go.
Nope. This is actually really important, but then you're going to forget you ever heard it because you're going to forget you ever heard it. Okay. Here's my battery, right? Everyone agree that that's a battery. Here's a plus and here's a minus. And here's a resistor like that. And current flows like that. It flows from plus to minus. Right? Everybody agree with that?
Yeah.
Okay, so here's my E and my R. Okay.
Direct current.
What is the charge on an electron?
Negative.
Negative.
Yeah, hold on. And I don't know why it just drew that. See, I'm still not quite used to this thing. Can everybody see okay?
Yep.
Okay. So an electron is a negative charge. Agreed?
Yep.
Well, if you have a positive terminal and a negative terminal on the battery, where do the electrons come from if they're negative?
Well, you'd think they'd gather on the...
Well, they come out of the negative terminal and they flow this way because they are attracted
Which is the
to the positive
definition
terminal.
of current.
Yeah. Okay, so what does anybody see a problem here?
Yes, that we made the convention for current before we knew what an electron was.
That's exactly right. Long before. Nobody knew that an electron was actually a negative particle. So what we're going to do is accept the fact that in the 1820s, they did not know this. And we're going to, just for the sake of argument, because things go from positive to minus, they go from higher to lower. Our voltage is measured with the plus and the minus, like this. And our 0 volts is going to be the ground reference, as we call it. It's going to be 0 volts. And this is going to represent the flow of current going this way. Even though we know that for a fact, the electrons actually go the other way. And that was actually one of the first things that we were taught in engineering school. Just ignore the fact that this is true because, you know, for the sake of calculations, they made a mistake. It was too late to go back and fix it.
Okay. But again, for testing purposes, this is what we
Yes. For the
go with.
And in fact, in all of engineering, current flows from positive to negative. You can think of it as the flow of holes, because that's what a lack of an electron is. It's also known as a hole. In semiconductors, it's called a hole.
Say that bullet point in all of engineering current flows blank.
It flows from positive to negative. In
Thank
the
you.
entire world, current flows from plus to minus. But just know that in your heart, you know better that they made a mistake.
So I have a question.
Uh-huh.
So if you take a voltmeter
Mm-hmm.
and you use a voltmeter to test something, like you're trying to figure out what's wrong in a circuit.
Let's draw that. So let's draw a battery. Let's just say you want to know if your battery is any good, right? That's a really good test. So let's say we have a battery here that says 9 volts, right? Not hooked up to anything. Okay, keep going. Keep going with your question.
And I'm going to use a voltmeter to see if things are working.
Mm-hmm.
Then what comes to mind? Whether a resistor's bad or whether something's bad that's on a circuit, then I have to.
Let's throw 2 resistors on there just to make it interesting, right?
Well, I'm not going to do any resistors yet.
Oh, okay.
But so this is a voltmeter, right?
Yes.
I'm measuring in parallel with the battery. I'm seeing what the voltage is across this device.
Yes.
Okay. So keep going.
And so normally you take the red lead that you have in the positive socket of your voltmeter.
Yep.
And you take the black lead, which is in the negative socket of your voltmeter.
Just like that. Yep.
And so you're reading literally the flow into that voltmeter is going through the black and out the red.
The flow of electrons, but again, you're not going to remember that.
And nothing's flowing here, right? This is just the potential at this point.
Oh, no. Something's flowing.
Oh, okay.
Because what's inside a voltmeter?
A resistor.
There's a resistor and an ammeter. So inside your voltmeter is actually a resistor and an ammeter. So basically, it's a calibrated resistor, and it measures the current. And by Ohm's law, E equals I times R. Calculate it by multiplying the resistance and the current. That's how you calculate. it.
So
okay, but when you're trying to troubleshoot said circuit because something's on it, and you're using those same red and black.
Red is the plus, always. The current flows into the black, but what are you going to do? They made the mistake.
couldn't we just say that their color in reality, knowing that electron's negative, the colors truly are backwards, but
yes, they are.
Yeah. I think that maybe that helps. I'm not sure, but
okay, so let's say we have this, right? And let's say you have a 9-volt battery. And then you have what should be 4 ohms and 5 ohms. Okay, these are resistors, and these are resistors in series.
So they're additive.
And the resistors are additive. So this is R1 and this is R2. And then R total is equal to R1 plus R2. Resistors in series add together. So what would the total and by the way, this will be on your exam, most likely. Two resistors in series add together. So what would the total resistance be expected to be?
9.
9 ohms.
9.
9 ohms. Okay. So how would you measure this? What you would do is you would disconnect the battery and you would put a
voltmeter
or an ohm meter.
Oh, ohm meter, yeah.
Right here. Okay. And what does that do? That actually has inside it
voltage.
It has its own plus and minus, and then it has an ammeter, and I might as well draw the plus and minus as an actual battery.
Yeah.
So it basically puts a test voltage across the circuit and measures what the current is. And then what
It's
does it
created
use?
its own circuit there.
It has.
Right? Yeah.
Which is why if you left the battery connected, what would end up happening?
2 circuits.
You'd end up with 2 circuits and your reading would be inaccurate. So that's why when you're measuring an in-circuit value, you always have to disconnect it.
And that's a lot of reasons why people get this wrong, because they don't realize that.
That's on your exam also.
Yeah.
Most likely. That's why you always disconnect if you're measuring a circuit resistance, you disconnect it. Because you want only the supplied test equipment to be giving you the value. All right, so does that answer the question or kinda?
Kind of.
Kinda. What's the rest of it?
So I'm thinking of like when I've tried to find where I have a short circuit or I have a problem. Like let's say I disconnect my battery from my vehicle. I'm sorry, no. I turn my vehicle off. It's completely off. Everything's
is
off.
it?
I turned off
Yeah.
the radio and everything.
Is
and
it?
I'm still losing.
Is it really off?
No.
No, it is
No.
not. That's the thing. It's not really off.
Right, because I've got my theft stuff and some stereos. So now I'm trying to find where that mystery draw is.
Parasitic draw.
And that's what you do?
Parasitic draw. Thank you.
You know what you do then? You just start pulling fuses.
Yeah.
You start pulling fuses and opening the circuit. So that brings us to the next point. Okay, so what we have now is we did a series circuit. What was series? It means that an electron has to go through all the things in order to do its job. So now we're going to draw another circuit. This is how most things are actually wired. And the reason being that let's say I have, in this case, a 12-volt battery. Where would you find a 12-volt battery, by the way?
In your vehicle.
In your car, yes. It is a 12-volt battery, nominally 12 volts. What voltage will be experienced by this resistor?
12
Everyone? 12 volts.
I didn't hear that. What was the question?
What voltage will be experienced by that resistor? How many volts? Assuming that your wire has no drop, no loss.
12 volts.
12 volts. How much voltage is experienced by this resistor?
12 volts.
12 volts. Okay. So that's excellent, right? Because if, let's say, somebody were to take this and cause an open circuit right there, like that, how much voltage would now be experienced by the second resistor?
Oh, the
12 volts.
12 volts. That's right. It doesn't change. This is how your house is wired. The reason this is how your house is wired is because let's say that somebody unplugs something from the wall. You don't want the whole house going dark, I assume, right?
Mhm.
If everything was wired in series, which looks like
Christmas tree.
this, yeah, let's draw that. And then this can be a little instructive. So let's say we have our DC power supply, and we have a resistor and a resistor and a resistor like that. Three of them in series, right? We have R1 and R2 and R3, all in series, right? Do these experience the same voltage?
Yeah.
No.
Yes.
No, they do not.
Oh, wait a
Because
minute.
for each one, what you can say is they experience the same current because the electrons have to flow through all three in order to get back, which means that the current is the same. But what is Ohm's law again? Everybody. E
E
equals.
equals IR.
So, depending on what the resistance is, this has its own separate E equals IR, and this has its own separate resistance, E equals IR, because the resistances aren't necessarily the same. So the total resistance is going to be R1 plus R2 plus R3, and then your total current is going to be defined by that total resistance. And then each one of those things is going to have a voltage, which is defined by its own resistor value. So what that means is that if these are slightly different, they're going to have different amounts of voltage appearing across them. What we haven't gotten to is the other half of Ohm's law, which is P equals I times E.
It's 14 hours.
This is
So are you saying
power.
that resistor 2 is going to receive less voltage because it went through resistor 1?
No, I'm saying that resistor 2 is going to receive a different amount of voltage because it's possibly different from resistor 1. And what you end up with is a circuit in this case that is unpredictable. For instance, let's say that resistor 2 was replaced by this, a short circuit, just connected from end to end. How much voltage would be appear across resistor 2?
Zero.
Zero. That's right. It's the same on the input and output. And if power is equal to current times voltage, and my voltage is 0 across it, how much power is there in my resistor?
Zero.
And if that is a light bulb, how much light do I get out of it?
Zero.
Nothing. Nothing. Similarly, if I were to take that and instead do this with it and open it, make it completely go away, what's the resistance across what's the resistance of an open circuit?
Infinite.
Infinity. Yeah, okay. So what's my overall circuit resistance if I add three things together?
Infinite.
Infinity resistance. And by Ohm's law, E equals I times R. And I know that E is not infinite, right?
Mm.
It had a real value, and R was infinity. So what does I have to be?
Zero.
No current. If I have no current, how much power do I get?
Zero.
And since power is what makes light, what happens to my Christmas tree lights?
They go off.
They all go out. That's why we don't wire our houses that way. That's why we don't wire our cars that way. Even if they did work, the individual resistances of the light bulbs or whatever it was would determine how bright each one was.
So back to the automotive scenario, you have multiple circuits that are sitting parallel with each other, and by pulling out those fuses, you're pulling fuse from one of those circuits. One of those circuits is the one that's continuing to draw current.
Right.
So once you find the one that you need, or you find a fuse you pull out and their parasitic goes away, you go, that's the circuit. That's the one that's drawing.
So fuse, in this case, we're putting fuses here. A fuse is a device that's designed to blow when a certain amount of current going through that branch is exceeded. We can also remove the fuse and create an open circuit. It looks like that. We can selectively open parts of the circuit. And if we see that the parasitic current goes away, we know that it was the thing that was connected to that fuse. We're solving
So
it.
my other
Go ahead.
question, and I'm still just a little stuck, so hang with me. The
Mhm.
picture you had before where you had the 3 resistors in series.
Okay.
If I were to take a voltmeter and go from one side of measure from the battery to the resistor, I'd have 12 volts. When I measure,
No. Right, like from here to here,
yes,
you'd have 0. This right here is our 0-volt reference. And let's say this is a 12-volt battery. How much what would the voltage be right here?
0.
It'd be 12 volts. This would be 12 volts.
In reference to 0
Right.
volts.
So if I measured from here to 0 volts, I would get 12 volts.
okay. And my next question is, if I now connect it on the other side of that resistor,
Mhm.
I'm going to have 12 volts minus whatever that resistance is. I should have less than 12 volts, correct?
Yep, because some work was being done in there. Yep.
Okay. So now that is the voltage. That new voltage is what's going to go into resistor 2.
That's what's available to it.
Yes. Yes.
But remember, that's available. That's being used by both downstream components.
Well, but the third one is going to get even
less.
more altered because I've now got the voltage that got dropped through 1 and through 2. So by the time I get to 3, it'll be altered again, correct?
Yeah. Yes. So here, let's do
Okay.
a little math. 4 ohms, 3 ohms, and 5 ohms. Okay. What's the total resistance? And by the way, something like this is a test type of question. What's the total resistance of those 3? Resistors in
12
series
ohms.
add. That would be 12 ohms. Okay. 12 ohms. What's Ohm's law? Everybody.
V equals
E
I
times R or
E
V
equals I times
E.
R. Excellent. Okay. So what don't I know? I don't know my current. All right. So I'm going to take my current, cross it out, and I have I is equal to E divided by R. What's the E of my battery?
12.
12
12
volts.
volts. What's the resistance?
12.
12
ohms.
ohms.
All right. So what's my current?
1 amp.
1 amp. 1 ampere. So my current is 1 amp. Okay. So now, can I do a separate calculation for the first resistor? I sure can.
Yep.
What law do I use again?
Ohms.
No. Yep. E equals I times R. Okay. But in this case, what don't I know?
Voltage.
I don't know my voltage. So it's E equals I times R. My current is
1 amp.
1 amp. And my resistance is
4 ohms.
4 volts. If I were to take a voltmeter and measure the voltage from this point to this point, I would get 4 volts. I would actually see 4 volts.
You
4,
lost
not
me
3?
Hmm?
Not 3 volts?
It's
12 divided by 4?
No. I would get 4 volts. In other words, the voltage dropped in that device is defined by Ohm's law. Everything comes back to Ohm's law. I would see 4 volts.
Okay.
I would see
So we
4
got to
volts.
calculate the amperage used by the circuit first. Once
Yep.
we know that amperage, then we can go back and calculate the individual voltage drops.
Yes.
Yep.
Okay.
So, okay, then Luetta, if I were to
Yes.
measure this side of the resistor and compare it to the 0 volts in the circuit, what would I see left? How many volts?
8.
I'd see 8. That's right. Okay. So now I'm going to do the second resistor. Okay. What would I expect to get? What's Ohm's law?
5 volts.
No. Well, yes, I would expect, but what's the voltage drop in the resistor? How many volts would be dropped?
3.
3 volts. Okay. So if I took a measurement across this, I would see 3 volts. And since I started at 12 and then I lost 4 and I lost 3, what would I be left with from here to here?
5.
5 volts. All right. And now we can actually prove that that's true. Here's the last one. What's Ohm's law say again? E equals I times R.
E equals I times R.
And what is it in
So
this
that should
resistor?
be 5 ohms at 1 amp.
1 amp times 5 ohms is how many volts?
5.
5 volts. So I measured it across this resistor. I would see 5 volts. And how much is measured from here all the way on the right down to here? Nothing.
Oh, nothing. Yeah.
There's
'Cause
no
it's
current.
all
It's just a piece of wire.
right.
So what we just did is we went around the whole circuit and we showed that the way we drew it actually works.
Mm-hmm.
And that's how you would measure things across a series circuit.
So are you saying that there's no current flowing after the third resistor?
No, there is. I mean, there's no voltage available anymore, but the current has to flow. The electrons come out of somewhere and go back to somewhere. They have to make the trip. But by the time they're through all 3 of the loads, there's no push behind them, which is fortunate because it's just a piece of wire and it doesn't take a lot of push to get it through there. In reality, this wire might be 0.01 ohms, which is really essentially nothing.
But you still have the electron generator on the left, so hence it just keeps flowing.
Right.
Yeah.
Right. There's just no push left to do any work.
Yeah.
Which is good. You don't want your wire to get hot.
So why does the system default to 1 amp with the 1A?
Because we added all the
what's
resistors together.
What's the
and
sum of
divided
those
the voltage
resistors?
into it. It was 12.
12 ohms.
Uh-huh.
And then again, back to Ohm's law, E equals I times R. You have 12 volts sourcing it, and 12 volts, that gives you 1 amp.
Got you. Okay.
So.
Okay, so if you change the 5 ohm resistor to say 2 ohm, or I don't know what, pick another number.
I like 2.
A lower number.
No,
what
let's
happens?
do 2.
Your current changes.
Yeah, my current would no longer be
1 amp.
1 amp, would it?
Mm-mm.
Everything changes. So what's my new total resistance?
9 amps.
9 ohms.
9 ohms, excuse me.
And what is my
Divided by
what is my new current? E equals I times R.
Yeah.
E I
so
R
12, 14.
Cross out I. You get
So
12 divided by 9
14.
is 1.3
Oh.
amps. And now I'd have to do my calculations all over again based on the current through everything being 1.3 amps.
And can you do that?
Sure.
Can you go ahead and show us that?
Sure. Okay. So what you tell me, what would the first thing that I do be? I want to know what the voltage is.
So you've got 1.3 amps.
Right. What's
times
Ohm's law? E equals
IR.
IR. Current 1.3 times
4.
4
is 5.2 volts.
Okay.
Okay. Second resistor.
That's
1.3 times 3.
1.3 times 3, 3.9 volts. Third one.
1.3 times 2.
Yep, 1.3 times 2 is 2.6. And roughly. I mean, I rounded.
Yeah.
So you add them together, I'm off by a little bit because I rounded, but essentially it's 12 volts. And so there's another law. Again, like I said, if you were alive in the 1800s and you were doing basically engineering work in the electrical realm and you came up with something, you got it named after you. So this was named this law, which says that if you start at a point and you go around and you end up right back where you started, your voltage around the entire loop has to be 0. This is known as KVL, or Kirchhoff's voltage law. And we can do that. We can start right here at our defined 0 volts. We call that ground. And as we go up through the battery, what's our new voltage? How many volts do we get?
1.7.
No.
Oh, what do you mean?
If we start at 0 and then we encounter a battery, which is a 12-volt battery, how much voltage do we have?
12 volts.
12.
Yeah.
And then how about over here, once we go through and drop, so this is really negative because we're using power.
0.
So we're left with 12 minus 5.2.
Right.
God.
Then minus 3.9.
We're left with 6.8.
6.8.
And now we have like 2.9, and then we have 2.6 with the rounding factor. And we're
2.9
back to
is
0.
Wait a minute.
Because it's 1.3333.
If
So
you
the
did
sum
the
at the end of the circuit will always be
3.9
zero.
minus that, then you get 2.6. 2.9, not 2.6.
Yeah, it is, but that's because I rounded.
Oh, okay. Gotcha.
I picked something that wasn't exact. Because the current is actually 1.333333 amps.
Boy, we're moving out.
So this is Kirchhoff's voltage law. Believe it or not, he also, because he was busy, came up with something called KCL. Anybody have any guess what that might be?
Current.
That basically means that if I have a current flowing here and I split it, so here's my I in, and here's my I out 1, and I out 2. Anybody guess what this is going to say?
Yeah, they're going to equal, if you add them together, it equals the IN.
Yep. That all the sum of all the input currents has to equal the sum of all the output currents at any given point. In other words, you cannot, in a plain old circuit, you can't accumulate current. You can't have an electron accumulation. And this is called a node. So at any node, you have to have the same amount of current flowing in as flowing out. And that's called Kirchhoff's current law. Clear as mud?
Clear as mud.
Clear as mud. Okay.
I always think of it like water too, and pipes and
essentially, yeah.
Actually, that's what they taught us when we were in the military.
Mm-hmm.
When we first started pipes.
Yeah.
It was
valve
easy.
resistors and yeah.
All right.
And-
Any other? Go ahead.
Oh, I was gonna say, you said clear as mud. This stuff is coming back because the circuit, the parallel circuit versus the series circuit. I know that's on the test.
Mm-hmm.
But how you handle, it's not the same with your voltage going across the series. Like if you had 12 volts, say 9 ohms in a series, you just divide it, you get your answer. And I thought you said on a series, the voltage was not the same.
Correct. The current is experienced
parallel.
in parallel. The voltage is. So here's my
parallel 12 voltage is the same, but not the current.
Correct. Right? Here's my 12-volt battery. Right. How much voltage is going to be right here? 12 volts. How about over here?
12 volts.
Okay. If I pick a resistor value of, let's say, 1 ohm right here, how much current am I going to get there? What law do I use to calculate it again?
It'd be 12
ohms.
E times up.
Yeah.
Right. And it turns out this would be 12 amps.
Right.
And if this one were 120 ohms, how much current would I get right there?
10 amps.
No.
Or other way around, sorry.
0.1 amps, right? So I get 0.1 amps. Okay. So the question is, does the power source care? Do each of those devices care what's happening to the other one?
No.
A little bit. The reason being that this wire right here and the battery have to source how many amps total?
12.
12.1.
12.1 amps. So
Yeah.
this thing has to be able to source 12.1 amps of current. This wire has to be able to carry 12.1 amps of current. So now what I'm going to do is take this 120 ohm resistor and I'm going to replace it with a 1 ohm resistor. Something bad happened and that is almost shorted out.
Yeah.
So what did we design our circuit for? How many amps?
12.1.
12.1 amps. Okay. Well,
From
what is my new circuit drawing? It's not 0.1 amps
24.
anymore.
24.
This is now, by Ohm's law, pulling 12 amps because it's the same as the resistor. So what's the new total current?
24 amps.
What if my wire is only capable of doing 15 amps?
You let the smoke out.
Yeah. Well, or what ends up happening is
Well,
P is equal to I times E. This is a good time to introduce Ohm's power law.
Yeah.
All right. Okay. So we have P equals IE and E equals I times R. Okay. We can combine these in a couple of different ways. We can make them with substitutions, say that P is equal to V squared over R, or P is equal to I squared R. If we have a resistor, this wire is not perfect. Let's say that it's 0.1 ohms. Or you know what? Let's make it let's say it's 0.1 ohms. The circuit was designed for a current, what was it originally? How many amps? 12.1 amps. But the new circuit with the failed component, which I'm going to circle over here, that's a failed component. It's not doing what it was supposed to do, or somebody built it wrong.
Yeah.
Well, we have a resistance of 0.1, and we have a current that we can plug in, and we can say how much power was originally getting burned up in this thing by Ohm's law. Okay. At 12 amps, let's say, P is equal to 12 times 0.1 squared, which is 0.01, is equal to 0.12 watts. Well, the new one, power is equal to 24 times 0.01, is equal to 0.24 watts. 0.24 watts. So what that could mean is, does everyone know what watts are?
Yeah.
A watt is a rate of dissipation of energy or a rate of use of energy. Energy can neither be created nor destroyed. Therefore, it has to turn into something. Resistive losses turn into heat. So let's say that this wire is inside a wall. What happens between dissipating 0.12 and 0.24 watts?
The heat increases.
The heat increases. Okay. And if it doesn't have a lot of room to get out of somewhere, let's say that this really got bad. And let's say that instead of 1 ohm, this new resistance was 0.01 ohms. There's a short circuit there. How much current would suddenly come through here by Ohm's law?
Most of it.
Yeah, this would be 1,200 amps.
Yeah.
Okay. Does anyone see a problem here?
Yeah, it's going to burn the circuit up.
Yeah. Okay. So if this is
It's
1,200
gonna
amps,
overheat.
well, yeah. So let's go over here to the left side and replace this with 1,200 amps. Right? Assuming that your power supply can handle it, which it probably can't. What'll end up happening is your power there will now be by the other part of Ohm's law. Again, now it'll be 1,200 squared times 0.01 is 144,000, no, 1,440,000, 14,400 watts.
We'll get to find out where copper's boiling or melting
That's
point
right.
is.
And if this is inside your wall, that's going to get really hot really fast. And what's it going to do?
Burn all your wire up.
It'll burn your house down. That's right. So
Yeah.
that is why it's very important to make sure this kind of thing doesn't happen. So we throw a device into our circuitry in order to make sure this doesn't happen.
Fuse or circuit breaker.
And that's known as a fuse or a circuit breaker or an overcurrent protection device. And why we do that is because if the circuit suddenly starts consuming considerably more power than we ever expected to, we're going to draw this again, go back to what it originally was. We will add a fuse in here that is rated at, let's say, 15 amps. So that if something were to go wrong, and this were to suddenly have a failure and become a 1 ohm load, and this current would rise to, let's say, 24 amps, all of a sudden, this calibrated little piece of wire, which gets hot, would get so hot that it would melt. And what happens when something melts?
Creates an open circuit.
It creates an open circuit, and it doesn't conduct current anymore, and it keeps your house from burning down and keeps your device from melting. And that's known as a fuse. And that is why we only ever use the desired fuse that the thing has been designed for, because it was designed for a particular purpose. And if it's not working anymore, then there's a reason for that.
I know we're not on this, but I got a question about putting wiring in for eventually ham radios. Not only do you want it GFCI, at least I do. I'm converted a porch into a 3-season.
Yeah.
Would you want an arc fault circuit interrupt? An arc fault breaker in there too as well?
I'm not sure.
Okay.
I think by code now you have to go arc fault if you're doing something new.
It depends on the voltage, I think.
Yeah.
Okay, so moving on to the.
I just enjoy that Joe has joined us from Australia.
All right. Really?
Your camera's upside down, sir.
Oh, really? Cool.
Yeah.
That's funny.
Wow.
Australia.
Okay, so
that's wild.
And now it's sideways.
Now you're in Europe. You were in Europe for a second.
Yeah.
Now you're...
All right, here we go.
I thought you were talking about somebody else.
Yeah. I thought once in a while we do get people from Australia. So, okay. So now what we're going to talk about is we're going to draw this circuit again. Okay. So here's our battery, which is going to say it's 12 volts. And we're going to run through a resistor right here. Okay. The way that this is drawn, which way is the current going? Out of the positive and back into the negative. Yes, I know it doesn't follow the electrons. Okay, so now, which way do those electrons, does the current ever change direction?
On a DC circuit? No.
Yep. Okay, well, we haven't covered DC yet. Because they're not changing direction, it's known as direct current, or DC. That means that the current is always flowing one way. Now, if I were to go in here and take this battery and do this with it and erase it and flip it so that the plus was now here and the minus was here, then the direction would be changed and the current would be now flowing this way. And if I were to do that a lot of times and keep doing it, it would not be DC anymore. So let's erase it again, like this. And I'm going to draw it again in a different color. Now it looks like this. Plus and minus. Now it's flowing like that. The fact that it's changing direction, if I change it in a periodic fashion, that would be known as AC, which is alternating current. And alternating just basically means it is changing direction from one to the other and back and forth and back and forth. The number of times that it does that in a second, anyone have a guess what that would be measured in?
1 hertz.
Well, what would the units be?
Hertz.
It would be hertz. That's right. So it would be measured in hertz, and the typical wall power that we have in the United States is 120 volts AC at 60 hertz. So 60 times every second, it's flip-flopping back and forth. It's making one complete cycle 60 times every second. And the voltage actually looks like this. And what's that a picture of, everyone?
Sine wave.
That would be a sine wave, which means that when it goes from plus to minus to plus to minus, it goes through zero. Now, why does it turn out that we end up with a sine wave? What do we use to generate our AC?
Oh wait, wait a
Motor.
second.
Motor.
Go ahead, Meredith.
Well, what do you mean? And then it's going plus minus, where you have the black arrows and then red and then green.
If I keep changing the battery and pulling it out and let's say flipping it upside down in the circuit, if I start doing that on purpose and I make the battery change direction, I've changed the plus and the minus, which causes the current to flow back the other direction. If I have something automatic to do that and it happens a certain number of times per second, I get a frequency in hertz. And what do we use to actually generate our power in the United States?
A generator.
A generator. And what is a generator? It's a bunch of electric coils.
Yeah.
And it's rotating. There's that circle again. As it circles, as it makes circles, it makes sinusoidal waveforms, which look like sine waves.
Via magnetism.
Yep. And so we go from plus to minus to plus to minus to plus to minus to plus to minus over and over and over and over. And as that happens, we generate a voltage at a frequency. And the frequency is how often it's going through one full cycle. So it's doing this full cycle right here 60 times every second. Now, interestingly, if I were to say, here's a battery, and this is not a trick question, and this is a 12-volt battery, what's the voltage of my battery?
12 volts.
Are you sure? Well, yeah, it is. So yes, you're sure. All right. Yes, you're sure.
Okay.
Okay. That's a 12-volt battery, right? If I were to take this battery and instead do 120 volts, what would the voltage of my battery be?
120 volts.
120 volts. AC or DC?
DC.
DC. Okay. Now, if I were to take that and replace that with a sinusoidal waveform generator, and this was 120 volts, and that was AC, that looks like it goes plus, it goes minus, and plus, and minus, and plus. 60 times every second, it goes through one full waveform. What would the voltage of my generator be?
0.
No. I mean, it's 120 volt AC. What would the
60.
volt? No.
It'd be 60. Oh, I was thinking 60 positive.
240? 240?
Nope.
Well, at peak, it's going to be 120, but
Nope.
on average,
That's actually wrong.
really?
Yes, that's wrong. Because how much is this? If I were to draw the current coming out of this thing and the voltage coming out of this thing, the voltage would look like this. It would always be the same. Do you agree with that?
Yep.
Yes.
Okay.
Well,
By
for
Ohm's
DC,
law,
yes.
by Ohm's law, P is equal to I times E. If the voltage is always constant, what is the power? That would be constant,
Always
right?
constant. As long
How
as
about what if I did this? If I did Ohm's law for this one, and
It's going to
what's the voltage
be
right here?
variable between 0 and then
Yeah.
at peak, it's going to be something.
What are the voltages whenever what's the power
zero.
whenever
That's
the
zero.
voltage? Yeah, whenever the voltage is 0, I get no power. Whenever it peaks, I get, whether it's plus or minus, I get a lot of electrons moving with a lot of push. And the formula actually is P is equal to V squared over R. And notice because it's squared, if this is really big negative, it's still a positive number. So my power actually ends up looking like this. But what happens in this time when it's 0? How much power is there?
0.
There's nothing. Yeah. So
Right.
what we do is we do something called, somebody mentioned it, RMS, which is root mean squared, which is basically a time average. So in order to generate the same amount of power that a 120 volt DC battery makes, this has to peak at about 170 volts. And this has to peak at about negative 170 in order to make the same amount of power. So if you were to stick your meter into the wall, you would see it would say 120 volts RMS. If you were to put it on an oscilloscope, which was which gave you a picture of voltage versus time, it would look like that, and it would peak at 170 and at negative 170.
And how did you get 170, that number?
Okay. How did I get that? Well, I have the time average of voltage squared R, because power is equal to voltage V squared R. And what I have to do is I have to take the integral from 0 to time period t of V squared R dt divided by the time interval t. And it turns out that once you do that, you end up with the square root of 2. You have to multiply it by the square root of 2. And this is RMS power.
Do
And then
we
you have
need
to
to know
divide.
this for the test?
No, you do not need to know
Thank
this for the
God.
test. But it is but it is significant to know, and because this is what's happening in your wall. So yes, but no, you do not. However, when you do take your general and extra class exams, which you will, because that's where it starts to get really fun, you do need to know what RMS is. You don't have to do the math behind it, but at least now you've seen it. So,
Or if you're buying speakers, you want to know what RMS is because
yes.
they lie.
Mm-hmm.
And I'm going along with that other lady. It's like, wow, I didn't know I was going to be working on a nuclear submarine. You know?
And RMS is root mean square. Is that correct?
Yeah, it's root mean square.
Root mean square.
So you have to integrate the power and then divide it by the time. It's basically a timed average, and then you figure out what voltage would have what it's equivalent to. All right. How about a 5-minute break, everyone?
Sounds good.
All right.
Sounds good.
Hello again, everyone.
Hello.
Hello.
Hi.
Okay, so we're doing AC. AC is cooler than DC. You know why AC is cooler than DC? There's a lot of reasons why AC is cooler than DC. Okay. All right, so now what we're going to do, is everybody ready? We're going to the
Yes.
next thing. Okay, so here's, instead of DC, we're going to draw our AC power supply. And it's AC because there's a picture of a sine wave. So that means that the current that is produced through this resistor will flow when this goes positive and this goes minus. It will go this way, and then it will pass through 0 when this thing essentially turns off. And then when it flips back the other way, this becomes plus and this goes minus, and then it goes the other way. What that means is that the electrons just flow back and forth and back and forth and back and forth. The resistor does not care. Doesn't care at all. What we're going to do now, however, is add some other components. Okay, the first one we're going to add is this. Anyone know what that's called?
Capacitor.
Yeah, it's a capacitor.
Yeah, capacitor.
Okay, a capacitor is two electrical plates that are separated by a physical distance. Big letter C, it's measured in F, which is farads, named after Michael Faraday. Like I said, if you were alive in that time and you worked on stuff like that, you got stuff named after you. The way that a capacitor works is that because these plates, these are actual metal plates, are separated by a distance. If I were to hook this up to a battery, what would happen is I'd get positive charges here, negative charges over here. And what do positives and negatives like to do?
Cancel out.
They'd like to cancel out. They're pulling toward each other, right? Okay, but what is happening right here? They are physically being kept apart, aren't they?
Mm-hmm.
By the space between them. So the space between them and the amount of charge on them determines how much force there is that the capacitor is basically allowing to exist. Because these things really are trying to pull each other together. And the physical capacitor is separating them apart. That is a storage of energy. That's a storage of, physical force.
No.
So that's energy storage. The desire for these things to get together, pulled together by electric charge, that's known as an electric field. So a capacitor is an energy storage device that stores energy in an electric field. We're going to add another one now, which is just a coil of wire. This is known as an inductor.
Mm-hmm.
Given the letter L, measured in henries. Henry was another 19th century scientist. I believe he was Scottish.
Let me guess. This one's going to store energy in a magnetic field.
This one stores energy in a magnetic field. And the way to explain why is that what we're going to do is we're going to take a current, or we're going to take electrons and move them this way. Oh, I take that back. Let's make it a current. Okay, so we're going to make a current that goes like that. Okay, so it goes from right to left. Everybody hold up your right hand with your thumb sticking out. Now take your fingers and roll them forward over your thumb. So it looks like that. That represents the direction of magnetic field generated by a current that is moving in this direction, whether it's in a piece of wire or otherwise. So essentially, that magnetic field exists at all different distances. The farther you get away from the wire, the weaker it gets. If you change direction, it will change direction as well. For DC, it's always one direction. Kind of boring. But the interesting thing here is if a magnetic field exists, then we're going to draw two wires. We're going to have a current here with a magnetic field here. Is that second wire in the magnetic field of the first one? What do you think?
It looks like it.
Yeah, okay. So if that second wire is in the magnetic field of the first one and a current makes a magnetic field, what do you think a magnetic field makes?
An electromagnetic
Electrical current.
It makes current. That's right. And in fact, it will generate an electrical current. This is known as induced current. Thus the term inductor.
Oh, in your second wire.
In the second wire, you will have an induced current in the second wire. Actually, it's going to be going the other way.
Is there an equation for what that induction looks like?
Yeah, I mean, you don't have to know it. But just the fact that this exists is actually really important because this is the basis for a lot of different things in electromagnetics.
This way?
The two keys are one, they're both storing they're both storing something, but one's an electric field and the other's in a
Magnetic field.
magnetic field.
Yep. So what's important about this, however, is that once a magnetic field is created, there's energy flowing. There's energy stored in the field. It doesn't like that field to be disturbed. If I were to cut off the current, for instance, right here, and take that away, now what do I have? I have energy in a magnetic field. And where does it go?
It just
Wouldn't
hangs
it just
out.
dissipate?
It can't.
Wouldn't it collapse?
Energy can neither be created nor destroyed. So where does it go? It moves things in the air. It causes a current.
Heat?
It has nothing to if it dissipates, yeah, but what it usually does is, depending on how this wire is built, it will cause a current to flow in the other direction, and it will generate a voltage in order to do so. So
Static electricity? Is that? Static electricity? Is that would cause like shocking somebody? No.
No. But so instead of that, what I can do, for instance, I can take my coil, and instead of having it be a straight piece of wire, now this is an inductor, and the magnetic field, if I flow this way, will generate a magnetic field that goes like this and like this. But the same effect is true, that if I have a battery that's generating it and generating a current, and I suddenly disconnect the battery and I turn the current off, now I have all this energy that's flowing and it still exists around here. I still have this big magnetic field that exists. What will happen is that magnetic field will have to figure out a way to get rid of its energy. Where's the most convenient spot? Right there. And what will happen is this magnetic field will eventually dissipate, and in the process of doing so, might generate, I don't know, 5,000 volts and cause a spark to jump across. So does anybody know where this can actually be used to our benefit? If you drove anywhere today, you probably use this.
Alternator?
Nope. Thank God, no.
Oh, what are you asking? One more time?
Alternator?
No, where would this be used if you drove somewhere today?
Ignition coil.
Ignition coil. This is how you make a spark. inside your, this is how you make a spark and deliver it to the inside of your cylinder to ignite gasoline or other combustible material. You intentionally, you create a current and then you intentionally shut it off and force that magnetic field to go somewhere. If you direct it properly, you direct it down to your spark plug terminal and you cause it to generate a very, very big high voltage spark inside your cylinder, which ignites your gas. Basic electromagnetics. Pretty cool, right?
Yep.
We use it every day.
Yeah.
It's amazing that it doesn't destroy your spark plugs faster than 100,000 miles anymore. Okay, so now what we're going to do is, now that we've covered inductors and capacitors, now we're going to start making them a little bit more interesting. So here's our DC circuit, right? We're going to use a 12-volt battery. Now, where do you find a 12-volt battery, everyone?
Inside your vehicle.
Inside your car.
In your
Okay.
car.
Yep. Okay. So let's put a resistor across it. And we're going to get current out of the plus. It goes like this. Does it matter to this resistor whether or not the battery, I don't recommend doing this in your car, by the way. There are some things that will care. The current flows the other way. Does the resistor care?
Nope.
Nope. Resistors are dumb and boring and they don't care. Okay. But now what we're going to do is we're going to take this power supply and we're going to draw like this. And we're going to make a plus sign and a minus sign. And here's our capacitor. Okay. When this is plus and minus, this side charges up to plus and this side charges up to minus. Once it's full, because this is a physical thing, once it's full and it can't hold any more charge, how much more flows into it?
Nothing.
Nothing. Well, what does nothing look like? If no current flows, that looks like this. Agreed? It's an open circuit. You can't stuff any more into there. So the current has gone to zero, which means it might as well be an open circuit. So now, instead, let us rapidly change this back and forth. So now it looks like that. Well, the minus charges go this way, the pluses go this way. Then you're now empty. And then if it sits there a little bit longer, you end up with this. Well, if that's the case, every time you flip it faster than the capacitor can charge up. If you flip it faster than the capacitor can charge up, does it look like the capacitor is ever filling up?
No.
No.
Nope.
And in other words, for AC, it looks like this. Why can't I draw that? There. For AC of a sufficiently high frequency, a capacitor looks like this. What does that have a name of?
Short circuit.
A short circuit. So for AC, a capacitor is a short. And for DC, a capacitor is an open. Okay. So now we're going to look at this again. Okay. So what's this thing called again?
Inductor.
That's an inductor. It's a coil of wire. And I establish a current that flows this way. So this is an inductor. Are we looking at AC or DC if I have it always going the same way?
DC.
DC. Okay. And if it's just a piece of wire and it makes a magnetic field in it and then it's stable forever, the key is it's stable forever. That means the current's always flowing. What does it mean if current's always flowing? What does that look like? At DC, an inductor looks like a short. But now, if I start flipping it back and forth, I have this magnetic field, which we already said doesn't like being changed. That's how we use an ignition. That's how we do an ignition system in a car. It fights back. If it fights back every time you try to change the current and you do it really fast, this starts to look like this. Uh-oh. Well, now we have a problem. Now we have a problem. Because
AC, they're not compatible?
Oh no, they're totally compatible, but that's not the point. They behave completely differently. So, well, being, engineers, we can use this to our benefit. Let's say we have a voltage source that looks like this. Right? So this is our 0 volt line. What does that look like? What does this thing look like? Looks like a sine wave, right?
But it's off zero, though. It's not
But it's
talking.
off zero. That's right. So, but it looks like a sine wave. If I were to shift this down a certain voltage, it would look like this, right? That would be a sine wave, a real sine wave where it's centered in the right spot. This is a complex waveform. This has an AC component and
A DC.
DC. They're added together. Ah, okay. Well, now, what if I were to do this and take that voltage and do this with it?
Oof.
Okay. Well, I take that voltage, and what did we just say about an inductor? For an inductor, AC is an open circuit, and DC is a short circuit.
Yeah.
The DC would go here. The AC would go here. How about when the AC, how about when whatever was left got to the capacitor? What does a capacitor look like for AC?
Short.
AC goes that way. And any DC that's left, it's an open circuit. So what does it look like when it gets to an open circuit?
Open.
If there was any DC left, it gets blocked. So what do we now have?
A sine wave.
Yeah, we have a sine wave here, and we have DC going this way. And what have we been able to do?
Make a complex.
We just
Still
filtered.
voltage.
Clean up
We just built
a
a
wave.
we just
Oh,
yeah,
a
we
filter.
we built a filter that separates AC and DC. Yikes, right? Just by adding components, we were able to separate AC and DC. Where do we find it useful to do this? Let's say we were to take this and we were to flip it the other way so that I drew it like this.
For an antenna?
Nope. You're using one right now.
Choke.
Yeah. So what goes through here? AC or DC? What goes through a
That
capacitor?
would be
AC goes through a capacitor, and DC goes through here.
yeah.
So most of our power supplies that convert AC to DC.
That's right. You're using one right now to run your computer, aren't you? That's the basis of something called filtering. It's how we separate AC and DC. And in particular, this would be known as, because what's the frequency of DC? How many hertz? That's a weird question, right? No.
Yeah.
How many hertz? How much does it
60
change?
hertz.
Zero.
DC has 0 hertz frequency.
Oh.
AC, in this case, is 60 hertz, or it could be 120, or it could be any number of different things. Well, what this means is we have created a filter that, looking at frequency, looks like this. It's open, 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 and then drops off. And at a certain frequency, it doesn't allow anything through anymore. We've managed to separate out frequencies by using capacitors and inductors. Depending on how you build them, that determines which way it works.
Yeah, I was going to ask that question. What's the difference between a low filter versus a high filter?
Well, what frequency is coming through? How many hertz?
0.
Okay.
DC.
That would be passing through the filter, so that would be a low pass filter.
Okay.
If we wanted it to be the other way,
So that's a low pass.
if we wanted it to be the other way, it would be a high pass filter because it would pass higher frequencies. Now, as it turns out, the next and really cool part of this is that there's actually something called impedance, which is related to resistance. Okay, resistance is the opposition to DC current. Impedance is opposition to AC current. For a resistor, they are equal. Does that make sense? Because a resistor is just like a block of carbon. It doesn't matter what's going into it. However, we know that for a capacitor has low impedance. And we know that an inductor for AC has high impedance. And that's because if you switch the frequency fast enough, a capacitor looks like a short circuit. If you switch it fast enough, an inductor looks like an open circuit. It turns out there are actually equations because this doesn't exist in the extreme, that this is negative 1 over 2 pi fc, and this is 2 pi fl. And that's known as reactance as well. So reactance, impedance, et cetera, et cetera. And you know what? Let's just not use impedance. I'm going to change that.
What's the L?
Inductance.
Okay.
We're going to change this to reactance. There we go. Impedance is opposition to AC. Reactance and impedance are similar. Impedance is actually the sum of reactance and resistance, and it turns out they're at right angles to each other. So, but the key here is that what's that little letter F right there?
Frequency.
Frequency. Aha. So, how an inductor and a capacitor behave in the presence of
frequency.
AC is dependent upon what?
Frequency.
Frequency. They are frequency dependent devices. They behave differently. So when you build a filter, it's dependent upon the capacitance and the inductance and the frequency at which it's being used. Well, so what becomes really cool about that is that I can do this, for instance. And I can have this be tunable. That means that it's variable. Like I can take a resistor that's 300 ohms, and I can do this with it, and that means I can vary the value. That becomes known as a potentiometer.
Okay, I was going to ask what the line in between.
Yeah, that means it's adjustable.
Okay, right.
So if I can do
arrow, right? Just to be clear.
just an arrow. So if I can do that with a capacitor, and I can do that with a capacitor, and I can do that with an inductor, I can make them by having this, I can say that this value is, let's say, between 2 to 50 henries. And this is between 30 and 500 picofarads. And this is between 30 and 500 picofarads. And by having those values be variable,
Tunable.
It becomes tunable, which means that I can make a filter that looks like this, or I can make a filter that looks like this, or I can make a filter that looks like this. I can do all kinds of stuff. And the more capacitors and inductors I use, the more it changes. So this allows me to select different frequencies by changing values, by selecting individual values. And in fact, if I were to do this, and I'm not even going to make it variable, I'm going to just say I have a capacitor followed by an inductor. This has an XC, X is reactance. This has an XL. This is actually negative, and this is positive. I could make them so that at a given frequency, these are equal and opposite and cancel each other. Well, if they cancel each other, it looks like they're not even there. And if they're not even there, they're not even there. What's the resistance or impedance of this piece of wire? That would be 0.
Sorry.
This is known as resonance. And being able to build resonant circuits is a basic basic function of what we can do with capacitors and inductors and why they're so cool. What that really means is,
sorry, I have a question.
Go ahead. Yeah.
You think of resonance as the baseline?
What you think of resonance as is the ability of something to resist AC. So if I have frequency here and it starts at 0 and goes to infinity, at one point my resistance or my impedance will do this.
Oh, they equal each other.
And this right there is the point at which the circuit is resonant. And you can hear this actually. Mechanical resonance is, for instance, if you take a fork and you bang it, you notice that it rings like a tuning fork at one frequency depending on its size, and it will do that for a long time. An electrical circuit behaves the same way, except that it's electrons back and forth. It allows them to flow essentially infinitely back and forth by passing energy back and forth between electric and magnetic fields.
So as you tune, that dip changes, moves across the line.
If I were to make this a tunable circuit like this, and I have a variable values here, I could take this point and shift it back and forth.
Okay.
That's the basis for how a tunable radio works. Yeah, it's pretty cool stuff. All right.
In reality, on the radio, normally your knob doesn't do both the capacitor and the inductor.
Normally you'd only do the capacitor because it's a lot easier to build.
Thank you.
Hey,
But
Scott,
yeah.
Can you throw that diagram back up there? I just figured out how to zoom out and zoom in to see it.
Like this?
The one up above it that you had.
Oh, like this.
That made a V. Yeah.
Oh man, that looked terrible. Let's do that again. It's kind of hard to hold my hand perfectly still.
I couldn't see it all, but you said it was
I threw it into the chat.
Yeah.
It's a resident. Is that right?
Resonance. Yeah.
And resonant is what now?
Resonance for this circuit is the point where the impedance or the reactance, because this is a negative impedance and this is a positive impedance, and this actually is minus J over 2 pi FC, and this is plus J 2 pi FL. You don't
John,
need
can you label the lines? Can you label the lines on the bottom?
Yeah. Yeah, you don't need to know this until you get your extra exam.
Okay.
And don't say, "Oh, I'm never going to do that." So, just know.
General.
Hey, Scott, can you label the lines on the bottom?
Right. So this is your frequency, and this is your impedance.
Oh, okay.
and you have a 0 line and it goes up, and you have a 0 line for frequency and it goes up all the way up to infinity. So at one particular frequency, which is defined by when this and this are equal and opposite, they will cancel each other out, and you will have no resistance to AC flow. And that's your resonant frequency. Right there. And in fact, it's never going to be perfectly 0 because, you know, the inductor is still a piece of wire. It has a little resistance. But this is the basis for tuned circuits.
I don't know what we were missing, man, all our lives.
I know, isn't it cool?
Yeah, it is.
This
I mean,
is
I was in telecom all my life, but
this is
the DC circuits were boring. They weren't, but anyway.
DC circuits are more boring. AC circuits are kind of magic.
You can do a lot with it though.
Yeah. Oh, yeah. Okay, so here's the next thing we're going into. We're going to take 2 inductors and put them back to back. Right? What we're actually doing here is we're taking a coil and we're winding it on an iron core. Iron is a very special kind of material. Steel works really well too. They are ferromagnetic, which means that if you try to create a magnetic field, the magnetic field will become concentrated in that material. So basically, if we create a magnetic field by running a current into this right here, what we'll end up with is a magnetic field that circulates inside this iron. When the iron gets to the other side, over here on the right, it will induce a current to flow in this wire. Anyone know what this thing is called?
Transformer.
That's a transformer. Depending on the number of turns of wire on either side, that determines what the ratio is. So if we have, let's say, 120 volts AC, and this only works with AC, we could do a 10-to-1 ratio and get 12 volts AC. And where would you find something like that?
Hanging on the side of on your telephone pole.
Well, not at those voltages.
Well, I mean, yeah, but
yes, where would you find one of these?
Inside your wall wart.
Inside your wall wart, exactly. So that's another use of inductors. This is the beginning of a power supply.
And the current increases, correct, on the right-hand side?
The current increases, and the reason being because
of that, yep.
And because energy can neither be created nor destroyed. So what doesn't come out is heat. These things are usually very efficient. So if you increase the voltage, you decrease the current, and vice versa.
And hence why we have very high voltages running, on power lines.
Exactly right.
We drop that power back. We drop that voltage down. Our current increases.
Right. So
in the example you said, you find that 12 volts, an example of what? What again? I couldn't hear, Jason.
That's a wall wart.
A wall board?
No, wall wart.
Oh, okay.
But this is
what's a wall wart?
A wall wart is what you plug in to run your computer, to charge your phone.
It's your power.
If you have a laptop computer, the little brick.
Yeah,
it's not really a transformer anymore, but
well, no,
anything that you plug into the wall.
There is a small transformer in there now. There's still a small transformer.
Oh, even with the new ones?
Yeah,
okay.
It's just not that big. It's there's still a transformer in there. So this is what you would find out on your power pole. Notice that says 7,200 volts.
Mm-hmm.
Yeah.
And in fact, in most cases, it's not 7,200 volts. It's 14,000
Wow,
volts.
like 14, yeah.
Yeah, it's 14,000 volts.
And
So
we have a
those,
lot of voltage right at that point.
yeah.
That can
So
go a long way.
yeah. So let's say that you draw, let's say you're using 10 amps at 14, let's say it's only 12,000. That makes the calculations easier. This is 0.01 amps to deliver the same amount of power. And because losses in your cable are done by P equals IE, which is equal to I squared R, notice that your current is very, very low. So your power loss is very low. So you can use very small wires on your power lines. They don't weigh very much. They can transmit large amounts of power over long distances. That's why a generating station might operate at 750,000 volts AC. Okay, next, we're going to cover nonlinear circuits. Any idea what this is called?
Diode.
A diode. A diode, just like if you see a one-way sign, it looks like this. That's a one-way street. It means you can only go that way. A diode will only carry current in one direction. So if I were to draw a circuit that looked like this, which is an AC circuit, which looks like this, and here's a diode right here. What would happen when, if it only carries current in one direction, when this is plus and this is minus, I would get current flowing through the circuit. That would be the top side. However, on the bottom side, when I'm negative, I would then have a plus sign here and a minus sign here, and I would try to be flowing current back this way. And what does the diode say?
No,
Nope. Diode says, nope, I'm not doing that. And in fact, it takes a little bit of voltage for the diode to turn on. It operates at typically, if it's a silicon diode, it's about 7.7 of a volt. If it's a germanium diode, it's about 0.3 of a volt just to turn on. But essentially, we can say that it's basically a one-way street. What that means is, if I have a voltage waveform that looks like that, which is going plus and minus and plus and minus and plus and minus, I have now, because of using the diode, taken away the bottom part. If I've taken away the bottom part, what do I see on the other side?
DC.
It's ugly.
Yeah.
Half wave.
Half wave
DC.
rectified DC. Yep. Now, if I were to take this and put a capacitor here, what would happen is that at the peak, the capacitor would charge up completely, and when it started to break down, when it started to dissipate, the capacitor would discharge into, let's say, here's my load resistor over here. And what would end up happening is it would look like this, which is closer to DC. Well, I can also add another device in here, which is a special diode. Remember I said that diodes only conduct in one direction?
Yeah.
Okay, well, that's not always true. This is known as a Zener diode, and it's a voltage reference diode. It basically says that below any voltage, any given voltage, it will be stable. If it gets higher than that voltage, it'll break down and it'll allow current to flow. And what that does is say, let's say I want a 5-volt Zener diode voltage reference. So that will say that here's my 5-volt line. Anything above will just basically drive down through the diode, and it'll knock the top off.
Like gives you that flat.
And
Is
that
that
gives
a-
you a nice flat line.
I was going to ask if that's a flat line above there.
Yep. So what does that do for you? What do I now have? Notice how many volts I drew. How many?
AC to DC converter.
It creates a constant voltage.
Yep. Where do we find a 5-volt device?
Oh, your
Your USB.
USB charger.
Oh, really? Is it US 5 volts?
Yep. It's a very basic USB power supply
In
for
the day
charging your
when I
phone.
used to have to wire up those little 5 and 10 button phones and the consoles that go with them, they were 100 pair.
Yeah.
and then you'd want one phone. Somebody wouldn't want the phone to ring on one phone, and they want to ring on the rest of them, or they all got really picky and decided they didn't want. You had to put all those diodes on a board,
Uh-huh.
and it was a pain.
Yep. Well, it was just allowing certain things to turn on and off.
Yeah.
So yeah, but this is basically how a diode functions as the core of a power supply.
Yeah, this is much cooler.
So another kind of diode that we do looks like this.
That's a light emitting
And
diode.
that's a light emitting diode. And instead of just allowing voltage to pass through, when the light emitting diode turns on, it allows light to come out. We use these for lighting. We use these for on-off circuits. We say, oh, look, it's on. The thing turned on.
Can we tie that back to the spectrum you showed earlier today?
Which part of it?
Put a correlation there.
No. Well, I mean, you can, but essentially it's depending on how it's built. A diode looks like this. It's a semiconductor like silicon or germanium. And depending on whether or not you put a few excess negatives in it or a few excess positives in it, that turns it into P or N silicon or semiconductor. And what that does is that it biases it so it only works in one direction.
Okay, but the light
The light is determined by when that junction works, what doping materials are used to actually generate light.
Okay.
Certain combinations make red, certain make green, certain make blue. All right. So the next thing is I can add something else to this. And what we're going to add is another block. Oh, I don't know why that came up like that. We're going to add another block. We're going to call this another N. It has some extra stuff in it. Now we have 3 terminals. We can do this with it. And now we have 3 terminals. Notice there's an N, a P, and an N. This is a transistor.
Yeah.
And a transistor is basically a gated device. So by applying a signal to the base, as it's called, and here's our collector, and here's our emitter. By applying a signal to the base, that determines how much current can flow from the collector to the emitter.
You open and close it.
Essentially, yes. But now we can use this in 2 different ways. We can slam this door totally closed at the base and open it wide. And we use that as a switch.
Mm-hmm.
We can also make it so that it's partially open and partially closed. And then it becomes an amplifier.
So one more time to make it a switch, you do what? You close
slam it open and closed.
Which one's the base?
The base.
Okay.
Essentially, this is a doorway.
Yeah.
By opening and closing the door completely, that allows a flood or nothing to go through, and that's a switch.
And to make it an amplifier, you do what?
Partially open it and partially close it. You essentially modulate it.
Okay.
And that determines how much it's going to get through.
So you send a little sine wave or signal into the base.
And this makes a much bigger copy.
Yep.
And in fact,
but you can have higher voltage going across that end to the other end, right?
Oh, yeah. And in fact, a transistor amplifier, a transistor looks like this. It has 3 regions. It has cutoff, linear, and saturation.
So that's your cutoff. That's your saturation.
So cutoff and saturation, that's.
And then what's in the middle?
Linear.
Linear, okay.
It's more or less a straight line. So this area is used for an amplifier. And these 2 areas, cutoff and saturation, that's a switch. That's what we do in computers.
really
You
fast.
oh, quick question. The
Mhm.
NPN it controls current.
That's well, the key is
Or-
that
more than that.
what I'm going to do is I'm going to redraw this. This is a transistor schematic. That's a schematic symbol. So here's the base, collector, emitter. A small amount of current on this base to emitter allows a huge amount of current on the collector to emitter path. It's like that's split down the middle, like that.
Can you say that again?
A small amount of current from the base to the emitter allows a huge amount of current on that path.
When you say huge, what's the ratio?
100 times,
I'm sorry, how many?
100, 200 times.
Okay.
It can be a lot. There's and this is known as a bipolar junction transistor, or BJT. There's another way to build a transistor. What does this thing look like right there? Let's see how.
Capacitor.
That looks like a capacitor. The capacitor works by way of an electric field.
Right.
This is known as a field effect transistor.
Okay. FET.
Essentially, instead of running a current, you put a voltage across this. The amount of voltage that you put across allows a huge amount of current to flow from the source to the drain.
Can you draw an IGBT just for shits and giggles?
An IGBT is very similar to a FET
Okay.
because it's an insulated gate transistor.
Okay.
Although I think
So-
it's an insulated gate bipolar transistor, but it's still an insulated gate.
Yeah.
So
So the BJT, a small amount of current controls a lot of current.
Right.
The FET, a small amount of voltage, controls the
A lot of
current.
current, yep.
A lot of current.
Yeah.
Okay.
So if you
It's
want to
always
think of it that
controlling
way,
current.
yes, current is the main thing that's getting control. So
Thank
that's
you.
known as a bipolar junction transistor, and that's a field effect transistor.
And you said over here on the FET, you said the V is. I see the V is coming in.
Well, it's
what is that?
actually
Yes.
it's voltage. The terminal's the gate.
Okay, voltage. And then what's the S again? Up on top?
The source.
Source.
It's 1530.
And
Yeah.
then
And the D is the drain.
drain.
So this is the gate. The gate, drain, and source.
Gotcha.
And again, you probably don't have to know all of those, but it's important to know the difference. I know that the
So-
BJT and the FET are both on it.
So the BJT is a current. It controls current.
Yes.
And FET controls voltage.
Yes. Voltage controls current.
Voltage controls the current. Okay.
Yeah.
They're both current. One's being controlled by current, the other one's being controlled by voltage.
Which one is more like a vacuum tube?
Probably
The BJT.
No.
BJT.
No.
Really?
It's a
The
field
FET.
effect.
Yeah.
Yeah.
Oh, really?
Yep.
Wait, I thought vacuum tubes were current controlled.
They are voltage controlled because you have basically by changing the voltage on the plate, that determines how much current will flow
Ew.
from the plate
Okay.
from the cathode to the anode.
Can you say that one more time?
You're
So
not going to
the
have
B-
to know that.
The BJT, the current is the controlling factor for the voltage. Is
No,
that
the
do I
current,
have that right?
the input current controls the output current.
They're both current. You're both controlling current.
Always controlling current. In a FET, you're using voltage to control current. Okay. Let's see. How about a switch?
Can I ask you a question?
Yeah.
Sorry. So, when would it be important to? Well, what am I trying to say? A BJT versus a FET. So they both.
Why would you ever pick one over the other?
Yeah.
Efficiency.
efficiency. Okay. And what were they be used in again with a scheme of? I know you talked about a vacuum tube.
Well, either as a switch or as an amplifier.
Okay, switcher. Okay, got you. Going back to what we first talked about.
And it depends on the region in which you use it. The output region in which you use it.
Oh shoot! What happened? Okay, I'm back.
Other questions? It's just about lunchtime.
Can you provide an example of where I would put voltage in versus current?
How about on a computer chip? Your microprocessor is literally
yeah.
exclusively built out of FETs.
You mean just a small chip that you like a Radio Shack chip?
Like an Intel microprocessor.
Right. Where it's got the little legs on it and you plug in?
Well, it's a lot more than that. There's a billion transistors in there.
Right. Okay.
And it's a lot easier to design a FET onto a tiny chip, onto a tiny multi-layer chip. Because, you have two pieces of aluminum and a gap in between. That's a gate.
Mm-hmm.
You basically just build it into it.
Radio Shack. I need to go find my Radio Shack kit again and start building it.
Other questions?
Scott?
Yeah.
Hi. As someone who is looking to volunteer in my neighborhood as things go bad and to be a ham radio operator, is there any way that you could, when possible, tie into, we're learning all this stuff, how would we use this in a day-to-day? We're sitting in front of our screen with our handheld thing. Do you see what I mean?
In other words, how does this apply to anything?
Well, and not just for
really,
the exam. I mean, I appreciate that you tell us this will be on the exam. That's very helpful, and I'm using the study guides.
Mm-hmm.
But I'm just wondering, do I really need to know this for day-to-day use?
So here's the thing.
Yeah.
Here's the thing. There are lots of things that you can do other than. I mean, I do FRS. I'm part of a CERT team. I do MCOM. There's, I do GMRS when I need to. What amateur radio is, it's the Swiss Army knife. It really is. And what this allows you to do is, okay, well, so you got this stuff. Let me ask the question. What are you going to do when what are you going to do when a big windstorm comes and knocks down the tree and destroys your antenna?
So this is mainly to fix things, would you say?
Well,
if things go wrong?
No, if you know how something works, you know how to make something work out of nothing.
You could build another antenna.
You can build a new antenna. You know what works and what doesn't, and why it works and why it doesn't. That's really the power in this. The fact that you basically have a much deeper understanding, and you're not just connecting something together with something else and hooking it to a computer and doing something.
This is much deeper than your basic electronics and I think what you're saying, like with the emergency, like with certs, like you talked about, or emergency, network, that the ham radio, like a spotter, like we had a high winds come through here a week ago Friday, and all the ham people were spotters through the National Weather Center. But if you can build your own system where you're up and running when everybody else is down, and something goes south on you, then you can build it, right?
The other thing is you develop a much deeper and better understanding of propagation and why things work the way they do. And when do you need an antenna that's more capable than something else? And how do you make it?
Yeah.
This is really, I mean, if you want to think of it, the stuff that we learn is the ultimate electronics and communications toolbox.
I was in telecommunications for 27 years, and I started out analog and then worked in through digital and then retired back in 2006. But it was mostly telephone work and fiber optics and all that stuff. But when you're talking about radios, it's really at another level that is so cool because it takes you to that different level. And there's so much to it. It's what I see. I'm learning so much.
There's a lot to understand about propagation. There's a lot to understand about polarization of antennas. We're going to get to that very shortly, and how that all works in with everything else. I mean, everything works with everything else. I mean, let's say you take let's say you have an antenna on the roof of your car, and you drive into an area, and the radio that you're using doesn't work worth a crap. Right? I've had that happen.
Yeah.
And it turns
Arizona
out that
or West Virginia.
No, this was just locally. And
local. Okay.
The reason, like in my neighborhood, the reason it didn't work worth a crap was because in that particular area, that particular radio on that particular frequency was getting bombarded physically because of where I was by so much RF that it was desensitizing the receiver because the filtering was so bad on the receiver.
Yeah.
And there was enough, because the antenna was bigger than it needed to be, it was receiving even more stuff, and the receiver couldn't do its job. Did you have
to filter it out?
No, I ended up getting a better filtered radio.
Okay.
But essentially the receiver, if there's no selectivity, it was just being completely desensitized. Mm-hmm. And if that happens, essentially it gets into a position where it's overloaded, just like a person. Being able to understand what's happening is really, really helpful. So.
Thank you.
Yeah, and that is how you find grow houses in your neighborhood. So. It's true.
Those lights are noisy.
They are noisy. Actually, the FCC cares. There are FCC approved lights and there are unapproved lights. They're not allowed to interfere with us.
Oh, what do you mean? Which lights? I'm sorry, I didn't hear that again.
Grow lamps.
What is that again? Row lamps?
Grow lamps
grow lamps. Really?
For pot grows.
Really?
Yeah, there are RF quiet lights and there are RF noisy lights.
Oh wow.
And the noisy ones are, let's just say that they are unintentional radiators, and if they interfere with us, they got to go. That's another thing. That we're the ones with the license. They are not. They got to go. And the FCC does care.
Yeah, because before you know it, you just got a bunch of noise everywhere.
You just have
right?
hash everywhere. Yeah. You just have
nothing's going to work.
You just have RF hash everywhere.
Yeah. As a person in Eugene, that's got to be pretty tough around Eugene, isn't it?
No, no.
Do you run into that frequently in town?
No, yeah. because people don't want to be the one who interferes with everybody.
Yeah. Okay.
That, especially before it was legal. They really didn't want to be the one.
Oh, you're talking about something else now.
Yeah. Well, pot grows.
Yeah. That's what I thought you were talking about.
Before it was legal, I mean, an illegal pot grow with RF noise, we knew exactly where they were.
Wow. Or you could have a directional finder and find them.
Yeah, it's easy to sniff out. Yeah.
Yeah, that's wild.
Oh, and that's important. That's for anything that's illegally transmitting, your GPS jammers and Wi-Fi jammers and anything else like that. Guess who's the guys that are actually knowing about it before the FCC?
We're often the ones who are most interfered with. Thus, we're the ones who are most likely to help people find them.
And
the power companies love us because things that like noisy transformers, those waste power. They want to know.
I learned so much just listening, even though I don't have my technical license right now. I got one of those old Radio Shack scanners, and I pick up all the guys here on the repeaters, with their RACES meetings or their net meetings every Monday. it was fascinating, even though it was scary. Friday, we had, like I said, 2 weeks ago here in Maryland, in Calvert, we had the a thin, basically wind shear that came through. It was 85 mile an hour winds, and all the spotters around the county, they were reporting what was happening. And down south, we knew it was coming quick, 85 mile an hour winds, people trapped in houses with trees coming down, that kind of stuff. So it was really cool because the net controllers or the races were reporting back to the public services, like sheriff, EMS, what was happening. You could see it 5 minutes before you'd get a hit on your public service, like if you're a spotter, you can sign up for that. So we were seeing that come up. We could hear it 5 minutes before they were reporting it on the internet, which was cool. So definitely the ham is where it's at.
All right, everybody ready for a half-hour break for lunch? So back at 15 after.
Sounds good.
All right, think about more questions, everyone.
Thanks, Scott.
And Joe Mandy, I'll take a look at your chat. Thanks.
Oh, sure.
Ed? No, that makes. So not defect inputs. It's okay.
Hello, EO, everybody.
Hello.
It's good.
Hello.
We got 4 minutes till we start again, so that makes it a good time to ask questions.
How many of the circle diagrams that you've been showing are there for remembering things, like the EIR circles?
There are 3. There are 3.
I'm gonna ask him.
There's, oops. Oh, I didn't want that. Oop.
One for wavelength frequency, one for the EIR, and what's the third?
Hold on. Let me do this. New whiteboard. Don, where are you located?
Fort Worth.
Fort Worth. You're not related to a guy named Ociel Rodriguez, are you?
Not that I know of.
You sound exactly the same. He's NG70. I'm going to Wallace Island with him in the fall. There's one.
Oh, is that the formula for the wavelength versus hertz?
Yep.
Man, that always gets you, doesn't it?
No.
If you don't.
Not after you've done it a few times, which we will.
I get confused between the FM versus the HF, but you know.
Between what?
I have to go back and look at my notes, Scott, but let me see. Well, you keep going. I did want to ask a question.
All right, you got 2 minutes.
Okay. You said if you test into the technical, and you should be doing like anywhere from like over 85 to 100, really, like I'm doing somewhat 90s right now.
Then you're ready.
But before I was doing, it's hit and miss. It's like it's fluctuated from the 60s to the mid 70s, and now I'm in the 80s or 90s. I think I got a little screwed up with the FM offsets, with the 70 centimeter hertz.
Yeah, we'll get that. We'll get there.
And then the band question, I had a question on the bands, but
that's just memorization.
Okay.
5 megahertz on 440 and 600 kilohertz on 2 meters. Those are your offsets.
One more time. So it's 600 kilometers on what?
600 kilohertz on 2 meters and 5 megahertz on 70 centimeters.
5 megahertz on 70.
Yep.
70 CM.
Yep. Hey, Elisa, are you here yet? Are you back?
Yes.
It is great to see. It is great to see you there. You know that Coos County Hamfest this year isn't happening.
I saw that. It looks like the closest is in Florence or Roseburg.
I don't even know if they're doing one in Florence. Are they doing?
It's on the map.
Is it? There's one in Grants. There's going to be one in Grants Pass, but where do you live?
I'm in North Bend.
North Bend. Okay. How long would it take you to get to Seaside?
I don't know where Seaside is.
Seaside is half an hour south of Astoria.
Oh, okay. Probably
take about
3 or 4 hours.
4 hours?
Yeah.
This coming weekend is the Northwest Division Convention in Seaside.
Okay. And what does that do?
It's Friday is seminars, Saturday is seminars, flea market and show stuff, and then Sunday and there's banquets and stuff like that. It usually gets about 2,000 people.
I've seen the information on the Seaside one. Somebody sent me a thing about it.
Yeah, I will be going.
And if I was to look it up, what do I look it up?
CPAC, SEAPAC.org.
Okay.
Yeah, it's if you're itching to go to a Hamfest, if you're just itching to go, and actually I was in Alabama working, or no, I was in Mississippi, and I had 2 jobs lined up back to back, with a few days in between, and I asked my boss, "Hey, can I just take the rental car and go up to Dayton?" So I went to Hamvention this past weekend. Just me and my 32,000 closest friends. But yeah, here's CPAC.
Okay.
And here's Hamvention. Hamvention. The last time I'd been there was 24 years ago, and it was just huge.
Is that Dayton, Ohio?
Yeah, Dayton, Ohio. I took a side trip. It was 750 miles up and 600 miles down. Totally worth it. It was awesome. Let's see. Okay. Everyone ready? I see we lost a few people. That's to be expected. Remember I was saying, everybody, you know what? My attrition rate, I usually expect 50%. So it just happens. So
Windows.
that's why I say, if you got any questions, you know.
I'm sorry, did you say 50?
Yeah.
Wow.
Yep. Well, it's a lot of
50 for
material.
the-
It's a lot of
50
material.
for the extra, is that what you said?
Say what?
50 for the extra, but what's it for the general? 35?
Oh, we're talking questions? I was talking about attrition rate.
Oh, I'm sorry. I apologize.
But yes, it's 35 for the general and 50 for the extra.
And you said try to roll into the general if
you're doing well. There's a lot of overlap.
Yeah, I see that.
Yeah. And
So you can skip the tech and just take the general.
No, you have to take
or
the tech.
You have to take both.
Yeah, but
Or, well,
if you
don't.
if you're doing well on the tech, I mean, you're doing practice exams and you're killing it, then you might as well just plan to take the general as well. It doesn't cost any extra, and you know, give it an extra week of studying, and you'll be ready.
Might take another month for me.
Yeah, okay. Well, whatever it is.
All
right, here we go. So, give me 1 second. I got to shut that up. Come here. Oliver, come here. Come here. No, come here. Come here. All right. Well, this is the noisemaker.
I couldn't hear anything.
Yeah, I could. I couldn't even hear myself.
Yeah,
Hi,
another thing.
Oliver. Yeah, this is Oliver.
Actually, cute.
Yeah, he's super cute. He's a good dog. He's
Yeah,
a-
it bites you at night when you're trying to put them to sleep or
sometimes.
wake them up in the morning.
Okay, there you go. Can lie here or not? Your choice. Okay. Let's see. Back to where we were. Everybody hear me okay?
Yep.
Okay, good. Okay.
You're good.
So, you know, we're kind of going back and forth through the book a little bit. Believe it or not, if you start looking at, let's say, the first 40 pages, you will see that we have done a lot of stuff. We did transistors. We did not. Oh, we did some radio wave characteristics. We didn't do antennas yet. Propagation modes. Okay. So what we're going to do here is we're going to cover some math stuff that is critically important to understand. So So here is something called a bell. And again, if you were a scientist in the 1800s, you got things named after you. This was named after Alexander Graham Bell. He named it for himself. And so a bell is a way of relating things that are very, 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 very different in scale, in size. The same way that we have a scale for measuring earthquakes, where every number is actually the logarithm, or actually the exponent, so that, for instance, an earthquake magnitude 3 is 10 to the third, magnitude 4 is 10 to the fifth, 10 to the fourth, magnitude 5 is 10 to the fifth, magnitude 6 is 10 to the sixth, so that a 6 compared to a 3 is 1,000 times bigger in intensity because it's the exponent. We have a situation where logarithms are kind of the opposite of this, but basically this is now, these are logarithms and these are exponential functions. We have something called decibels, which work very similar to this. So let's say we have a reference signal. Okay, and that reference signal is amplitude 1. Okay, so that is a unit. So we have to find something that says 10 to the something's power is equal to 1. Everybody remember their exponents? Anything to the what power is 1?
0.
0. Okay, so that would be a 0 decibel signal. And we want something that is 10 times bigger than that. How would we get 10 times bigger than that? What would we make it?
2.
No, we go 1.
Oh, 1 to 10. Oh, 1.
Right.
Yeah.
So this is actually also 0 bell. This is 1 bell. 10 times bigger would be 2 bells, and so on and so forth.
Yeah, so 10.
3 bells. So it's the same kind of linear, it's the same kind of exponential scale. So this is 1 times, this is 10 times, this is 100 times, and this is 1,000 times, and so on and so forth. Now, fortunately, with earthquakes, we don't usually get higher than a 9. However, with bells, we can get 12, 15, negative 22, stuff like that. We can get big numbers, which represents a lot of zeros that have been taken out of this whole thing. That's kind of the idea. Like if we have 12 bells, that would be 1 0 0 0 0 0 0 0 0 0 0 0 0 times. You can see why we would use that, right? That's a lot of zeros to carry around.
Mm-hmm.
Well, the other thing is, if we have a 12 bell, this is a way of comparing two signals to another, and then we have a negative 6 bells, this is 0.000001. Well, we can actually just see this and say, since they're exponents, 12 minus 6 would give us 6. And we can say 1, 2, 3, 4, 5, 6. And it turns out, no, we're using bells. We're not doing it interchangeably yet. So you can see that it just basically works on the number of zeros, which is actually very convenient for us. 1, 2, 3, 4, 5, 6. Okay. Now, it turns out that the bell was too big. So, because not everything goes in a factor of 10, so it turned out that they then created something called a decibel, which is 10 times the log of P2 over P1. So that log is, let's say, if you had 10 to the 4th power, then your log would be 4. If you had 10 to the minus 4, your log would be negative 4. So we added this factor of 10 to give us numbers that made a little more sense instead of having decimal points, because you want to essentially get rid of all the extra numbers that why would you want to have 2.16 bells when you could make it 21.6 decibels? So they went with 10 log P2 over P1. So that is the formula for the decibel. And the way to calculate this is, because it is not an absolute thing, it's, notice, a ratio. You're looking at the difference between something and some reference point. So let us say that we have a magic box. Come on. Here's our magic box. And we have 1 watt coming in here. And something happens in this box. And we have 20 watts coming out. So what would be the thing that that box did? What would you say that it did?
Gain.
Right? Of how many times?
20.
20 times. Okay. So let's say that then we went through another box. Right? So this is 20. And then we went through another box. And we got, let's say, 10 watts out of that right there.
So it reduced it by 10.
Right. So that's 1/2 times. Right. Whatever that did, that attenuated the signal. It caused there to be loss. Well, we could say 1 times 20 times 1/2 gives us 10. Depending on how many things are there, that could get quite long. So what we can now do instead is to say, okay, 20 times. We can plug that in right here to P2 and P1 because it's a 20 times ratio, and find that this is approximately 13 dB. And the way we do this is every time we have a gain of 10 or a loss of 10, power of 10, this is 10 dB. This would be negative 10 dB. And that's an exact number. Anytime we have a gain of 2 times, that is 3 decibels. 1/2 is negative 3 dB. So in order to go from 1 to 20, we had to go, if you want to think of it this way, 1 up to 2, and then 2 up to 20. So this is 2 times, and this is 10 times. And we look on this table, and we see that 2 times is the same as 3 dB, and 10 times is the same as 10 dB, and we add them together, and we get 13 dB. We can do the same thing for the next one, which is 1/2. We'll find that 1/2 is negative 3 dB, like that. And then we can add plus 13 and negative 3 for the whole thing, and find that the total gain is 10 dB for the whole circuit. And we see 1 in here and 10 watts here. Well, that's a gain of 10 times, which is 10 dB. So the math works. Where this comes into play, these numbers are fairly small, right? Where this really comes into play is, let's say that you have a signal, and we usually start with something called dBm, which is dB compared to a milliwatt, so 1,000th of a watt. We go up our feed line, and this is specified as having a loss of 3 dB per 100 feet at 7 megahertz. And this cable is 42 feet long, up to an antenna that has a forward gain of 7.4 dB. Goes through space, and we're going to be line of sight, but it still dissipates. Going to have a path loss of negative 115 dB, and then another antenna, which has a gain of 9.4 dB, and then feed line, which is going to be 4 dB per 100 feet. It's negative. And it's 68 feet long. How much signal gets to the other end, and can we hear it? So these calculations, they look a little, if these were like numerical values, you would see this minus 115. You'd actually have to write out 0.000000000 and then something 18 times. You'd have to maintain all of those zeros. So instead, we're just basically working with the exponents. All we have to do here is say, okay, we're going to start at 0 dBm. And it doesn't really matter what we start at, but we're just going to start at a 0 point. Okay, so we have negative 3 dB per 100 feet and 42 feet. So multiply those, we get minus 1.26 dB. All right, so we had a 0, minus 1.26, plus we have a gain from the antenna, 7.4 dB. And minus 115, that's the elephant in the room. That's a big one. And then a plus.
Where did you get the 1.2?
Oh.
Where did you get the minus 1.2?
Well, it's 42 feet long, and the manufacturer has specified a loss of 3 dB per 100 feet. And we're at 42 feet long.
So it'll be 0.42 times minus 3 dB.
Yeah. So that's one.
Oh, is it?
That's negative 1.26.
So it's 4.2 times 3?
Yeah. Roughly.
So it's 1.26?
Yeah. And its loss. I'll make it a little cleaner. Okay. So
7.4.
The 7.4 is the gain of the antenna. I just picked that out of the air.
Oh,
okay. It's a fairly good number for a.
So
for
it's
a
a minus, and then you're adding.
Right, and then over here, plus 9.4 for that antenna. And then notice we have minus 4 dB per 100 feet, and it's 68 feet long. So we're just going to say that's about 3 dB. So let's grab the calculator, minus 115.
Is it 3 times, would you say it was 3 times 0.68?
Well, it was 4 dB per 100 feet and 68 feet long.
Oh, it's 4. Okay.
It's again.
He's using a different cable on the right side.
Different cable on the other end. Yep.
Gotcha. Okay.
And different antenna.
So that's
antenna.
272.
Yeah. And
Gotcha.
these are real world things.
Right.
So 1.26, let's see, minus 1.26 plus 7.4 minus 115 plus 9.4 minus 3 is minus 102 dBm.
Okay, so I still don't get how you got the minus 3 dB and the minus 1.26
Okay.
at the beginning. Yeah,
Well,
but where did
okay.
you get that?
Okay. The manufacturer, this is how cables are specified. At a given frequency, they have a certain loss per 100 feet of length. And I used a certain length. So if it's minus 4 dB per 100 feet and I use 68 feet, so that's 68 out of 100 times 4. And over here, it was 100. It was 42 feet times 3.
And it's
Is
negative.
the one on the right somebody that I'm sending to, and that's their antenna and what they're receiving? Is that what's supposed to be?
Yeah. I mean, it's just, it doesn't matter whose it is. Those are just, what exists. You're trying to see if the signal that gets sent will get to the other end.
So in reality,
Okay, thank you.
So if you started with 1 dBm or 1 milliwatt, you would have 102 decibels of loss. You'd have 102 decibels of loss in that path. Why is this important? Because that would say that, let's say I have a receiver that, remember what this means. That is 10 log base 10 of P2 over P1 is equal to minus 102. That's the same thing as saying, okay, well, how much power did I lose? I have this much power left. 0.000000009 watts, milliwatts. This is how much power it actually gets to the other guy. So, or you can just say it's minus 102 dBm.
And question for you. How do you know if that's good or not? How do you know if he's getting it 102 dB?
Well, it depends. And then you have to look at, this is my receiver, and my receiver is specified as being good down to minus 108.
Oh, okay. So you're good.
That's your sensitivity.
If that's true, if your sensitivity is good enough, then you're fine. But let's say that your receiver is good down to minus 90 dB.
Then you're not good.
Then you're not good. And you have to do something to fix that. This is why understanding how signal strengths work, this is kind of like on a macroscopic viewpoint. And this is why decibels are very, very helpful. Because everything, if I start with a milliwatt over here, how much loss do I have? 102 dB. If I start with 1,000 watts here, how much loss do I have? 102 dB. But since I started at a higher point, this is just a ratio. Looking at the whole thing as a system, from output to input. So that maybe that says, okay, my receiver will work if I jump up from 1 milliwatt to 1,000 watts. Maybe all of a sudden my signal works and gets to the other side.
The 102 dB equates to how much for loss again? If you were
10 to it's 10 to the 9th power.
10 to the 9th.
10 to the minus 9th.
So we're getting, if we put in 1,000 watts, we're getting a milliwatt out.
A microwatt.
Micro.
Yeah,
Well,
yeah, a couple milliwatts.
Okay.
Yeah, I mean the numbers are really quite staggering. The thing is that when you're working with radio, you know, you start looking at, okay, well, here's an antenna and it's got some gain. Your antenna's pattern is spread in 3 dimensions that way, right? And it's not a very narrow beam width. So let's say that the other person is that big, 50 miles away. Where is most of your signal?
Around it.
Everywhere. It totally misses it. By the time you've dealt with, you know, you've dealt with objects in the way and a little bit of loss due to the atmosphere and especially if you're starting to deal with ionospheric skip, which we're going to get to, you know, you're down into the picowatts, which is, you know, 10 to the minus 12th, a billionth of a watt. And let's say you started transmitting at 1,000 watts and you're down to, at the receiving station, a billionth of a watt that's left. But it's still barely enough. I mean, this is the kind of stuff that is the real world. This is how the real world actually works. This is why a lot of this stuff is really just, you know, an absolute miracle, because it's dealing with power levels and stuff that we take for granted as, you know, working. But it's really, I mean, you basically have equipment that can amplify a signal 1 trillion times to be able to hear it on the other end.
while filtering out the noise.
While filtering out the noise, yeah. Okay, so that is decibels. Yes.
How did you come up with the 115 loss?
I just picked it out of the air. It's just, I mean, there are lots of other ways you could look at it too. I mean, we have signals that we have the ability to, let's say, aim at this big reflecting object in the sky, and a signal comes back down the other way. And this is, any guess what that would be? It's 240,000 miles away.
Satellite.
Satellite or moon.
The moon.
You said 240,000?
Yep.
The moon.
The path loss for this is usually about 220 decibels. Think about that number. It's 10 to the minus 21st. Yet we can still make it work. Barely, but we can make it work.
And then an example of your minus 115 dB would equate to about how far?
It depends on what's in the way.
Understood. I just meant in
hilltop.
general.
It could be a line of sight path with a hilltop where the hill is kind of in the way and distorting your signal.
Free path, everything at the same height.
Even then, I mean, it depends on your distance. Because,
yeah, that's what it was. Generically, 115 dB if it's line of sight.
Yeah.
Because your towers are really tall. About how far would you? 100 miles.
Line of sight, 100 miles.
Okay.
All right. Let's see. Next. Next. Okay. Does everyone remember what milli and micro and stuff like that are? Milli, micro, pico, nano.
Milli, micro, nano, pico.
Yeah, nano, pico.
Somewhat, if you look at it, keep looking at it.
Yeah. So there's a table in here in the book, and it is on page, oh heck. There we go. It's math. Math.
I don't want to be stupid, but did everybody download that book on your?
Yeah.
Okay. Except for me.
Okay.
I did. At least.
Yeah, and actually, it's not the best book I've ever seen, but it covers everything, and it does it very well. And it's.
What would be the best book you've ever seen?
Well, I mean, it depends. If you're just looking for a study guide, there are many different ones that work. I mean, the ARRL technician class book is more of a reference handbook.
Okay.
This is written with the intent of just, reading through and understanding everything enough. But so here we go. Okay, so everybody see that? Giga, mega, kilo.
Yeah.
Yep.
All right, milli, micro, nano, pico. All right, some things.
And why isn't the K capitalized?
It never has been. You can blame the
It's
meters.
annoying.
You can blame the meters. Well, no, because we also have little lowercase m versus big uppercase m.
And
Yeah, but those are going smaller.
Mega.
Yeah.
Milli mega.
Yeah, that's true. You can blame the meters, the MKS system for that. So I think that comes out of France. So you can blame the French. So most important thing to remember: don't mix up milli and mega. And let's brainstorm some things that we think of as giga and megas.
Giga would be your frequencies for radio, like cell phones,
Microwave. Yep.
Or your Wi-Fi in your house.
How about other things that are giga?
Hard drives,
gigabytes.
LAN networks.
Yep, gigabit Ethernet. Yeah. Okay, how about mega?
Storage.
Yeah, megahertz, frequencies, megabytes, megapixels. Kilo.
Grams.
Kilogram, yeah, kilometers.
Yeah.
Okay.
Meters.
How about milli?
Measuring volts.
Yeah, millivolts. There's also henries are also usually in millihenries. And what's a henry a unit of, everyone?
Inductance.
Inductance. Yeah,
Inductance.
Henry is inductance. How about micro?
Microcomputer.
Micro, yeah, but microhenries is another one. You can also have microfarads. That's a very common one. Microvolts, because a lot of the signals that come into an antenna will be on the order of microvolts. Nano. Don't say nanobot.
It's the wavelength for lasers.
Oh, good answer. Nanometers. Yep. And pico, the most common one is picofarads, or we call them PF. For some reason, we use microfarads and picofarads. We don't usually use nanofarads. So I don't know why, but like a little ceramic capacitor is often like 22 picofarads. And for electrolytic capacitors, we use micro. So, okay, excellent. What's equal to a kilovolt?
1,000 volts.
1,000 volts. So where would we often find a kilovolt in our equipment?
That's your, isn't that your reading for your meters coming in? No, the other way
No,
around.
no, I'm talking about specifically in our radio equipment. Where would we often find like a kilovolt?
Probably on the input.
No.
No.
Not on 12 volt.
Linear amplifier?
Your linear amplifier, yeah. Because especially if it has a tube in it, if it has tubes, those operate typically above 1,000 volts. Some operate as high as 3,000 or 4,000 volts. Okay, decibels. So, okay, so I'm going to bring this up one more time because it's like that important. Okay. How many decibels is 2 times?
3.
3.
Approximately equal to 3 dB. 1/2 is approximately equal to negative 3 dB. Whoops. 10 times? How many decibels?
10.
10 dB. 1/10 is equal to?
Negative 10 dB.
Negative 10 dB. Those are the only things you need to commit to memory. And I'm going to show you why. Here we go. Here's why. Those are the only things you need to commit to memory. Because let's say that you have a system where you have 1 watt going in and you have 838 watts going out. Okay? What's your gain? You could calculate it exactly, right? You could be 10 log base 10 of 838. You could do that, but what fun would that be? So instead of that, we're going to say, okay, well, let's start at 1 and figure out how to get up to 838. So somebody tell me a combination of 2s and 10s that would get me from 1 to 838 by multiplication. Okay, so 1.
100, wouldn't it?
What?
Would it be 100?
Well, that would be, it can only use 2s and 10s.
Oh, 2s and 10s. I'm sorry.
10 times 10 times
Okay, so that
2.
would be 1 up to 10. Where do you want to go next?
Up to 10 again.
Okay, so
or
that'd
up
be
to 100.
Okay.
And then we'll use a bunch of 2s.
Okay, 200, 400, 800. Okay, and then we're left with a little bit, right? Okay, so from 1 to 10 is how many dB?
10.
10. From 10 to 100?
Another 10.
Okay, and this is 3 dB, and this is 3 dB, and this is another 3 dB, and what do we have? Add them all together.
1, 2, 3, 4.
29 dB.
5.
Okay, 29 dB. I'll add up all the numbers. All right. So now we're going to say, okay, how close did we get? Okay, so I'm going to share. Cancel
Could you
that.
put that back up? I'm not quite done copying what you had.
I'll put it back up in a sec. Let me grab my calculator. Okay, and I'm going to share my calculator, and we're going to go to the scientific version, and we're going to say 838, and somewhere is log times 10. How many dB did we get from that? 29.2, which is pretty darn close. So
29.2 what?
It was 29.2 dB. And what did we get
dB.
from our rudimentary calculation? 29. Close enough.
Okay.
So we went from 1 watt to 838. So we went from 1 to 2, or sorry, we went from 1 to 10 to 100 to 200 to 400 to 800. This is 10 dB. This is 10 dB. This is 3 dB. 3 dB. 3 dB. Add them all together. We get 29 dB.
So where'd you go? 10, 10, and then you jumped to 3.
Well, I couldn't do another 10 because then I'd be at 1,000.
Oh, gotcha. Okay. So, okay.
That'd be too high. I mean, I could also have gone that, and then I would have gotten 30, which would have been close. I mean, the answer is 29.2. So what it really comes down to is just getting close.
Is this what you got to look? Oh, I'm sorry.
Somebody, you were all broken up. Let's try that again. Was that Luetta? Your audio's all chopped up.
Do you have to know all this for your technician class test? Because I thought it was like
you could memorize.
10 divided into 200 would give you a 10. Is that correct or no?
Wait, say it again.
What you need to know for your technician license, it wasn't that complicated. This is probably what you need to know for your general, right?
Well, I mean, or for real life.
Yeah.
You know.
That's what we're getting into.
That's what we're doing, yeah.
Okay.
But back to your calculation of the reason why you use the multiples is because that way you could just use that original. You just have to remember these 4.
Really,
equations.
it's only 2. Yeah.
Yeah.
So
right.
3 dB, -3, 10 dB, -10.
Yeah.
Really just 2 times and 10 times.
Okay.
I mean, that's really what it comes down to.
Oh, it's 10. Okay.
Because if it's getting smaller, then it's negative because the exponent's negative.
Right.
Okay, batteries, rechargeable batteries, nickel metal hydride. It's still all choppy. It sounds like your connection's a little funky. Yeah, I think that just kicked her off.
Only problem with digital.
Yep, exactly. It does.
That leads to the question of what 5 by 5 means.
5 by 5? 5 by 5 is 5/9. 5/9's a perfect signal.
5/9's the perfect signal.
We'll get there.
Okay.
Batteries that are rechargeable: nickel metal hydride, lithium ion phosphate, lead acid, nickel cadmium. Those are all rechargeable. That basically means that your chemical reaction, because a battery is just a way to store energy, is a reversible chemical reaction. Carbon zinc is a use once, throw away. Okay, diodes. Let me make sure we covered everything. Oh, here we go. Diodes. If you're using a diode, the banded end is the negative end. That's also, if you're going to draw a diode, that's also known as the cathode. Looks like this. Whoop. Oh, stop. Stupid computer. So this is the plus and this is the minus. This is the cathode. And it's got a band on it. If you actually physically look at it, it would look like this. All right, so you'd see a physical stripe on it. The voltage drop, every diode is a little bit different. Again, silicon, it's a semiconductor. Germanium is also a semiconductor. A silicon diode is 7/10 of a volt. The germanium is 3/10 of a volt. Okay, where are we now? Transistors, field effect, we did that. Schematics, electrical components, just making sure we covered everything. Batteries, switches. Okay, we didn't cover switches yet. A switch is known as a pole, is known by the number of poles and throws. Okay, so if I have a switch that looks like this, that would be a single pole because it connects one thing, single throw because it only goes one way. If I have something that looks like this, and these are tied together, then that connects to here and that connects to here. That is still a single throw because it only runs one direction, but it's a double pole. So that would be a double pole, single throw switch. I could also rebuild this so that it looked like this. Shall I do that?
The full double throw.
There we go. Let's fix that. There we go. There we go. Okay, so that's a single pole, double throw, because it's one circuit. That's a number of poles and a double throw. It could either be there or it could be there. If I tied two of these together, these would be ganged together. That would be a double pole, double throw switch, or a DP-DT. Okay, another use of a diode is as a rectifier. We use a rectifier. It means to fix something. It converts DC to AC. That's known as a rectifier. Let's see, resonant circuits. We did that. Other components, switches. A relay. Okay, should cover what a relay is. A relay is a combination of a switch,
coil,
and a coil, magnetic coil. What happens is that the magnetic coil will create a magnetic field when current is run through it, and it pulls this piece of metal down to close the switch. So it's a magnetically operated switch. It uses an inductor and a little piece of contact material that responds to the magnetic circuit. One other thing that we started to talk about there was if we have two pieces of wire and one of them is carrying a current, it will generate a magnetic field like this. And what will happen is if the magnetic field extends beyond the reach of another piece of wire, you will start to develop a current in the other one. This is known as crosstalk. If you're using audio cables, crosstalk is very bad because then one signal will appear in another wire. Your microphones, for instance, will start to interfere with each other. So what we do here is we take each cable and we do this, get rid of all of that, and now we have just the magnetic field that's inside here, and we put a shield around it that looks like this, and we ground the shield. That puts the whole shield at 0 volts, and it also means that it contains the magnetic field on the inside. This is the definition of a Faraday cage. It contains all the fields that are generated on the inside, and if they're on the inside, they can't affect the other wire. Similarly, what we would do, we would probably also shield the other wire, and that completely isolates them from each other. Okay, next.
Hey, Scott.
Yes.
Can you remind me, what was the magnetically operated switch called?
It's a relay.
Relay.
Mm-hmm.
Oh, easy.
And Scott, can you go back to page 28 of the booklet?
Page 28. Page 28. Let me...
Circuit diagrams.
Yeah, circuit diagrams. Okay, page 28. 28. Okay, here we go. Yep.
So that picture.
Yep.
So what is the direction of current flow in this picture?
Okay. So
is it going from 4 to 2 or 2 to 4? Because it's using
4 to 2. Well, so I'm going to redraw this and I will show you. All right. So basically what we have is a circuit that is grounded like this. This goes through a resistor and then the base of a transistor and then through a light. That's what this is up here. And then, okay, it looks like this, and then this goes to ground also. All right, so we have this transistor. This is the base, the collector, and the emitter. This is actually an NPN transistor. And the way you remember that, you notice the arrow pointing outward down here on the emitter. It's not pointing in. NPN. So when this was built, this transistor is an NPN transistor. It's a sandwich of 3 layers. That it's an N, a P, and an N. So it's a P gate. So it goes N, P, N. Okay. So we really have, in this case, a dividing line in the circuit right here, where the base to emitter current is the activator for the switch. So when a signal turns on right here, it activates and puts current between the base and the emitter. And what that does is that it opens this channel between the collector and the emitter. So this channel becomes wide open. So the way that this is drawn, it has a positive and negative terminal. So current would flow this way. It would flow through the light and then through the transistor to ground, thus turning the light bulb on.
Oh, okay.
There, we'll make
So
it.
what they're missing there is that where your check mark is, typically that would be another battery or something.
Or it could just be it could be any number of different things. This could be a waveform that looked like this.
Yeah.
That would be like a pulse width modulated lamp.
Yeah.
If your lamp was capable of doing it.
Mm-hmm.
So it'll roll from the lamp over to the cathode side and then down through the diode. It won't be able to come back. It'll hit ground at the bottom there.
Yeah.
So so the key is the NPN is not pointing in.
Correct.
Okay.
And if it's a PNP, then all the directions of current flow are reversed.
And that arrow would be turned the other way.
Right. The end result is the same, but you have to wire it differently. NPN transistors are easier to build, which is why most of them are that. But not all. There are a lot of PNP transistors out there. And while we're at it, the gain of a transistor is represented by that letter, which is the Greek letter beta. That's the ultimate output to input gain. Usually when you build a transistor amplifier, you would do this. And that would allow some of the feedback back into the input side and reduce it so that it's not as affected by that the gain is less affected by the beta of the transistor.
Mm.
So
it'd be less sensitive?
It'd be less sensitive to actual hardware changes. Like, because then you could take any, like my dad always told me when he was working, building electronics, that one of his coworkers said, I need an NPN transistor. He said, well, what do you need? It's like, I don't care. Any NPN transistor. They had to replace something in a circuit. He said, give me anything. Because it was built in a way that pretty much any NPN transistor, independent of how it was built, independent of its gain, would do the job. So if you've designed your circuit correctly, the actual gain of the transistor doesn't really matter that much.
Okay.
And even within a batch, you can have significant differences from one to another. So you want to eliminate that.
Is the gain calculation required for any of the in a circuit, doing the resistors or whatever? Is that required for any of the tests?
No.
Like not even the extra?
I don't think so. There's on the extra exam, I think there's an op amp.
Okay.
That's a transistor amplifier that simulates a perfect amplifier with no input impedance and infinite input impedance and zero output impedance. It's an optimized. It's called an op amp for that reason. Essentially, it's an amplifier that comes very close to being the perfect amplifier, and part of that is that you do have feedback, and you have to know that the feedback has because the amplifier has infinite gain as designed, that the feedback element actually gives you controllable amplification. But that's only on the extra exam, if I remember right.
Thank you.
I actually found the extra exam to be easier.
Really?
Yeah, because it's all
In the general?
yeah, because it's all there's very little. You've already done all the memorization stuff. At that point,
Yeah.
it's just math.
It's application.
It's application and mathematics. So yeah.
And did you take that before or after your double E?
Before.
Oh, okay.
In that case, it was a lot of memorization. But then just a few years ago, actually about a year and a half ago, just to be current, and just to be able to talk about it, I was in Canada and I took my Canadian exams.
Oh, that's cool.
So,
Is there much difference?
No, they're longer.
Are they?
And their version of the extra exam is the advanced exam, and it's 50 questions. And again, it's very technical. So, and I honestly found that to be easier, because I could always, it wasn't necessarily memorization. If I didn't remember the answer, I could just go calculate it.
Yeah. Once you have the theories and everything, right, you can start.
Exactly. But yes, when I was a kid taking my exams, I did have to do just a lot of memorization. I mean, I got my extra when I was 17, so I was a freshman in college. We hadn't done anything yet. One exam per month for 4 months.
Back in
Okay.
the old days when you actually had to know Morse code.
Oh yeah, well I passed my 20 words a minute back then. So okay, so we are into either, okay, what do you guys want to do first? Antennas or radio or propagation? I guess antennas would be more appropriate. Okay.
Please.
So, antennas, okay. So, what we're going to do is, now that we've established that what creates a magnetic field?
Electricity.
Well, what in particular?
Current
Flow
flow.
of current. That's right. Current makes a magnetic field. And having a voltage at a given point generates an electric field. So, if you have a current, then you have a magnetic field, which is a B field, and you have an electric field generated by voltages in space. As these change, you end up with radio waves that work outward as electromagnetic waves, and also are going like this. It's really kind of amazing to see. They propagate in the outward direction. If something happens to be on the other end, a piece of wire that encounters these fields will have voltage and current induced in them. What happens at that point is that those are then fed down through a feed line to a receiver.
And amplified, right? That's why we got such a low on one side, right?
Yep. So here's your transmitter. Your transmitter connects to a feed line. The feed line works up to an antenna. There are electrons that are moving in the antenna. They generate these fields, which then travel through space and encounter, again, this other wire. And in that other wire, you create voltage and current, which then travel up and down the wire and down into the receiver. Again, magic, right? It kind of is. I mean, that's the thing about this. This is almost magic. So again, here's our transmitter, feed line. Here's our antenna. Signal travels through space. We have an E field and a B field. And then we have another wire over here, which is affected by the fields which are traveling through space. Now, the tricky thing is also, these are not, your antenna is not only affected by this particular signal. How about if there's another signal over here? And I'll draw it in a different color.
And natural, right? There's natural things happening.
And there's natural things happening. So, what is your antenna picking up?
Well, it's picking up all those signals.
Yeah, okay, so let's have another signal. that's being transmitted on a totally different frequency. What's your antenna picking up?
All of those.
Okay, so you have on that antenna at one time all of those different signals, which contain a bazillion different frequencies, all at once. How do you pick the one you're looking for?
Filter it out.
You filter it out. You basically have series of inductors and capacitors, and then you take signals and mix them together to generate new frequencies, and you filter again, and you mix frequencies to make another set of frequencies, and you filter again. And the end result is that you are able to pick the one frequency that you are specifically looking for out of all the stuff that's coming in off your antenna. Because your antenna doesn't know what's hitting it. It's a dumb piece of wire. So what we can do with our antenna is we can tilt the odds in our favor a little bit. And the way we do that is, let's say that we specifically want to selectively choose, let's say, 10 megahertz. Let's say that is of particular interest to us. Well, okay, so do you guys remember that 300F lambda thing? Okay. What do we need to know? We have our frequency. We have the number 300. Well, that number, it requires the use of megahertz because it's actually 300 million. So by using the mega there, that means that we can use the number 300 here and not 300 million.
Right. Because
the speed of light is 300 million meters per second. So this means that we have to use the megahertz value. Okay, so let's use the megahertz value, and our frequency is 10 megahertz. Let's plug it in. We don't know our wavelength.
30.
Yep. So our wavelength is 300 divided by 10 is 30 meters. Okay, so now we have to get to a couple of really interesting thought experiments. The first one is right here at the end. What is the current by Kirchhoff's current law? What is the current at the end of the wire?
It's the additive of everything. No, it'd be the other way around. It'd be the...
Here's a close-up of the end of the wire. What does the current law say? The current has to be at any point.
Equal.
The current in has to be equal to the current going out. If that's true, what is the current right at the end?
Whatever's going in.
Has to be the same as
the input.
But where does it go?
Oh, yeah. Goes out into the...
It doesn't go out into space. It's constrained in the wire. So what is the current at the very end? Have to be.
Has to be zero.
Has to be zero. So we have no current right here. How about at the other end?
Also zero.
Okay. So what we've done is we've now developed a set of constraints that say that our current at the end of the wire, unless we're leaking to somewhere, which we're not, hopefully, has to be zero. Okay. So now what we're going to do is we're going to draw a wave. So what does our wave, this is the current version of our wave. let's say that our wavelength is this long. That's a wave. Right there. What's the starting point at the end have to be?
0.
Has to be 0. So we're drawing our current. We're using that wave, and we're going like this. And why is it that we had to start at 0? Because we had to, because physics says so. All right, so on the other end, we do the opposite, because we can't go any further. And we're pretty close. I think I drew one too many waves. I did draw one too many waves. There we go. Okay, so now this antenna satisfies physics. We drew our current distribution on that particular antenna, on a piece of wire. The feed line has current going up and current going down, and they cancel each other, so we don't care about that. What we care about is now how this antenna looks. And if we were to look at the current high points and low points, we would also be able to look at it and say, what are our voltage high and low points? Typically, current minima equate to voltage maxima. So there's our current, and now we're going to draw our voltage.
Are you drawing something?
Yeah, I'm about to.
Okay.
Here we go. Not perfect, but so, and then we have to do the same thing from the other end.
So this would be current, or we could flip it around and say one's current, one's
And that would be voltage.
Okay.
All right. So what has to be true, the only thing that has to be true is that by Kirchhoff's current law, the current at the end has to be 0. So, would this antenna work? Sure. I mean, you'd have current at different points, and it would be going up and down, and your voltages would be going up and down. And now what you have to do is you have to match this to your feed line, because you have to be able to deliver power into it, because you have current going up and current going down. So you have to be able to translate those into something in the antenna. Well, as it turns out, now you have to look at something called a feed point impedance. There's that word impedance again, which is resistance to flow of AC current. Your feed point impedance, Ohm's law again, E is equal to IR. But in this particular case, impedance is the letter Z. It's actually complex. So our new equation is E equals I times Z. But you can think of it as similar to resistance. It works out the same way. And in fact, E equals I times Z, and we can figure out that Z is equal to E divided by I. Okay, this is our E, and this is our I. This antenna is known as a half-wave dipole. Well, in this particular case, though, it's not a half-wave. How many waves do you see on it? There's actually quite a few, right?
Yeah.
Okay.
6-ish.
So this is just a dipole. It's a long dipole. And it turns out that because it's a long dipole, it could work. It might give us some kind of weird results. And we also find that E divided by I in this case is actually quite high because of the voltage and the current right here. Most coaxial cable that we're working with has an impedance of 50 ohms. This might have an impedance right here of 300 ohms. That would give us something called a mismatch. It would give us a standing wave ratio mismatch. And we would have trouble delivering power into that antenna at that particular frequency. Now, could we take this antenna and change the frequency at which it was operating? Sure. Could we take this antenna and change its length? What do you think?
Yeah.
Sure.
Yeah.
Right? You just have to trim the ends off. Now, if you change for one, what happens to the other one?
It's not.
It might be different, and then you have to redraw it. So ideally, what we have is an antenna that is the easiest, most perfect antenna to build. And what we do is we set our constraints so that here are our ends. And what does the current have to be at the end points? Everyone?
Zero.
Zero current at the end, which means that the simplest way to draw this, it's just like a piece of rope. How many waves is that?
Half.
That's a half wave. This would be a half wave. And it's a dipole. It has two legs, so it's got di, and each one is called a pole. So this is called a half wave dipole. So that's our current. And this is our approximate voltage. Oops, like that. And it's not zero at the center, but it's at its minimum. And what is our Ohm's law again? Everyone? E equals
IR.
IR, but in this case we're replacing R with Z for impedance. So E is equal to IZ. Z is equal to E divided by I, which is equal to, we're just going to call this qualitatively low, and we'll call this qualitatively high. So low divided by high. What's low divided by high?
Negative number.
No. What's a small number divided by a big number?
0.
Well, it's not quite zero.
Approaching 0.
Yeah, we'll just say it's a low impedance. And as it turns out, for a half-wave dipole, this is about 72 ohms. Coaxial cable is roughly 50 ohms. That's not a bad match. That actually works out really well. And this antenna, we're going to go back to the fact that we were making it for 10 megahertz. All right, so we're going to figure out how long it needed to be. Here we go. So it's at 10 megahertz. What's the formula for that again?
For megahertz?
No, what's the formula for wavelength and frequency again? What's that circle?
300 divided by the frequency. Isn't it?
300 F lambda. Okay. Our frequency is 10 megahertz because that was where we started. We want to figure out our wavelength. Wavelength is 300 divided by 10 is 30 meters. Okay. How many wavelengths is this antenna?
One full wavelength.
No, that's not a wavelength.
Oh.
What? Half wave.
15.
Okay, so how long would a half wave be?
15.
Half of that
15 meters. Okay, now, because we are existing in the real world, we actually need to shorten this by 5%.
Is that for loss?
It's because of self-inductance and coupling and all other kinds of effects. So we actually shorten it by 5%. This is an important thing to remember when you're building something. So let's see, 120 at 10% would be, okay, so this is 14.25 meters. Okay, so how long would each leg be?
Half of that.
Half of that. So like 7.12 meters. That's it. That antenna is a perfectly matched antenna to operate at 10 megahertz. And it would probably be very, very close on the first pass. So, would you cut it?
Start a little long and then trim back if you have
I
to.
was just going to ask that. Would you cut it too long or too short?
Yes. Too long.
Too long.
Because you can always cut it shorter. It's very hard to find a wire structure that works these days. So, it's a lot easier to trim something that's too long. So,
where did you get 72?
7.12? Well, each one of these legs of the antenna is half of the whole thing.
Oh, no, I'm sorry. The 72
ohms
of loss.
Oh, this is actually just an
Sorry.
This I'm not going to go into.
You just know it.
This is just that's the center. That's the feed point impedance of a resonant half-wave dipole. And we could go through and calculate it, but it would take the rest of today and tomorrow.
Okay, so it's fixed for a half wave.
Yeah.
Roughly.
Right.
Okay.
Now, here's the other thing. If we were to take the same antenna and instead of using it at 10 megahertz, we were to use it at 20 megahertz, for instance, we would see this. It would still meet, the requirements. It would have zero current at the ends. But what do you see happens at the feed point? What does our green current line do?
It raises.
What's our current at the middle?
Oh.
Looks to be zero.
It's very close to zero. It's very low. So current is low. And typically that relates to, if we were to look at the voltage, that
The
would
highest
relate
potential
to
of the voltage.
the high voltage. Yeah, so we'd go like this. So we have a high voltage and a low current. Well, let's do Ohm's law again. And what do we get?
A low impedance.
No, you get a very high impedance.
Oh, this one's high?
Right, because what does Ohm's law say? This is why it always helps to go back to Ohm's law. What does Ohm's law say?
E equals IR.
Yep. Or in this case, E equals IZ.
And Z equals E over I.
Yep. Always helps to go back to that. I still go through and do it. E equals I times Z. Z equals E divided by I, which is qualitatively voltage is very high and current is very low, and something that's big divided by something that's small
is high.
Is high. And in this case, it's about 2,500 ohms. If you have a 50 ohm coaxial cable, good luck getting a match there. You have,
why is voltage high in the middle?
Because the current is low. Current zeros translate to very high voltage points.
It's 1730.
Because of the sine wave you showed us earlier, right?
Yep.
Where they crossed.
Yep. So that being said, if you have a match of 2,500 ohms for the antenna and 50 ohms for the cable, that's like basically tying a jump rope to a door, like a doorknob, and slamming the door shut and then whipping the rope. What happens when the wave gets to the doorknob?
It's really fast.
Well, and most of it bounces back to you.
Yeah.
Some of it shakes the door, but not very much.
And
that's what you're effectively having happen here. Okay.
What do they call that when that happens?
That's just a big impedance mismatch.
Where'd you get the 2,500 ohms?
That's the approximate feed point of a center fed full wave dipole.
And how'd you know that?
Because it just is.
Okay. All right.
Whenever you get to a voltage maximum at a current minimum, you'll typically get about between 2,000 and 2,500 ohms.
Okay.
So now
go
ahead.
Are those numbers that you would commit to memory, right? As you're going through stuff.
Okay, so we have a couple of choices here. Let's say we really, really, really wanted to use this antenna. What are a couple of things we could do?
Well, we'd have to change the length of the wires.
Nope, you can't change the wire length.
Okay.
Antenna tuner.
You could use that wouldn't really help though, because the problem is you could put an antenna tuner up here and it would do an impedance match. But then again, that has to be something that's designed to be outside in the rain.
Can you
Would
put
it
a
have something?
something
Would
on
it
it?
have something to do with your current that you would change?
Yeah, but it wouldn't really help.
It wouldn't help. Okay.
No.
You can change the position of the mouthpiece of your oboe.
Yes, you can.
Oh yeah,
Okay.
you can do that.
You can. You can change your feed point position. You won't be perfectly balanced anymore, but you could move the feed point over here, and that would be an off-center fed antenna. And then you would be feeding it at a much better spot. Okay, good choice. What's another thing we can do? And I'll give you a hint. I'm going to draw you a hint.
I could have swore you can still virtually change the wire length with your tank circuit.
Yeah.
No.
Well, I'll give you a hint.
Yeah, I was going to say a coil, right? You can put a
Not a coil.
well, transformer. Transformer.
A transformer not only changes voltages, but it can also change impedances. So if I have an N to 1 transformer, this changes my impedance by N squared to 1. Where N is the number of turns. So if I have a ratio of, let's say, 7 to 1, that would be a 49 to 1 transformer for impedance. What's my ratio of 2500 to 50? It's about 50, right?
Yeah.
Well, that's a 49 to 1. I could actually do it that way. And in fact, there are antennas where you intentionally feed it at the end, and this is what you use to feed power into it. It's called an end-fed half wave.
Scott, that's funny you say that because I just went with a guy today. He's showing me how to do ham. He used a long wire like that and had a transformer on the end of it.
That's exactly right. That's why.
That's why.
Yep, because you need to be able to feed it at a really high impedance. So you use a transformer to match that impedance. And now you can tell them why.
Yeah. Now we were talking to people in Alabama. I'm up here in Washington State, and it was cool at 14 meters or 14 megahertz.
Yep.
Wow.
Okay.
The red thing, impedance matching transformer is the name.
Yep.
Okay.
Okay. Next, we're going to get into other forms of antennas and other things that they do. So let's say that I have an antenna that looks like this. Here's the roof of my car.
Oh, that's your car?
Yeah, that's a terrible car. I need to get a new car. Here's the roof of my car. And here's an antenna that's fed like that.
I'm making a car.
Yeah.
Meter with a heater.
Okay, here we go. So here's an antenna. This is a quarter wavelength long. My feed line comes in right here. One leg goes this way. One leg goes to a plate that's sitting above the roof of the car. Okay, so this antenna is actually electrically almost identical to an antenna that would look like this. So if that were a quarter wavelength above, how long would this one be down below? A quarter wavelength.
Quarter.
Okay, so what does 2 quarter wavelengths look like? What has another name? Right, this is a half wave dipole.
Half wave. Oh, okay.
Right, except that in this particular case, we've done some trickery to make it look like this isn't even here, to make it look like it's here without putting it here. The easiest way to think about this is if you were to, let's say, look in a mirror and hold something up against the mirror. If you didn't know that whatever you were holding up in the mirror, if you didn't know there was a mirror there, you wouldn't know the difference. So from the distance, if I were looking at this antenna, for instance, and I were looking from here, I would see if this was a reflective surface, I would see this reflected. And I would see a perfect above image and below image. As far as I were concerned, I would basically see two halves of the same antenna, but they're really the same thing. That's if this was a perfect reflective surface. That is what a ground plane does. So this part of the antenna isn't there. What I see is an imaginary part of the antenna down below, which makes me think that I'm seeing a half-wave antenna. And if I'm seeing it, well, there must be something to it. The way I feed this antenna close in is like this. So here's my roof. And I have my cable that comes into this antenna. And it's actually like that. It has a center conductor. The center conductor goes up to here, up into the sky. The other part of it goes down to a plate, which is sitting above and separated from the roof of the car. I'm going to change the color. It's usually separated by a little piece of plastic.
It's outside of the car, above the car?
Above the car, because there's a magnet that's holding it all down.
So it's in the base, built into the base? Would it be built into the base then of the
magnet?
antenna?
The magnet is built into the base, but there is a gap in between.
Okay.
Okay. How in the world does this work? Based on what we've already talked about today, you have to visualize this.
That's your ground though, right? On the bottom?
That's the roof
That's
of
your
the car.
car.
Yeah.
Yeah.
How is it working? How does this electrically connect this part with this part?
Magnetics?
Close.
Electro?
Come on, look at that. What do you see? You see two metal plates that are parallel.
Capacitance.
Capacitance.
So this is capacitively coupled to the roof of the car. And because we're typically operating at, let's say, 150 megahertz, you know what, I won't use 150. I'll use the actual frequencies. Let's say 144 megahertz, which is 2 meters, or 440 megahertz, which is 70 centimeters. At those frequencies, that gap acts like a short circuit. If it's a short circuit, what does that mean? Electrically speaking, it is connected. It is capacitively coupled between the antenna, mag mount, and the roof of the car. And they are indistinguishable from each other at that point. So then, the roof of the car now becomes the ground plane, capacitively coupled, and acts like it's like physically electrically connected.
So that acts as the
What
other
is
half.
what creates the space? I guess I don't understand. The
It's
bottom where the red is and the blue is the top of the car.
It's physically the way it's built. Like that space is usually just like a thin piece of plastic to keep the antenna from destroying the roof of your car.
So it's all one piece. It's built together.
Yeah. So typically what you'll find is if I do a little bit better job of drawing this, and I know because I tore one apart last year just to see.
Oh, you did?
Yeah, I did. It was an old Larson antenna. So basically the mag mount looks like this. There's a big magnet right here. And then below that, separated from the magnet, is an electrical plate. Just a conductive metal plate. And then like there's an insulating layer here and then an insulating layer here. And then this plate and this connect to the cable.
But if you'd go and scrape your paint and everything else and you'd actually connect it to the metal, it would work exactly the same.
It would work a little bit better, probably.
Okay.
And I have done that before, although it's very nerve-wracking.
Can you run the flat copper wire and run it down to like your frame of your car?
Sure.
And cause the same thing? Okay.
Yeah, sure.
So you've got a wire that's between in plastic pieces.
Well, it's actually a metal plate. I mean, it's a copper plate. It's not just a wire.
Okay, so there's a copper plate between those two red pieces, and the red represents plastic.
Yeah. They basically just sandwich it and insulate it, and then keep it waterproof, and keep it from destroying the paint on your car.
That's why you don't want grounded dirt on underneath it.
Oh yeah, I've done that before. Yeah, sometimes I'll put another piece of like vinyl on top of it, so that because sometimes even if you get road dust, it'll just grind it in with the vibration.
Mm-hmm.
So.
Hey, Scott.
Okay, so the wires come out, and then is this going to your radio, or is this going to the antenna?
Goes to your
radio. This part goes to the radio. Okay.
The antenna's up here.
Okay.
Scott, are you going to talk about the ground planes that are the horizontal wires that come out of the base of an antenna?
Yeah.
Is that the same concept? Okay.
Yeah. Okay.
Can I ask another question? What's the difference between a quarter wave and what's the other one, a 5/8 wave?
There's a quarter wave and a 5/8. Okay. So how long is a quarter wave?
Quarter of a wave.
Quarter wave. Minus a little bit, right? How about a 5/8?
5/8 of a wave.
Okay. So it's time to talk about array factors. All right. We started to talk about this before. Okay. So let's say that I have, what time is it? 2:45. We'll take a break in a couple minutes. Let's say we have a radiator here and a radiator here, and they're spaced a half wavelength apart. So if these are putting out the exact same signal at the exact same time, let's say they're fed by a single cable, right? Each of these puts out waves that are in phase with each other, right? So let's say at this point in the distance, these will arrive at the same time. How about over here?
Nope. Take longer.
1, 2, 3, 4, 5. And then this one will take more. It'll take longer to get there. And depending on how these are phased, these will actually, if they're a half wave apart, you'll have this, and then you'll have this.
Right, what the fuck?
Someone needs to go on mute.
So these will then cancel each other out. So this would then be a broadside array. It's broadside to the line. If I have a whole bunch of these doing the same thing, if I have a whole bunch of them doing the same thing, I'm going to get an enhanced signal perpendicular to the line like this, and I'm going to get very little signal off the ends. So that would be sort of like building an array.
You lost me on that. Can you do that again?
Yeah.
So what did you get rid of?
So we have two things that are fed, let's say, a half wave apart. Well, if I do this like this, here's my waves. Because these are fed together, they're fed exactly at the same time by the same signal. These two signals are going to arrive at this point perfectly perpendicular to the line connecting the two at the exact same time. So they're going to add. But if they have to go this way, they're fed at the same time. By the time this one gets there, it will be out of phase.
So that part I get.
And that cancels out. So here's the line connecting the two. This would be known as end fire if it was enhanced in that direction, and in this direction would be broadside. Because it's broadside to, like, I could put more elements on here. I could put 5 or 6. Essentially, it would enhance the perpendicular signal, perpendicular to the line that makes up the antenna.
Okay.
So a 5/8 wave antenna is you could actually draw it like this, and the current would look like this. Let me think, 5/8. So that would be 5/8 wave. So you're feeding it at a decent point, and then you have a lot of current up here. You get to maximum. Whereas with a quarter wave, you'd basically be looking at something that's this long, and you only have this much energy, this much that's transmitting perpendicular. The bigger the current you have, the bigger the signal will be. So a 5/8 wave antenna will give you a better signal in the perpendicular direction. And since we're now talking about something on the roof of your car, that's exactly what you want. Because most people that you're talking to are somewhere on the ground or just above the horizon, like a repeater station. Last thing we do before we take a break is we're going to draw this dipole antenna. The direction of movement of the electrons is the same as the electric field. That determines the polarization of the antenna. If you're familiar with polarizing sunglasses, it's the same thing. It's the direction of movement of the electric field. So a horizontal wire will have a horizontal polarization. This wire, which is a half wavelength long, will also have a radiation pattern that looks like this. And like this, and like that, if I were to draw in 3 dimensions. Essentially, it makes a donut shape around the wire. It makes a donut-shaped radiation pattern.
What does a vertical look like?
A vertical would just be turning it sideways. So a vertical would look like this. Let's say it's a half wave vertical. I managed to feed it as a half wave. The radiation pattern would look like this.
Okay.
The advantages to that, this would be a vertically polarized antenna because the wire goes up and down, so your electric field goes up and down, and it's vertically polarized. The nice thing about that is that if you have another vertically polarized signal, your electric field is going to be going up and down. Crossing polarization will cause you something like 25 dB of loss.
Oh.
So if you have a line of sight antenna, crossing vertical and horizontal polarization will cause you a lot of loss, like a huge amount of signal loss. Okay. So that's why it's important to match the polarization of the other station that you're talking to. So
you said, going back to that 5/8 versus a quarter wave, and I apologize for laughing earlier. You said if you were trying to talk to somebody earlier, a 5/8 is better because it's shooting the signal out higher. Is that correct?
No, it generates higher current.
Okay, it generates higher current.
It has more higher current areas, and it generates a stronger radiation lobe along the horizon.
Okay, and then so it's a higher current. And then the second thing was one more time, Scott. I'm sorry.
It just basically has gain along the horizon. It has a lower angle of radiation, which, because everyone you're trying to talk to, if it's on the roof of your car, for instance, is along the horizon, including repeaters.
Yeah.
So if it has 3 dB of gain over a quarter wave antenna, everybody, what's 3 dB of gain? How many times? Twice. So if you're running 25 watts with a quarter wave antenna, now if you're running 50 watts with a quarter wave antenna, how much power would you have to be running with a 5/8 wave?
Oh, be the other way around. It'd be
25. You only need half as much power to do the same job.
Okay, can you say that again?
If you're running 50 watts with a quarter wave antenna, if you changed it to a 5/8 wave antenna with 3 dB of gain, you would only need to be running 25 watts. to get the same amount of power along the horizon.
Scott,
Yep.
I get the distinct impression that I'm like don't understand something or miss something. So I have my radio, a ham base station, okay?
Okay. Yep.
And I'm going to attach my cable to the back of my radio.
Yep.
My antenna.
Mm-hmm.
I don't know who I'm going to talk to because I'm hoping to reach out and see how far I can reach out, but I need an original antenna to start with, something to start with.
Yep.
How would I construct my antenna? How would I figure out what I needed, how long things were to make this first antenna?
Okay. So what band are you looking at, first of all? Let's look at 2 meters. Right? That's 146 megahertz. So we're going to start on 146 megs. Okay. What's the first thing we do? Luetta, you're going to take me through this.
I don't know how. That's why
Sure
I'm
you do.
asking.
Here we go. 300. We go back to this. F.
Mm-hmm.
We're going to go all the way back to the beginning. Remember this circle?
Yes.
Okay. What's our frequency?
146 megahertz.
Yep. So what don't we know?
So what I don't know is my wavelength.
Correct. Okay. So we got to calculate the wavelength. Okay. So we're going to cross that out. So our wavelength is equal to 300 divided by 146. What do we get?
Hold on, I'm writing this down. Okay, 2.05
meters.
Meters.
Okay.
Yep.
And what do you want to build? A quarter wave?
Well, you said a 5/8.
Yeah, a 5/8. Okay, let's do a 5/8. How okay, so how long would 5/8 be? Times that.
Times that or divided by that?
This is one wave. We need 5/8 of that.
Okay.
So
give me a second. Okay, so that's going to be 2.05 times 5/8.
Yep. Okay, what do we get?
How do you multiply the 5/8, Scott? I'm sorry.
Go 5 divided by 8 and take it to decimal.
0.625. All right, what do we get?
I think she's cutting out.
Okay, we got it. 1.28 meters. Okay. And now we need to cut it down by 5%.
Times 0.95.
Yep.
Should be what, 111 something?
1.22 meters.
Okay.
All right, so that's a good starting point. And I'm not 100% sure what the feed point impedance is going to be. My guess is that it's probably going to be doable without much impedance matching, so that'll be good. So there you go. This is where the theory meets the real world.
Question for you.
Yeah.
And I apologize for interrupting again. You said you take 0.05 times 2.05. Is that correct?
No.
0.62.
0.625. It's 5/8. So 0.625.
And you got that by the
it's
65 by
0.625.
Yeah, you take 5 divided by 8.
5/8 is 0.625.
Oh, okay.
You can just take it on a calculator
Oh,
and go
gotcha.
5 divided by
Okay.
8.
Gotcha. Okay. Thank you.
So that's how we do
And
that.
the 1.22 meters is how long the antenna has to be?
Yep.
And
What
is it vertical? So
Doesn't matter.
with a 5/8, okay.
Typically,
It doesn't matter whether it's vertical or
no,
horizontal?
I mean, that's physics. It doesn't really matter. Now, I will say that this antenna will probably work better over a ground plane. So
Why do you say that?
just because of how it's designed to work.
Okay.
I mean,
So it's just a feel.
yeah, I mean, you typically wouldn't use a 5/8 wave. I mean, it's going to need a counterpoise because this is designed to be a single element. It needs something else.
Need the ground plane.
But you could do a 5/8 and a 5/8 and feed it like that, or you could turn it on its side, and that would be 5/8, and that would be 5/8.
Mm-hmm.
I mean, those are both fine. I mean, they would work.
But you need to know what's receiving on the other end at that point, right?
That's right.
Okay. Because you want to make sure that you're oriented the same.
You want the same polarization.
Yeah.
Which is why for weak signal work, for instance, an antenna would be horizontally polarized.
Yeah.
And rotatable.
Yeah.
So this is a Yagi, which is a multi-element antenna, and it's going to have a half-wave dipole as the driven element, so your cable's going to feed into that, and everything else is going to be parasitic. So you're going to have a little bit longer, and all of these are going to be shorter, and that's going to have gain in the forward direction.
So Yagi's directional, but
Yeah.
if I'm trying to talk to someone halfway around the world bouncing off the ionosphere, that's probably not.
Oh no, Yagis still help.
Still
For
helps.
Sure. Oh yeah, a lot. Because there's only really usually one path that works. So if you can direct, so here's a typical radiation pattern for a dipole. So in that forward direction, you have that much extra gain in the forward direction. Maybe this is 10 dB. Okay, so let's say it's 10 dB. So normally I'd be right here. And let's say I were running 100 watts. What would my effective amount if I went to a Yagi, what would my effective amount of power be if I had a forward gain of 10 dB?
1,000
watts. Yep. I don't know why it keeps doing that. So that is the improvement, essentially taking all this power, which is going out in directions where it's doing no good, and pushing it off in the forward direction where it can do some good.
That's right.
That's the benefit of an antenna with gain. The same thing, like here I'm going to draw a microwave dish, right? We can repurpose microwave dishes for all kinds of purposes, right? So
you're still pointing it in a direction, but by the time it gets there, it's really covering enough area that,
Well, ideally, it's not even covering area. It's covering a very, very small area. Essentially, what we've done is this is a dipole right there, which would normally have a radiation pattern like that. But now we've taken everything going backward and redirected it in the forward direction. And even stuff, in some cases, going toward the sides because it's parabolic, redirected everything. So you could build a dish that has 30 dB of gain. If you have a 1 watt transmitter, how much do you get with 30 dB? What's the equivalent? Every 10 dB is 10 times.
10,000, yeah, 1,000.
You get a kilowatt. It's the equivalent of a kilowatt in the forward direction using a 1 watt transmitter. Because you've essentially taken everything else that's going off in all the other directions where it doesn't help you and directed it in directions that do. This is why we do this.
Scott, I've got one question for you around antennas. I've got
Only one?
Well, I got more, but I'm just gonna boil it down to one for now. But I've got a little 3-inch, really fat antenna. It's a NMO,
Okay.
It's on my truck. Why does that still work well?
All right.
Because it's not that long.
No, it's not. They suck. Frankly, they suck. Okay,
Okay.
but here's the math. All right, so let's say you've got an antenna. Okay, so how long is a quarter wave at 2 meters?
Be
19 inches.
Nine.
19 inches. Okay, does it matter if it's 19 inches stretched out or 19 inches coiled up like that?
Okay.
And the answer is no. What happens though is that your peak current is at the base where you're feeding it. And if I do it like this, coil and then that works. Straight wire works. All coiled up also kind of works, but this might have a gain of 0 dB. This might have negative 2 dB. This could be negative 8, and this could be negative 15. That's not really good, is it? That's negative gain.
Yeah.
That's loss, right? Okay, but let's say, this is where it helps to understand what's going on. Let's say that your repeater is over here on top of a building, right? Here's your repeater station on top of a building. And your path loss between you and here is, let's say, 50 dB. And the repeater sensitivity is minus 110 dB M. And you're transmitting at 50 watts, or let's say 20 watts, because that antenna can't handle that much power. So maybe because of what you're doing, you can absorb that loss of 15 dB just fine. In which case it becomes, it becomes situational.
Okay.
Because of how you're using it, it might be perfectly fine. Like I take my handheld I take the rubber duck antenna. Yeah. By the way, for anyone who doesn't know.
That's on the test too.
Yep. This is a rubber duck antenna. This antenna right here, this is called a rubber duck because it's bendy and it also has a fair amount of loss. If you want an antenna that works better, you stretch out the 19 inches of wire into a real long antenna, but as soon as you put it on your belt, it jabs you in the armpit. So not really very practical. But this, what he was saying is if I take this antenna, which is about 8 inches long, and I coil the whole thing up into an antenna that was only 3 inches long, I'd have all those electric and all those magnetic fields that were canceling each other out for the most part. That would be a terribly inefficient antenna. But if I was right under the repeater, there's still enough signal that it'll work.
Yeah.
So that's why everything becomes situational.
Yeah.
Everything is related to, the application in which you're using it.
Yeah, I'm in a valley. I'm in Yakima Valley, and everything sits up on the ridges.
Mm-hmm.
All my repeaters sit up on the ridges.
Oh, that really helps.
Okay.
Unless you're trying to do simplex and talking to somebody on the other side of the ridge.
Yeah. Then I would need some height at that point.
Right. And you drive up to the top.
Yeah.
Does are the coils on the antenna bad to get our length versus just going straight?
What was the question?
Well, a lot of people use the coiled antennas just to get to that length. Is that less performance than just having the straight antenna?
Oh, yeah, much less.
Okay.
But maybe, if you have 20 dB of loss, that might still be acceptable. If you're 3 miles from the repeater and you don't care if you can talk to anyone else, that antenna is perfect. I'm line of sight. I'm 2 miles from one of our local repeaters, and it's on a hilltop. I can literally see it from my house.
Your rubber duck would be just fine.
I could probably take the antenna completely off, and it would still work. So,
I think Herb had a power-related question in the chat. Power limitation or something.
What was it? Let's see.
When
Practical number of added forward elements. Okay.
When you configure the Yagi, you showed multiple horizontal elements. I mean, why wouldn't you make a Yagi with 10 or 15 elements? There must be a practical limit.
You can start with 2, right? A single element is a dipole. You put one reflector on there, it becomes a directional antenna. You get a few dB of gain. You put one more director on there in front, you probably get up to like 7 dB of gain. It's not quite a linear relationship between adding elements and gain. But the problem then becomes, let's say that you're building an antenna for let's say 40 megahertz. or sorry, 7 megahertz, so 40 meters, right? I would love to have a Yagi on 40 meters. So here's my 40 meter Yagi, right? This is 66 feet long. Okay? This is 68 feet long. My boom is a quarter wavelength. This is 46 feet long. Right? Heavy, huge, right? I probably have to have supports that look like this, and maybe even that look like this, to keep the whole thing from crashing to the ground, right? That thing is heavy, okay? So now, instead of that, what would it take to make a 3-element? I would have to have another one like this, so my boom increases to 92 feet long. Right? I'd have to feed it right here. My boom length would be 92 feet. This would be probably 300 pounds. Okay, so there's a practical thing. So, not practical for most people. I mean, it's just not. But now you take a 2 meter Yagi. All right, so here's your driven element. This is 30, let's say 39 inches long. Reflector, 40 inches, then 38, 37, 37. And so this is, let's see, for 2 meters, this is a quarter wave. So this is about 20 inches, 20 inches, 20 inches, 20 inches. So a 5-element antenna would be about 80 inches long, which is about a little under 7 feet. Want to keep going? You can certainly get aluminum that can stretch that out a long, long way. I mean, Cushcraft makes an antenna called a 13B2. There's 13-element 2 meter Yagi. Doesn't weigh that much. It's probably, I don't know, 16 feet long. Certainly doable. I mean, and then you go to 70 centimeters. Everything just scales.
So how much gain do you get with each element that you add? Does it
a few dB.
Okay.
So, but for 70 centimeters, your driven element is what, half wave, so 35 centimeters. So about 14 inches, maybe 15 inches, then 13 and 12, and you can have all the way up to 12. And the spacing in between these is a quarter wave at 70 centimeters, so 17. So that's about 7 inches spacing. So you can build a 25-element Yagi for 70 centimeters and get a boatload of gain. Now, what that means is you have to be pointed exactly directly at somebody else, because if you're even just a little bit off, your gain is really, your beam width is really narrow.
It's always narrow, but does it become narrower?
Narrower the higher the gain. Because where are you getting extra gain from?
Sure, from the compression of the signal.
That's right.
Yeah. All right. You had a quick illustration of using a microwave dish.
Yeah.
To up your gain by 1,000 dB or something.
30 dB. 30 dB.
Oh yeah, 30 dB, 1,000 watts. Yeah, from 1 to 1,000. Would anybody complain about that?
No.
It's all legal.
Well, yeah, it's fine.
Okay.
We are allowed to run 1,500 watts of transmitter power. So this is another reason why you take a class. Because let's say you build a 1,500 watt transmitter and you somehow manage to get that 1,500 watts into the focal point of a microwave dish. What's your forward power? What's your effective radiated power in the forward direction?
In your example, it would be 1,000 times that.
Which is?
1.5 million.
150,000. Yeah.
No, 1.5 megawatts.
Okay. Yeah.
That would be great for moon bounce. What if that was pointed at someone's house? What if that was pointed at the house of one of your neighbors?
Would it kill their television? And
it would probably do a lot of things.
They might not have kids after that.
That's right.
Popcorn suddenly popping on the counter.
Yeah, exactly. There's Our privileges give us a lot of ability to do a lot of damage. That's another reason we take exams, like a lot of things we do are pretty safe. A lot of things we do don't necessarily have to be. So, all right, you guys ready for 5-minute break?
Yes.
Yep.
All right.
I have one more question.
Hold on
So
to it. Hold on to it.
Okay.
Bio break.
I don't remember any of this stuff.
Oh, yeah, you do.
No, I don't, honey.
Mona, yours isn't muted.
Oh, okay. Thanks.
What did you say? Squirrels have been back and forth. First, I put a handful of peanuts out there, and then I put a big handful of sunflower seeds. They keep coming back and coming back. That's about 4 feet from that, I think. Skinny one.
Annabelle.
She jumped on the telephone pole and went out of sight. Went off the pole. This morning almost fell off that 2x2. Not really, but sideways. And on. To me, it's amazing how they can hang upside down. If their little toenails are bent one way.
Mona, I sent you a question in the chat.
Oh. Hey, are you still planning on coming today?
Yeah.
All right.
Okay, I'd be there.
No, I know that stuff comes up, and I know sometimes if you're anything like me, it's last minute. So I just thought in case you forgot to say something or whatever, I would just call real quick and say, hey.
Hello.
Yeah, be there at 6.
All righty.
Okay, talk to you later.
Bye.
Okay, everyone. Let me take a look and see where we are. Antenna polarization. Okay, now we're into
So I don't quite understand this idea of pointing the antenna at somebody, because let's say there's not another ham close to me. I live rural. So where do I want to point my antenna?
I don't know who you're talking to. One of the things about a vertical antenna is that you won't be pointing it at all. A vertical antenna is going to be an omnidirectional pattern. So what you will get, let's say, okay, we're back into class. Let's say that you put up a dipole, right? Okay, so here's a vertical dipole. There's a vertical dipole, half wave. That's going to have a radiation pattern that looks like that. Right? Good so far?
Yes.
Okay. So that's going to have a radiation pattern that is nothing off the ends, which are up and down, and everything horizontal. That's exactly what you want if you're talking about a VHF FM antenna, because everybody that you want to talk to is along the ground. All the repeaters are along the ground. What you can do, really the only thing you can do, I mean, you could make it a Yagi, in which case it's rotatable. They're all vertical elements, in which case then your antenna pattern is squeezed in this direction, and then you'd have to have a rotator for it that would turn it. The other thing you can do is that you can take that antenna pattern, and by putting this over a ground plane, essentially what you're doing is you're changing the feed point impedance to 36 ohms, but no big deal. It'll still work just fine. You need a ground plane down here. This is what I have on my house. So I have a ground plane antenna that I built that cost me all of $5.
I am not seeing your whiteboard. I don't know why.
Make sure you click up top. There's a selection for meeting and another one for whiteboard.
Yeah, it says I'm seeing your whiteboard, but okay. I think it's starting to head that way, maybe.
Okay. Okay, so there's my antenna. Let me clear it. This is my antenna.
There we go.
This is my antenna. I have these tied together. This cost me $5 to build. It's a quarter wave. So to improve this antenna, what I would do is I would go to the next step of building it, which is I would do ground plane like that, and I would do.
When you say ground plane, you mean
like 4 wires, just 4 wires hanging down at a 45-degree angle.
But they're attached to the ground?
No.
No.
It's an elevated. This is elevated on a pole above my house.
Okay.
Or just like a piece of PVC. So this is a quarter wave, and then what you would do is a phasing element or phasing stub, and then a half wave up here. And what this does is that it ensures, because this is very small, it ensures that this section and this section are now radiating at the same time. They're in phase with each other, which causes them to have an additive pattern along the horizon.
And so I'm not sure, what is this, the coiled part that's attaching them?
So if you get like a Comet GP3.
Okay.
Look up a Comet GP3 and then a GP6 and then a GP9. They're basically a fiberglass radome that contains all of this stuff. And when you take it apart, essentially it's a quarter wave section at the bottom with a phasing coil, which puts the next half wave section in phase with the lower section. If you get a GP9, that's repeated again, which increases your gain along the horizon even more.
And how are you making sure that those other tails stay at a 45-degree angle?
Well, if you're getting one of the Comets, it'll have the ground plane built in. It'll be part of the antenna.
Okay.
But yeah, look up Comet antennas.
That's the one I use on my house.
It's a good place to start. They're built well and they work. They last a long time. All right. And
thank you.
Yep. Let's see. Interesting and propagation. Okay, so now we're into propagation. Okay, so propagation is how signals travel through space. Okay, so if we have two antennas that are within line of sight of each other, remembering that the Earth is curved, if they are within line of sight of each other, that's known as line of sight. That can cover long distances, especially if you're high up. I mean, an airplane has a line of sight of 200 miles in all directions. From a hilltop, not quite so much. And so let's say that you're on the ground pretty low, and you're dealing with a signal that's going out this way along the ground, and somebody else is over here. The curvature of the Earth, because radio waves don't bend very well, the curvature of the Earth is going to get you. Now, this is known as the visible horizon to here. Radio waves will typically often do this and curve along the horizon because they're a lot longer wavelengths than light. So radio waves will often curve along the horizon a little bit further than light waves. So the radio horizon is further out than the visible line of sight. Okay, so that is basically sending signals along the ground. So now we're going to talk about what happens when you get signals up into the sky a little bit. So we're talking at VHF and UHF at this point. Those signals, when they get up into the atmosphere, these will just go out into space for the most part. This is what we use to talk to astronauts. VHF and UHF. That's often 50 megahertz, 144, 222, 440 megahertz, and so on and so forth. Those will typically puncture right through the atmosphere, but not always. In the bottom layers of the atmosphere, which is where we live, in the troposphere, we can get temperature inversions, which can essentially create boundary layers which cause radio waves to essentially bounce back to Earth. So on very high frequencies that we would not normally expect propagation to work, this is typically not going to be reliable, but sometimes it'll work. This is known as tropo. There's tropoducting and tropospheric scatter. These signals will basically send signals back this way and also forward, depending on the way that it's working. And these can cover a distance of 300 miles on, for instance, 2 meters, like 144 megahertz, which is very strange to hear. It's typically due to, again, temperature inversions in the upper levels of the troposphere. But now we get up into stuff that happens above that. So we have the troposphere and the stratosphere, and above that we get into the ionosphere, which is usually clear to radio waves above 50 megahertz. They will typically just pass right on through. This is separated into multiple layers, the D, E, and F layers. And this is not to scale. The D layer starts at about 50 miles up. The E layer is typically about 100 miles, and the F layer is about 200 miles. And it extends all the way to the edge of space at 600 miles. Sometimes it actually bifurcates into F1 and F2. Usually during the day. So the D layer, its main function is to prohibit us from listening to AM radio stations, which are in the 0.5 to 1.5 megahertz range. What happens here is that solar radiation tends to cause a lot of ionization in this layer. This causes a lot of absorption of radio waves up to about 10 megahertz during the day, which is why we can't hear long-distance AM radio stations during the day. The E layer is very odd in a lot of ways. What ends up happening in the E layer is that sometimes you'll get something called sporadic E. You'll get heavy layers of ionization up here, heavy clouds, which will tend to refract signals back on 50 megahertz in particular, sometimes up to 144 megahertz, which is 2 meters. And these can cover distances of 1,000 miles. on VHF, which is a very strange thing to hear. The other thing that happens up there is that sometimes we'll get an aurora that occurs, and you can take signals largely on 6 meters, and you can actually bounce them off the aurora. And that is I did that for the first time last year in my entire life. We had a really big aurora here in Oregon. We all pointed antennas up at the North Pole, and on 50 megahertz I made multiple contacts by bouncing signals off the aurora. The signals by the time they get back are really distorted and sound very weird. Another thing that happens is that you will sometimes in that same region get meteor storms, meteor showers. And what happens is that when a meteor makes a streak, what's happening is that it is basically burning up and creating an ionized trail. It's creating a layer of electrons floating around up there. The signal that you send up will be sent back to Earth because it hit an ionized trail and it found a reflective surface. So we typically do that on 6 meters as well. So moving on from there, we are now into the upper levels of the atmosphere. For the most part, VHF and UHF are not particularly interesting at that point. If they made it up past the E layer, they're pretty much done. They go into space and never come back. But the higher up layers we have, when we start dealing with long distance communications, like really long distance, we get signals up into the F layer. And because it's so high up, we can get signals that cover large swaths over the Earth's surface to the distance of 2,500 miles at a time. And that's known as skywave. And so the area that we can't hear somebody on a particular band, this is known as our skip zone. The reason that it exists is because the angle up and down is simply too steep to make that path work. The other interesting thing about it is that we have signals that are headed up into space, and so what I'm going to do is I'm going to redraw this. I'm going to change the scale a little bit. Okay, so here's the Earth, and so here's the D, E, F1, F2 layers. Right, so we're really dealing with those F1 and F2 layers. So the fact that this kind of communications works at all is due to the fact that we have this big glowing thing in the sky called the sun. The sun generates a lot of different energy. The sun throws out a lot of radio waves, believe it or not. We don't typically use those. They just make a lot of noise. So we, for the most part, ignore them. They're fairly low energy. The sun also puts out a lot of ultraviolet, and it also puts out a lot of X-rays, along with visible light and heat, as infrared and stuff like that. But the ultraviolet and X-rays are of particular interest. The really hard rays will often, again, make it down into the D layer, which during sunlight hours causes us to not be able to hear anything below 10 megahertz. When we start to get the densities up here of the atmosphere are very, very thin. So what happens is that a lot of X-rays and ultraviolet rays pass right on through, but not all of them. What we end up with then is a few atoms for which an electron gets ripped off. Depending on the amount of solar radiation that's coming in, these can actually form into like clouds, and signals that head up there can refract back down to Earth and again cover distances of up to like 2,500 miles at a time. So because it's generated by the sun, and the sun goes through roughly 11-year solar cycles, we're pretty close to the top right now. We're a little past the top. The amount of solar radiation that rips electrons off has been very high, so our levels of ionization have been very high. Typically, the higher the level of ionization that occurs up here, the higher the frequencies that will work for covering very long distances. So this is known as our maximum usable frequency, or MUF. And this peaks during the day because at night, when the sun disappears from the sky, it's no longer generating large numbers of ions. And what can happen is that the atoms that have been ripped apart, they're able to reconnect with electrons, and the density of ionization goes down. So this changes from season to season, day to night. It's going to be at its peak. You're going to have your peak maximum usable frequency when it's the middle of the summer, in the middle of the peak of the sunspot cycle, during the middle of the day, or just shortly after noon. So we also have something called the gray line. We're not going to get too much into that, except to note that the difference between the line that exists around the planet between day and night can be of particular interest if you like talking over long distances, because you get very similar propagation along that entire line, and it can carry signals completely around the planet. I've actually heard that before. It's pretty interesting. Okay, let's see what's coming up next. Okay, so we're going to talk about a couple of interesting things that can happen when you're on the air. Okay, number one is picket fencing. Okay, so what we get with picket fencing is the fact that there are times when, because of two different paths that get followed by a radio signal, they will either be additive or subtractive when two different signals get there at two different times. If they're subtractive, you'll hear a weak spot, kind of like someone will go away. And when they suddenly add back together, the signal will be very strong. So one thing that if you have not noticed it before, if you haven't gotten to be on the air much, is that when you listen on a handheld radio, this is, let's say, on the 2-meter band. What's the wavelength on the 2-meter band, everyone?
2 meters.
2 meters.
2 meters, excellent. What is that approximately in feet?
6 feet.
About 6 feet, okay. So what will happen sometimes is that you will be, let's say, in a room like this, and the repeater is somewhere way out over here in the distance. And for whatever reason, there's, let's say, a truck parked here, and some of the signal bounces off this way and goes this way. Some of it goes this way. This is known as multipath. What will happen is that, depending on where you are, you may be at a point where the signal here that looks like that, there's a signal that's here, but it's delayed. When they get there, you get this combining with this. You add those together, and what do you get?
A null spot.
You get a null. So in order to change that, what you might have to do is move so that one of the signals has to go, let's say, a half a wave further than the other one was. So you might have to move a little bit. And it seems counterintuitive, but sometimes a spot that is like over here now receives those two signals, and this one is coming in down here, and this one is coming in right here, and they're in phase, and all of a sudden you've moved 3 feet, and what happened? Everybody can hear everyone. And if you can hear people, they can hear you. So it's very important to understand that the difference between a bad spot and a good spot might only be, especially on 70 centimeters, 2 feet, a foot. You know, you moved just a little bit and you moved into a good spot or a bad spot. If you're driving a car, you might go from good spot to bad spot to good spot to bad spot very rapidly, which is known as picket fencing. So that's known as multipath. If we're doing digital, multipath will generally create higher error rates. If you're using a directional antenna, let's say a Yagi, sometimes it might not be a bad idea to bounce a signal off of a mountain or off of a big building. I know people who've done that. They used Mount Hood as a reflector. Let's see. What else? Okay, knife edge diffraction. Sometimes aiming a signal over the top of a mountain, especially one with a very sharp peak, can actually cause it to bend back down and refract down to the other side. That's known as knife edge. VHF, UHF, and microwave signals. Vegetation. We have noticed, even here, that the difference between winter and summer is rather significant because leaves are reflective. They also contain water at certain frequencies. They absorb a lot of radio waves. So vegetation can cause absorption of signals. Okay, if you have cross polarization of antennas.
Hey Scott, just real quick, a quick story on that. I had that common antenna,
Mhm.
and it was working really well. I just put it up during the end of winter, and when it was working well, and then suddenly the trees started getting leaves, and I was losing everything. I couldn't hardly hear, couldn't transmit anything.
Isn't that amazing?
So I had to raise it up about double what it is, and then I'm back in business.
Yeah, isn't that amazing? Okay, so we have a horizontally polarized antenna. The electric field is going this way back and forth. When it hits this other antenna, which is vertically polarized, it's trying to jiggle electrons back and forth. But what can happen here? What happens in here? The antenna is very, very narrow because it's vertical. You will lose, typically, again, 25 dB by not changing your polarization to match. Sometimes that's good. Most of the time it's not. Let's see. Meteor scatter. The most common band to do meteor scatter is 6 meters. Tropospheric ducting. Rain. Okay. Rain. Does anyone have satellite radio in their car?
I do.
What happens when it's raining?
Yeah, it gets a lot worse.
Gets a lot worse. That's because microwaves tend to get absorbed by water. Rain is water. There you go. If, in fact, you are on the high frequency bands, the rain does absolutely nothing to you. On VHF, it typically doesn't affect you either. Okay, we covered HF propagation. We covered antennas. I'm just making sure that we're okay. All right, so we are on now page 50. And is it okay with everyone if I go a little long today? We've had a lot of questions, and I just want to make sure we have enough time to cover everything.
Yes.
It's okay? Okay.
Yep.
Okay, feed lines and connectors. Why is coaxial cable the most common feed line used for amateur radio systems? And that is because it is cheap, it's easy to work with. One thing that you have to do with coaxial cable, okay, this is the answer to everything. Most coaxial cable is 50 ohms. Coaxial cable can also typically be direct burial, which means you can just bury it in the soil and it'll be okay. You can also just put it out in the sunlight and hang it on a tower. Now, there's one thing that will destroy cable. Who knows what it is?
Moisture.
Moisture.
Water.
Yes, water intrusion. So if you're doing cable, that is the answer to literally every question with regard to coaxial feed line. Cable gets destroyed by water because water gets in there and it corrodes the copper, and then it doesn't work anymore. It also fills the area where the dielectric is. So when I mention dielectric, I'm going to draw a piece of coaxial cable. This is coaxial cable. Okay, so we have a center conductor and we have the outside, which is a shield. The area inside here, which is the hatch, this is a dielectric, which is basically an insulator. It's usually polyethylene. It could be air. It could be any number of different things. The spacing is important because the spacing and the dimensions and the ratios of everything determines the characteristic impedance. You have this gap. Excuse me. You have this gap. The gap between two conductors is a capacitor. The fact that this is a piece of wire is an inductor. So you can actually model a piece of coaxial cable like this. No, not like that. And then you can do multiple different segments of it, and since it goes on forever, it has impedance, but it doesn't actually cause any significant loss other than because of its resistance. So the bigger the cable is, the less lossy it is. So if I have the same proportions from one cable to the next, it will have the same characteristic impedance because they're proportionally the same. So I could have this cable, I could also have this cable. And they would both be 50 ohms if they were built to the same proportions. Which one do you think will handle more power, top or bottom?
Bottom.
Bottom one, because it's physically bigger. The conductors are bigger. It won't burn up as much heat because of ohms, of resistance. That causes heating. The bigger a wire is, the less resistance it has. So the more power you can put through it. So now, again, if I get water in this, let's say I put a connector on this. What happens if I leave a little gap right there? What's going to get in if I put it outside?
Water.
Water, guaranteed. Water gets everywhere. So water will get in there and it will destroy the cable and it won't work anymore. What happens if I leave this out in the sun and it's not UV proof?
Gets cracked.
It gets cracked. Okay, it gets cracked. Then what goes through the crack?
Water.
Water. Okay, so the answer to every single question about coaxial cable is water. That's the most important thing to remember. Coaxial cable, it's either water or cracking or bad connectors, which cause water to get in, and then it gets ruined. Another thing you can do is you can use air-insulated hardline instead of this material right here, being like a solid plastic. What you would do is you would seal it off, especially if you were, let's say, operating a TV station and you were running 50,000 watts. And you didn't want any significant losses because that costs a lot of money and energy. So what you would do is you would seal the whole thing and pump it full of nitrogen and keep it pressurized. Because what does nitrogen have? It has no water. So it keeps everything dry and doesn't allow the cable to get destroyed. It also might be that you are using, let's say, quarter-inch cable, quarter-inch diameter, or half-inch, or 6/10 of an inch, or 1.5 inch, or 6-inch cable. All of these could be 50 ohms. Which do you think is the hardest to work with?
Probably the biggest stuff because it's harder than flex.
Yeah, you can't even bend that in a 20-foot spool.
Hey, Scott, you need water.
I know.
It's the answer to everything, right?
Yeah, exactly. We once had 1.5-inch hard line, as it's called, and it came, somebody drove it down to us in a 10-foot spool on a truck because that's as tight as you could bend it. This stuff
Scott,
is also...
when would they... Sorry, go ahead.
This stuff is also insanely expensive. So what would be the benefit of using it?
It'd carry more power.
Yeah. You were getting there, though.
And it uses...
You were almost there. You were going to say it.
Less loss.
Less loss. Yes.
Yeah.
And in fact, here you go. Here's a convenient chart. Hopefully this will open and I can... come on. Darn it. That wasn't the one I wanted to see. That's the one. Come on. There we go. Okay. So remember I said that the cables are rated in dB of loss per 100 feet?
Yep.
Here you go. Notice that it changes by frequency and it changes by cable. So the cable that you use at 80 meters, which is 3.5 megahertz, is very different than the cable that you would use at 440 megahertz. Because let's say you have a 100-foot cable run and you have 6 dB of loss in your cable. If you put 100 watts in, how much do you get out at your antenna? What's 6 dB, everyone? It's 3 dB and 3 dB.
Yeah.
The first 3 dB cuts your power by
half.
And the second 3 dB then cuts that by
half.
Okay,
Half
so that's
again.
a quarter. So your 100 watts is now cut down to 25 watts. Where's the other 75 watts?
It's in heat.
It's keeping the cable from getting ice on it. Yeah.
Yeah.
Right? That's not a very good use of your power, is it? So that's why, TV stations operating at a gigahertz either have the transmitter way up on top of the tower or they have really big low loss cable going up to the antennas. And these are, published. Every manufacturer that makes cable publishes these numbers to allow you to figure out what you want to use. Okay, ultraviolet light. Okay, a PL259 versus an N connector versus an SMA. Okay, so what we're going to cover now is RF connectors. Okay, and I'm going to, oh, perfect. Okay, let me share this. Yeah, sometimes the web is good for something. Okay, so these are your typical RF connectors. Notice there are many, 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 many different ones. See all of those? There's so many different ones, it's insane. How do you pick? How is it possible to pick? Okay, this one right here is known as a PL259. That is a UHF connector, which stands for Universal High Frequency. Very bad for UHF frequencies. Extremely bad. They are good to maybe a couple of hundred megahertz, and that's it. But we find them all the time on high-frequency radios. This one right here, for instance, that is known as an N connector. Those are waterproof and good into the many gigahertz range. So for a lot of higher frequency radios, microwaves and stuff, you'll find N connectors in use. These most handhelds these days come with these. These are known as SMA connectors. They are also good to many gigahertz, but typically because they're smaller, they can't handle as much power, which is why for a higher power radio, you will end up using like the one on the right. Let me go back and find a good N connector. Ooh, that's a good N connector. So those are again N connectors. Double protected and waterproof. Okay, next we are on to standing wave ratio. Okay, standing wave ratio in the simplest terms is a measure of what kind of signal you are getting out compared to how much is bouncing back. A standing wave ratio that is perfect is 1:1. Right? It's a measure of how well a load is matched to a transmission line. The load being the thing using the power. We would typically call an antenna a load. So we can actually look at our standing wave ratio. We can calculate it by looking at our impedances. So what are most coaxial cables that we're going to use? How many ohms?
50.
50.
50 ohms, okay. And this goes up to an antenna. I'm going to make it like a black box. And this antenna has an impedance of 300 ohms. If we were to just connect those, standing wave ratio is literally the bigger one divided by the smaller one. That would be a 6-to-1 mismatch. That is a terrible mismatch. And what ends up happening is that whether this is 8 ohms, that would also be 6-to-1 because 50 divided by 8 is approximately 6. Those are both terrible. What would happen is your signal would be inverted or not, but you'd have a little bit of signal going out and a lot of signal bouncing back down. So if your transmitter was here and you had, let's say, 100 watts going out and you had 60 watts coming back, how much power shows up in your transmitter? It's actually a lot more than 100, isn't it? Because you have 100 watts that's being generated going out and 60 watts coming back. If those are in phase with each other as far as voltages go, you could actually generate some voltages in your transmitter that can actually destroy your transmitter. So in order to prevent that from happening, most transmitters have what's known as a fold-back circuit these days. And they see how much power is coming back. And if it goes too high, they purposely limit the amount of power being generated so as to not fry the transistors with the signal coming back. Because you don't want to do that. So that's intentionally folding back the power output. A 1-to-1 is perfect. 2-to-1 is, okay, you're still doing okay. 4-to-1 is a significant mismatch. So one of the things that is frequently used to remedy these issues is that you have something called an antenna tuner. So here's my transmitter, and this connects to a tuner. So this looks at 50 ohms right here. The antenna, the transmitter is designed for 50 ohms. The input of the tuner is designed for 50 ohms. What will happen is then we have some kind of questionable signal, questionable system out here with some unknown antenna, and inside the tuner, what we have is a circuit that looks like this. So looking at it, so here's the in and here's the out. This is now connected to the outside something. That's a symbol for an antenna. And this provides us some question mark impedance. This question mark is now in series with this capacitor, which is then in parallel with this inductor, which is then in series with this other capacitor on the left-hand side. We can vary all three of these. Notice that these are all tunable. They're all variable. And we can find, in most cases, an impedance match that, by changing those values at a given frequency, makes this look like 50 ohms. Well, if that happens, the transmitter sees how many ohms?
50.
50 ohms. Is the transmitter happy?
Mm-hmm.
Yes.
Do you still have a problem?
Nope.
No, actually you do. Because you don't know what kind of a mess you have out here. You still have power going out and a lot of it bouncing back, which then gets here and it comes back up, and then it comes back down, and it comes back up, and you basically end up with recirculating power going up and down and up and down and up and down. The transmitter's happy. But what's happening in this cable? What do you think?
It's heating up.
It's heating up. Because what do you know about every piece of cable? Remember that table that we just looked at? dB per 100 feet, right?
Yeah.
A certain amount of loss in dB per 100 feet. If this is 100 feet long and and those signals are making 10 passes, for instance, that means they had to go through it 10 times. And every time it goes back up to the top, a little bit comes out and a lot of it goes back. So a really bad piece of cable basically burns everything up as heat. And it can actually make your SWR look not so terrible because it's resistive. It's going away as heat. So it's it's an interesting situation. If you have a mismatch, what this tuner allows you to do is protect your transmitter and still be able to run. And it depends if typically the transmitter will, the tuner will have an automatic tune setting, which you can select. Very often I don't use it. I use an external tuner, which I can tune by hand. I still like to do that. I like to know what's going on.
And so by you having to tune it, then you know how much it's coming back to you?
Yeah, there's a meter inside the tuner, inside the external tuner, that will show me exactly how much power is going out and how much is coming back. Now, what it doesn't do is it doesn't really tell me what's happening way up here at the top. I don't really know. Ideally, this is a 50 ohm piece of coax and I have a mismatch way up here at the top and I install a tuner up here at the top. That would work better. But what are the problems with doing that?
Water.
Water. It's outside. Yeah. So it has to be completely waterproof. And because it has to run on some kind of power, there has to be power sent up to it as well. So not only do I have a piece of coax running up there, I probably have a control cable running up there, or I've superimposed power on my coaxial cable, which you can do, by the way. How do you think you can get away with that?
You got to filter it out at the top, though.
Yep. You have a filter which takes the RF and sends it one way, and the power and sends it the other way. That's exactly what you do.
Also, if you put the tuner up there, that's not protecting your transmitter because you have to know you have to tune it.
No,
so you could turn it on.
It'll still be okay. If it's up there, then the assumption is that the tuner is not down here at all, and you're just you're gonna set it up to run automatically, and essentially you've got a good match all through here because you built this all as 50 ohms. So if you have a mismatch up here, you can let the tuner handle it, and since it's right at the antenna, it'll usually do a good job. It basically acts as a transformer.
Scott, I heard you say you use a tuner. Do you get your antenna close without it and then use that as more of a kind of, tune it even better?
Personally, no.
Okay.
Because, so let's take a look at this. Everybody, we're going into this, so I might as well go into this, right? So, okay, these are the ham bands. This is in megahertz, 1.8, 3.5, 7.0, 10.0, sorry, 10.1, 14.0, 18.1, 21.0, 24.9, 28.0, and also 50.0, right? These are in megahertz. How do I get a single antenna to do all that is actually, functional?
You can't.
No, you can't. But I do. I use one, and the way that I do it is I have a tuner right here, and it has a transformer in it, which has a 9-to-1 or 5-to-1 or something like that. So the assumption is 50 ohms here, and then this goes through ladder line instead of coaxial cable, which has an impedance of 450 ohms, but very, 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 very low loss. Exceedingly low loss, like 1 dB per 100 feet. Really low. So when it gets up here, this antenna is essentially random length. It's not totally random, but it's pretty close to random. I mean, it's probably perfect on one frequency. I think it's cut for 80 meters. But on every other frequency, it's either a little bit short or a lot long, which means it's acting weird.
Yeah. On those other frequencies.
Yeah, it's acting like, I don't know, whatever it is. Yeah. But what it does is so my radiation pattern is definitely not directional. It probably is largely omnidirectional on a lot of bands, which I'm actually okay with. But what I can do is I can use the tuner, and because the loss is so low, like 1 dB per 100 feet, I don't really care how bad of a mismatch it is right here. I really don't. It's
because all you're tuning out now is just the loss at the top and nothing else.
That's right.
Okay.
So I let the tuner do the work. This is also known as a doublet, I think. I don't know. I just sort of came up with it myself. A lot of people use it, I guess. And if you, depending on who you are and what you want to do, it may not be. You may want to put up a 6-element antenna that does all 6 and is resonant on all of them. This is not resonant on most bands, but I can get it to work. And remember when I said that the perfect antenna, it might be that why you can get away with the 3-inch long antenna, and that's because it's in a good spot.
Yeah.
I live on a 450-foot hill. So does it really matter? Sure, it would be better if I had a big antenna on a tower, but I probably don't need it because of where I am. It makes up for a lot of deficiencies.
Yeah. Okay.
What are the chances of having problems with like you were saying, your antenna's on top of your house?
Mm-hmm.
Do you end up with radiation that radiates into the house?
Probably. I mean, it's at a low enough power level and a frequency where it's really part of what we have to do is we have to go through RF safety tests. That's another thing that's covered on the exam. You actually have to do a radiation exposure test with, I might as well bring that up now. And I think we've actually pretty much covered everything there. A directional watt meter is used to measure SWR. RF power meter, where it goes. An antenna analyzer is something that you use to tune an antenna. Antenna tuner is a matching device. A dummy load is a device that acts like a fake antenna. It's a 50 ohm non-inductive resistor mounted on a heat sink, so it turns RF into heat on purpose. Okay, so what was the question one more time? Because I think
I was wondering. I was wondering about radiation coming back into the house.
Yeah. Okay, here we go. So
because my radio room is going to be right on the side of the house where I have an antenna pole that's higher than the house where I'll put my antenna.
Yeah, you'll be fine. But one of the things we have to do is notice this FCC OET Bulletin 65. That's an RF exposure test. So we also have this thing called essentially you can use a calculator to calculate this. Hint link, RF exposure. There we go. Okay. So somebody give me your scenario. Where it's going to be. Average power. Was that Luella or Luetta?
I don't know the answer to
Time
that.
average. What kind of transmitter? 25 watts?
Yes.
Let's say worst case. So let's say you're net control for something and you have a 50 watt radio and you're operating half the time. 25 watts. Okay? Notice how the antenna gain is measured. This is in dB compared to an isotropic radiator. And let's say it's a Comet GP6. So what we're going to do is we're going to look up Comet GP6 gain. Guess what it's going to be measured in?
Decibels.
It's going to be in decibels, and it's going to be probably dBi or dBd, depending on what it is. And let's see, where's the gain? Instructions. It's probably going to be there. Maybe. Okay, here we go. Gain right there. dBi, 6.5 dBi on 446. We're going to say 9 dBi. Okay, dBi is isotropic. dBd is compared to a dipole. They're 2.2 decibels different. Isotropic radiator doesn't matter. So we're going to go in dBi though. It says, because enter it in dBi. We're going to use 9.0. How far away are you going to be from the base of the antenna when it's mounted? Total distance.
6 feet.
6 feet. Is that all? That might actually be a
pretty-
problem. Let's find out. Here we go. You are still safe according to the calculations. So, because here's the power density based on, you know, spherical distances and all that other stuff. If you are in a controlled environment, you're good up to 1.47 megawatts or milliwatts per square centimeter. Uncontrolled, which means somebody just walking through who doesn't know what you're doing at all and hasn't been warned. They're good up
Your
to 0.3.
distance is in meters, though.
Oh, yeah. Okay. Well, you're right. Oops. 1.8. This might change things a little bit. Oh, okay. So it's pretty high, but you're still below the level in the controlled environment. And for an uncontrolled environment, notice that you are now exceeding it. So essentially, you need to inform people if anybody can walk by who is not educated as to what you're doing. That's what uncontrolled means. So let's go
Right,
with,
but still, that's too close for me, it seems like.
it says it's legal. I would try to move it away. Now, the other thing that can happen is to say, what is your actual average power? Are you really going to be operating 50% of the time?
No.
No. So let's go down to 144 megahertz and see what happens. And it's similar. Your exposure limits are a little bit less. But let's say that let's say that you're actually transmitting a quarter of the time. Okay, so you're still not okay for uncontrolled, but you're fine for controlled. And let's say 9.0 for 440. Let's see if that gets any safer. It's the same result.
Interesting. Okay.
Yep. But we are actually required to do this.
Hey, Scott.
Yeah.
I didn't catch what's the levels we're trying to stay below?
Right here, whatever that minimum permissible exposure limit is.
Okay.
And there are multiple different calculators out there. They all essentially, notice this FCCOET bulletin 65. That's basically this is a mathematical implementation of what the FCC says you should do. You could also walk around while you're transmitting and take field strength tests. That takes a lot more effort. And the other thing is, when you say that it's 6 feet away, is it 6 feet vertically, or is it over and over?
It's over and up. So if I'm sitting at my desk, it's going to be maybe 6 feet to the right and then 6 feet up from there.
Okay, so Pythagorean theorem, square root of 70. So that's actually about what, 9 feet?
7.6.
Yeah, 8.5 feet. So that'll change the distance a little bit.
Okay.
But that's
Thank
why
you.
that's why we go through the process of this, to understand what's safe and what's not.
Scott, could you just add a section of pole to it?
Sure.
In section?
Absolutely. And if you can add a section of pole to it, that would actually improve your performance as well, because it's up higher. Your line of sight gets bigger.
Height is might.
Okay.
What if you have a 50-watt radio inside a car? Do you need to warn people if you're using it?
Are you operating all the time? You know, it really comes down to what your duty cycle is. You know, like if I'm in the car, I mean, a 50-watt radio is going to have a 5-watt setting. Personally, unless there's a really good reason, I'm running 5 watts. For that very reason. You know, I mean, legally you can run 1,500 watts. You know, I might not want to expose anyone to that, including myself. So, all right, shall we do one more section? Everyone?
Yes.
Yes.
One more section. Okay, one more section. We're going to do one more section. All right, so we're into signals. and modulation modes and signal bandwidth. And this will actually give everybody something to look at overnight, as if there's nothing to look at overnight, right? So has anyone ever heard of a web SDR?
Yep.
Has anyone ever really used a web SDR?
Nope.
Okay.
A normal SDR.
Yes. A web SDR is a software-defined radio. That's what an SDR is. That has been essentially tied in so that there's an interface on the web that people can then use to control it. And these are wonderful little things to use because they give you experience and practice listening to radios and tuning things and understanding how that all works. And I'm going to point this thing east. All right, here we go. And I'm going to have to... Did I share the audio?
Yep, 73.
Yes, you did.
Oh, good. Okay. So notice what we're looking at right here. What we're looking at here is the entire 20-meter band in one fell swoop. Okay, so what we're doing right now, let's take a look over here. Okay, so what we're able to do here is look and see that right here on the left-hand side, that little vertical stripe is the center frequency. That's the dial frequency. And obviously we're listening to upper sideband because we're listening on the upper part of that frequency. An AM signal produces an upper sideband and a lower sideband. If I were AM being amplitude modulation, if I were to switch to the other sideband, what would happen is I would see the signal try to decode something on the other side. So here's lower sideband. Now, one thing that's interesting, if anyone has ever noticed this before, if you try to listen, you will hear that. And notice we can't understand any of it. The reason that is because upper and lower sideband are symmetric signals around that vertical line. But in order to save energy, this is an amplitude modulated signal, meaning basically the louder you get, the wider it gets, the higher the frequency gets. And ideally, in an AM signal, this would be a mirror image on both sides of that stripe, that little vertical stripe. But because it's single sideband, there's been since 1956 a desire to only transmit one of them because otherwise it's wasteful. I mean, you're wasting bandwidth, which is a resource, and you're wasting power because you're sending two copies of the same thing. So what we're able to do here is take a look at signals. This is one of the great things about an SDR. So let's say over here.
Kilo Quebec 4, Kilo Lima Mike.
Okay, so again, these are single sideband. Okay, so now what we're going to do is take a look at another part of the band. We're going to go down to the digital band. And notice that we still have that selection set up, that big yellow area. That is 3 kilohertz wide, 3,000 hertz. A single sideband signal is about 3,000 hertz wide. If we zoom in, how big is that signal that we're looking at right now? 14,097 to 14,097 200. It's 200 hertz wide. That's a digital signal that takes up about 1/15 as much space. We're going to take a look at another one. So that whole signal takes up about 500 kilohertz. It really could take up a lot less. That's Morse code. So let's take a look at another one. Oh, here's one.
Is that 500 hertz or 500 kilohertz?
500 hertz.
500 hertz, okay.
Okay, so now we're looking at a mode called FT4. This is a digital mode. Notice each one of those vertical stripes is about 100 hertz wide at most. Each one of those is a unique signal from somewhere that contains unique information. We'll take a look at FT8. These are packed in there so tightly that you really can't even see the fact that they're different ones. But there's about 30 signals packed into that one space. If I had a decoder, I could decode. If I had a decoder running, I could decode it all. We'll take a, there happens to be a contest going on right now, which I will be doing as soon as this class is over today.
Are all these streams audio?
Well, when you say audio, they're RF.
Okay, but are they someone speaking?
This? Well, it's Morse code.
Okay.
I know Morse code.
Not voice. Yeah.
Now, Scott, does this SDR do digital as well as analog?
Yeah, well, yeah. I mean.
Okay.
I mean, these are all digital modes up here.
Scott, is this a software interface that's on your computer pointing to something?
No.
That you have in.
This is just web. You type websdr.org.
Okay, so I can go in and go look at this.
Yep. I recommend that everybody does to get some experience listening to it if you haven't done it. So here's here's one of the things that comes up. Okay, so what we're listening to right now, you probably hear 4 or 5 signals at the same time. Every different pitch is somebody sending something different. Okay, so one thing that we are able to do with a narrow bandwidth signal is we can do this. PW2F. We can filter the heck out of it. Now remember we were talking about filtering? This is a bandpass filter. This is what filtering is for. We went from this to this. We're able to eliminate everything else around it that we don't want to hear. So this is known as selectivity. This is a very selective receiver because of the filtering that's built into it. And most HF radios today will have this.
And this is facilitated by someone having a radio, plugging it into their computer, and allowing us to have
us to see the whole stream.
Okay.
So, and the web interface that we're looking at right now actually has the. I assume it takes the stream and allows us to convert it into audio.
Mm-hmm.
So, anyway,
these are all analog frequencies. That's why I was asking about the digital, Scott. I wasn't sure if this also monitors digital as well as the analog that you can listen to.
I mean, if it's there, it hears it. Whether it's digital or otherwise doesn't really matter.
Okay.
It does. There's no difference. So.
I've been a Motorola tech for many years. That's why I was asking, because the DMR, DMR and analog conventional is different. Yeah.
Yeah, you can listen, but you won't be able to decode it. So, you know. All right. So, mostly, what type of mode? I'm just going to share my screen, and then we'll be done. What type of mode is typically used on VHF and UHF repeaters? That would be FM, which is frequency modulation, or PM, which is phase modulation. For packet radio is digital over voice using FM. We use it all the time. Amplitude modulation, that is basically taking the signal strength and making it bigger based on the baseband signal, which is my voice. Single sideband is a single side of an AM signal. For weak signal on VHF and UHF, believe it or not, we use single sideband. Not FM. FM has a very nasty effect, which is known as the capture effect. Two signals that are overlaying each other will typically wipe each other out, and that's because of the nature of FM. It's also true that FM typically requires a good amount of strength, or else it gets really scratchy really fast. The break point on the high frequency bands is 10 megahertz. Below that, we typically use lower sideband. Anywhere above that, literally anywhere above HF, VHF, and UHF is upper sideband, and that's a lot of it comes from when it was originally generated. It was easier to do it that way. Single sideband, an FM signal is typically 10 to 15 kilohertz wide. A single sideband signal is about 3 kilohertz wide. A VHF repeater signal, again, 10 to 15 kilohertz wide, which basically means that it really uses up 5 times as much bandwidth resource as single sideband. But what you get is higher clarity. Let's see. Approximate bandwidth of AM fast scan TV is 6 megahertz. Not kilohertz, megahertz. So looking at the frequency charts, how many different places do you think you can actually run fast scan TV? What do you think?
When you say places, what do you mean?
Like different frequency bands.
Oh.
60
So now
meters.
it's time to open this chart up. Because everybody has this chart. All right, so you need a 6 megahertz wide swath to run fast scan TV. 10 meters goes from 28 to 29.7. That's only 1.7 megahertz for the whole band. Amateur fast scan is light blue. The first place it shows up is on 70 centimeters because it's the first band that has enough bandwidth to actually run high data rate TV. And there's only 2 channels because it takes up so much room. Notice on the 900 megahertz band, we actually have 3 TV channels. And on 1.2 gigahertz, we actually have 5 whole TV channels. It takes a lot of space. Okay, NTSC is fast scan color TV. Yes, we do fast scan color TV. We also do slow scan TV, which is like typically 2 frames per second. It takes a long time to paint a picture, but it also doesn't take a lot of bandwidth. CW is Morse code. The narrowest bandwidths are typically CW, and there's also something called PSK31, which has an even smaller bandwidth of roughly 31 hertz. Very, very narrow, and it's fast enough that you can type keyboard to keyboard. And an electronic keyer allows manual sending of Morse code. Electronically, it's a lot faster and easier. PSK31, packet radio, IEEE 802.11, that's also known as Wi-Fi. FT8, those are all digital modes. Packet radio transmissions. Packet is kind of cool because there's actually error detection as opposed to most other modes that are analog. Packet is digital. It has automatic repeat requests. If something gets lost, it says I didn't get it, and it tells the other station to resend it. APRS has anyone ever played with APRS? Essentially what it is a combination of VHF radio, GPS, and mapping. Allows you to put people's locations and speeds and things like that, weather information on a map. So GPS data, text data, weather data, they can all be on a map with using APRS. PSK31 is phase shift keying. PSK31 is literally only 31 hertz. It's incredibly narrow and still fast enough to send good amounts of data. DMR, somebody mentioned digital mobile radio. DMR is a protocol that allows radio to run over digital channels instead of analog. You can use a single repeater channel and multiplexing, where you basically split time slots, and it allows 2 different people to have 2 different conversations at the exact same time using digital signaling. WSJTX, that was when I mentioned FT8, FT4. Those are part of the WSJTX suite. We use those for weak signal, meteor scatter, and moon bounce, as it's called. FT8 is a digital mode capable of low signal to noise operation. It's part of that WSJTX protocol. And mesh. Has anyone here ever done any mesh stuff, Meshtastic or anything like that?
I have, yeah.
Yep.
Okay. So Meshtastic is 915 megahertz, if I remember right. We have a lot of people here in Eugene who do a lot of Meshtastic. Those same people, they also do a lot of ARDN, Amateur Radio Emergency Data Network, which is essentially a parallel RF Wi-Fi network over long distances. So you essentially start with Wi-Fi routers and you hack them up and make them behave like ham radios. All right, safety, 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 safety. I can put this in a nutshell. Never change out a fuse with a bigger fuse. So if a 5 amp fuse blows, don't put in a 10. Don't put in a 20. Electrical current flowing through the body will cook you, so watch out for high voltage. If you're operating near power lines, you need to stay at least 10 feet away, and that's including if stuff falls. It needs to be at least 10 feet away from the power lines because arcing can happen over long distances. The black wire is the hot wire, the white wire is the neutral, and the green wire is the ground. You should ground everything in your station, if at all possible, to the safety ground, which is the electrical ground in your wall. A fuse removes power in case of overload. And let's see, there should always be a fuse placed in the hot conductor circuit. Inside a power supply, capacitors can stay charged up, especially high voltage power supplies, like for vacuum tubes. 12-volt storage battery, I had a friend who had this happen once. There was a spark near his almost completely discharged car battery, and the thing blew up due to a hydrogen explosion. So you need to be really careful. And if you discharge a battery too quickly or charge it too quickly, it can overheat or outgas. Okay, antenna and tower safety. Most people never have to deal with this. But again, stay 10 feet away from anything. Never go up on a tower by yourself. Always wear proper harnesses so that in case you fall, you will not hit the ground, because it's not the fall that kills you, it's the sudden stop at the end. Don't climb a tower by yourself, because you could get stung by a bee and pass out, in which case you're just hanging there and nobody knows. Don't use a utility pole because it's not yours, unless it is yours, in which case you need to make sure that there's no high voltage lines on it. When climbing a tower,
what are we considering high voltage?
anything that will kill you.
Well, it'll all kill you.
You know.
Okay, maybe not these 9 volt.
Yeah, yeah. When climbing a tower, always wear a headgear. You know, a hard hat, tie-offs, approved climbing harness. Don't ever go up without a helper. Also, bring a spotter, somebody who, if you're trying to manage a really, remember that 40 meter Yagi I mentioned? That thing has a really wide swing. I know somebody who was killed when he went to go move one off of a guy wire. It got hung up on it, and the other part of the antenna was touching a power line, and he died. So there was nobody who was there to say, hey, stop, you're about to hit that power line. And that was the last thing he ever did. When using a crank-up tower, don't climb it unless it's retracted or you have safety devices locking it in place. A safety wire through a turnbuckle. Turnbuckles tend to vibrate in the wind and loosen. You want to avoid that. Follow local electrical codes. If you're putting up a tower or an antenna, you need to use ground rods, one for each tower leg, bonded to the tower and each other. They need to be 8 feet long if at all possible. And when installing ground wires, short and direct, and no bends. Lightning does not go around right angles very well. How should you bond them together? You use a heavy wire or conductive strap. Give it as much surface area as you can. And the lightning arrestor goes in a coaxial feed line as close to the building entrance as possible. and then it gets tied to a common plate, which gets tied to a ground rod. That actually will, if one of your antennas gets hit by lightning, hopefully it will cause the lightning arrestor to arc internally and then shunt the power. Instead of into your station, it will hopefully shunt it to ground. All right. How about that's it for today?
Yeah, sounds good to me.
Tomorrow we'll do RF. We'll start at RF hazards and radiation exposure, which is on page 70. See,
Scott, thank you very much. This has been great.
Thank you.
Appreciate it.
I enjoy doing it. And I know it's a lot of material. And
thanks, Scott.
As soon as I have the video, I'm going to send it to everybody. And yeah, we'll see how much my wife lets me get away with. And I mean, I actually just spent the last 2 weeks on the road. I got home Thursday night. So, and I have a piece of equipment in Texas that I need to work on because it's apparently dead. So.
Thanks again,
always
Scott.
work to do, yeah.
Great job.
If you've got any questions, please ask. Send me an email or do it right now.
I got one real quick one. How do you go back and download the book that you're reading? I know it's on the HRE, test quiz stuff, but where you had all the